So welcome everybody. This is the first workshop for WiseML, and we are happy to see everybody here. Although now it's the first workshop, but actually in the last 2 years we had this workshop virtually. So welcome everybody, and thank you for all the authors, reviewers, conference and the workshop community support to make this workshop happen. And I believe this will be a successful event. So people will come here to meet friends, to exchange ideas. And I also want to thank the keynote speaker, John Davis from DARPA. So he will give a keynote talks. Title is Accelerating AI for Automation for Uncertainty Environments. I think this will be a very interesting talk. Let's welcome him.
Thank you. Thank you. Good morning, everyone. Really appreciate the opportunity to have a dialogue with everyone today, and very honored for the invitation. A little bit about me before we get into the talk. I am a program manager in the DARPA Microsystems Technology Office. I joined DARPA a little over 2 years ago. And my research area focuses on cognitive RF systems, as well as associated architectures and accelerators for improving decision-making at the edge. I thought it would be useful, before I dive into the talk proper, to give a little bit of information about DARPA and how we operate. I know many folks in the room have worked with DARPA before, but for those who haven't, I thought it would be useful just to understand how it is that we develop new program concepts and how we interact with the research community. If you've never been to the DARPA building before, you might imagine that it's full of research labs and teams of scientists. The reality is we have none of those things. We are a building really full of program managers who are really, their job, my job, is to identify sort of new ideas that support new research programs, and then to identify the external researchers, the researchers in academia, in industry, and other parts of government, that can then execute and implement those key research and evaluate those key research concepts. So what I'm really hoping to get out of today is to share with you both sort of the key successes of a recent program in RF machine learning, specifically the RF Machine Learning Systems Program, or RFMLS, and then also identify the key areas coming out of that program that are opportunities for new research concepts. And sort of a key reason why DARPA programs are relatively short, just a few years, compared to say other government programs, is to provide that opportunity to make advancements on sort of the most important problems of the day, really look at those problems after next, and ensure that every few years we have an opportunity to take stock, reevaluate, and make sure that the best of breed technologies can be applied to the most important problems of the future. So really, coming out of this talk today, what I hope to share with you is to understand really where those opportunities are for new research, and as well as get your engagement in these research ideas. Fundamentally, the strongest, some of the strongest DARPA programs are developed through just that kind of dialogue. And again, I hope that at the end of this talk we leave a lot of time for questions to get that dialogue started. So let me unpack really at a lower level what I hope to convey in today's talk. And why am I focusing on RF autonomy? Why am I focusing on uncertainty? At a high level, I like the term RF autonomy versus, say, cognitive, talking about versus cognitive RF, because it really emphasizes what we're asking RF autonomous systems to do is make decisions at the edge, make decisions on our behalf, as opposed to making radios that think. Now, a key reason why this why we need RF autonomy is that the kind of decisions made in the spectrum are fundamentally made at machine speeds. Unlike other kinds of autonomy, here we don't have sort of humans in the loop that can reasonably make these kinds of decisions. It's not a self-driving car where we could reasonably have a human being give you a strong standard of performance. Here, we really need that RF autonomous system to be able to act on our behalf at that microsecond, nanosecond kinds of timescales. A key benefit from the use of RF autonomy is improving overall spectral capacity. This is a key finding that was demonstrated at DARPA's Spectrum Collaboration Challenge, where we showed that teams of collaborative radios that weren't operating on a predefined decision plan could improve spectral capacity over expert-defined solutions. And the key reason why autonomous systems can provide this capability is they can use localized information, to make localized decisions, modify their waveforms in a more optimal way based on the information they have at their disposal that really wasn't available to original designers. I think we can see strong motivations for incorporating these kinds of autonomous behaviors into future wireless networks. And fundamentally, by having these autonomous frameworks, we can deploy our capabilities faster. The more trust that we have that RF autonomous systems can execute our high-level goals for spectrum usage, the more confidence that we can have in finding new use cases, new uses for and new capabilities for that best utilize those sparse spectrum resources. Now, the problem of uncertainty undercuts a lot of these high-level goals that we want to achieve through RF autonomy. RF autonomous systems, are fundamentally operating in highly complex, nearly entirely machine-made environments. These environments, the laws of physics apply, but unlike, again, our autonomous vehicle example, the equivalent of buildings in the spectrum, structures that our RF robots need to avoid, can come and go as they please. It's like making a self-driving car where every car can teleport anywhere it wants at any time. So thinking about those very fast timescales and the degrees of freedom over which these RF autonomous systems can act, adds enormous complexity in how these systems have to make decisions. There's an overwhelming number of choices, particularly as we look at advancing RF systems that have higher degrees of freedom in terms of spatial degrees of freedom, waveform degrees of freedom, timing degrees of freedom. Our software-defined radios produce far more opportunities for our agents to make choices, and those choices are overwhelmed both in terms of our local agents' options as well as the options of every other agent in the environment, where we have to imagine what all the other actors in the system are going to be doing and make our own choices within a context that we are going to have a difficult time unpacking and attributing all the observations that we make back to the choices made by all the other agents, all of the other actors in that scene. And a key driver of uncertainty is, as we're designing these RF autonomous systems, we're going to have relatively low trust in the assumptions that we make. as part of those designs. If we're projecting forward to a future where the spectrum utilization is not tightly governed by specific spectrum uses and specific frequency assignments, then we really unlock the ability for software-defined radios to operate freely across wide spectrum with a wide range of waveforms across time and space. Then our assumptions about what kinds of environments we're going to see when each of these RF autonomous systems is deployed is going to vary widely. We can't possibly have exhaustive data sets. We can't possibly have exhaustive specifications for all the kinds of things all the kinds of environments we might face. So how do we develop systems where we have this fundamental uncertainty about any requirements, any assumptions we're making about how these systems are going to behave? Now the RIFMLS program, RF Machine Learning Systems program, developed fundamental machine learning tools that can be applied to this future autonomous RF vision in uncertain environments. But there's some major challenges laid out here that we need to address to really realize a future vision of RF autonomous systems in uncertain environments. So DARPA likes to think about AI across 3 waves. The wave 1, handcrafted knowledge. You can think expert systems. Wave 2, statistical learning, machine learning, involving categorization of data. And wave 3, a future wave emerging now, is in explainable AI with contextual adaptation. Now, I wanted to lay out this map to show where RIFMLS fits within this overall vision. The fundamental focus of the RIFMLS program was to demonstrate that second wave AI, statistical machine learning, can succeed in the RF domain, that the kinds of performance gains achieved for machine learning of video processing, image processing, audio signal processing could translate to signal processing of raw IQ signals. And so understanding that the focus of RIFMLS was to really overcome the technical challenges associated with translating the successes of other domains and addressing core unique challenges of the RF domain. And I'll unpack those challenges in just a few minutes. In order to demonstrate advancement against the thesis on the previous chart, that the machine learning can be applied to RF signals, we identified 2 key challenge problems. The first was RF fingerprinting. There's a lot of talks coming up today in RF fingerprinting, so I'm sure that this is a well-understood concept for most in the room. Fundamentally, we're talking here about taking unintended effects imparted by the hardware transmit chain of an emitter and using that to uniquely identify emitters sort of by serial number that are nominally transmitting otherwise identical waveforms. So can we use machine learning to discriminate RF systems using these classes of fingerprints? And the second challenge problem was an important signal detection. You can think of operating in a very crowded spectrum, many different kinds of signals. But from a high-level system goal, only some of those signals in the environment are important. And we want systems that can focus their attention wholly on those important signals and ignore the unimportant or background signals. Now, across both of these challenge problems, there were sort of secondary tasks that added a control element. Let's say on the fingerprinting problem, were there ways to change the transmit in order to improve the fingerprint quality of the system as a whole? And on the important signal detection problem, once we included the degrees of freedom of a receiver in terms of both spatial degrees of freedom and searching across frequency, could we improve our ability to find important signals across wide bands? I'm going to focus today in terms of accomplishments on the top two tasks, sort of the open loop problems, and the problems that involve. In interest of time, I'll defer discussions about these challenge problems involving the control. So the core outcomes of the Ripples program across these two challenge problems was that we demonstrated that with respect to RF fingerprinting, we could enable discrimination of signals using far more subtle features than could be defined by expert systems. And that this inherently allowed our systems to scale to discrimination across much larger populations than a traditional expert-defined features. And with respect to key findings of important signals, we showed that by using a machine learning approach, you could rapidly design new detectors and classifiers for important signals much faster than equivalent approaches to using expert-defined features, designing exquisite detectors for specific signals. And I'll unpack these two results on the next couple charts. So specifically, we showed under Riffmals that we could surpass our ability, so we exceeded our stretch goal in discriminating, using our machine learning generated our fingerprints to discriminate large populations of emitters. Building off, sort of coming into the program, looking at prior art, looking at expert-defined features, our ability to discriminate these particular signals was roughly at 100 emitters. Under Riffmals, we showed that this could be exceeded by 2 orders of magnitude, growing to populations of 10,000 emitters using machine learning techniques while maintaining 95% accuracy. This was really a critical result coming out of the program and really gave us confidence that machine learning techniques can take RF fingerprinting and grow it to addressing more operationally relevant population sizes of emitters that a spectrum sensing system might have to manage and encounter. A key enabler of both this result as well as the performance on the important signal problem was the development of data sets that supported development of and training of machine learning networks. So a core foundation of the DARPA Riffles program was the development of data sets that supported identification of commercial signals that let us scale up to these kinds of numbers. On the important signal problem, I've gotten away this far without actually telling you how we defined important signals under this program. But we had 2 related definitions. The first was important signals as a previously known signal of interest. That is to say, we have an example of a signal, just really an IQ snapshot of a signal that we've seen before and want to see again. And another class of important signal, it really flips that problem around. It says we don't know what new signal we're looking for, but what we do know is signals we're not interested in. So we've defined a set of signals that match. We defined a set of background signals that we know don't contain any interesting signals. And we want to find signals that are new that don't match the statistics of those backgrounds. And for both of those processes, we started with either labeled examples of signals of interest or unlabeled examples of background environments, trained deep neural net, and then ran that neural net at an inference across a 500 megahertz wide IQ stream. The core output was a labeled spectrogram, where you can think of in the known signal case, we're highlighting all of the known signals that we've defined previously as important with bounding boxes in time and frequency. And in the anomalous case, the new signal case, we're similarly developing time frequency bounding boxes of those signals that don't match, that are anomalies, that didn't match the previously observed background. And you can think of these two detection approaches as part of one signal processing flow, where if we can start with a new signal detector, an anomaly detector, to find interesting signals in the environment, and then take those IQ examples from the labeled spectrogram, fold them back into the detection of known signals of interest. And through this kind of approach, we demonstrated on RIFMOLs that we could train new detectors in the span of hours, detecting new signals in real time, and then redetecting those signals from detections of anomalies, all while processing multiple 500 megahertz bandwidths of streaming IQ. So there's really a core set of machine learning challenges that we addressed in order to achieve these goals. And these are really sort of key differences between a sort of a traditional image processing based approach for machine learning and an approach focused purely on RF signals. The first challenge overcome was the incorporation of complex data processing, where we specifically developed complex valued neural network architectures and activation functions. A key factor that is sort of inherent in any RF signal processing in the wild is managing multipath. And there were many different approaches that we explored on how to take account for multipath within our networks. It's fundamentally a confuser, a nuisance parameter that has to be isolated in order to get the kinds of discrimination that we want to achieve. And we experimented with a wide range of approaches that included more standard equalization, all the way through developing new neural network architectures that were fundamentally channel invariant. Another major issue that RF machine learning classifiers had to overcome was the dynamic features, which is to say that because RF signals are so agile and change their characteristics over time, we needed network architectures that could tolerate the kinds of the changing of features over time at microsecond kinds of timescales. And this was addressed through structuring our network sparsity to better take account of the various features across these timescales, as well as ensuring that our architectures were tracking these multi-timescale features. So I've talked about what we accomplished under the program, but what were the core challenges exposed? What were really some open research questions coming out of this effort? At a high level, a major factor is the computational costs of wideband streaming data processing. Under this program, we developed capabilities to process wideband signals in real time, multiple channels of 500 megahertz data. But in order to actually process these signals, it took multi-GPU servers that could process these inference networks in real time. Really, solutions that don't align with what you might want to see in an embedded environment. We applied, in order to achieve these goals, achieve real-time processing, we applied many kinds of, I'll say, machine learning optimization techniques to improve our real-time performance. This includes things like pruning or architecture search, quantization of the networks. All of these got us to performing on wideband data on server class architectures, but it doesn't bridge the gap to processing wideband signals within at the edge within much smaller systems. And a key opportunity here is to take the utility shown of focusing on important signals and translate that lesson into the underlying hardware architecture. And I'll unpack that in the next couple charts. The other major challenge, and I alluded to this earlier in the talk, is in training for uncertain environments. We developed capabilities that largely leveraged supervised learning approaches on previously collected data sets. And we did some, layered on top of some of that, some experiments in unsupervised learning, and including a mixture of unknown signals along with the examples from our training sets. But if we are looking forward to a future where there's a large degree of autonomy in the spectrum, and our ability to know in advance exactly what mixture of signals that we might see, our ability to compose effective training sets is going to be significantly reduced. So there's an opportunity here to look at co-design of the experiences, training and evaluation for RF systems as a mechanism to improve and enhance our architectures and make them more robust against in uncertain environments where we have a very low degree of confidence about what specific signals that we're going to see. So in order to sort of structure the discussion on these next challenges, really want to introduce just a high-level block diagram of an agent concept. Now, this is not meant to be an architecture, or this is not meant to represent any physical implementation, but it's useful to highlight the pieces that are needed in order to develop any kind of autonomous RF agent or cognitive radio. Fundamentally, these systems are built on a perception decision cycle, where they have to develop, they have to sense the environment, process receive data, translate that into actionable perceptions, make decisions on what we want to do next. Those decisions in an RF system really coming with two flavors. Those decisions can be changing how I'm going to receive signals in the future, or changing how I'm going to transmit signals in the future. And so looking at this loop, we looking at where RIFML is focused is we're very focused on the sensing part, the development of perceptions that could be used to support decision making. In the control tasks, we to a certain extent closed the loop and added decisions, either manipulating a radio or changing a transmit waveform to include that part of that decision in action. But I'll say the core accomplishments of the program focused on perceptions. There's a few other things I want to highlight on this chart. Fundamentally, these systems are an RF system isn't operating in the spectrum purely for its own ends. It needs to be interacting with some higher level objective or function. And there's two ways that system interacts. One is by providing information, both receiving and essentially having an information exchange with that higher level mission objective. And then the second is by executing a decision plan. And what do I mean here by a decision plan? This is how you can think of this as a policy, you can think of this as a behavior set. This is how we want the agent to perform in the environment. And I'm going to get to some more details about what I mean by that decision plan in a few more charts. So what I really want to tease out here is this interaction between decision and sensing. And this is shown really as very monolithic, that there are a set of perceptions that come out of the sensor, distilled from that raw data, from that raw received data, that then turn into decisions, that turn into our decisions. But the reality is how we want the system to behave is much more layered. That we don't want to think of decision as happening monolithically off of one set of perceptions. We want to think of a tiering, a multi-timescale set of decisions, where the decisions that we need to make at the faster timescales are supported by the information extracted at the faster timescales, and the decisions we need to make at longer timescales have that same kind of correspondence. And if we want to fully close the loop, we want the decisions made at those longer timescales to actually update and change the decisions we're making at the faster timescales. The full loop closure includes making choices at the highest levels, at the highest timescales that reflect how we make those fast timescales and choices in the future. If you're a fan of thinking fast and thinking fast and slow, we can think of this as sort of a system 1, system 2 decomposition, where our reflexive choices are established by a more cognitive layer on top that's reasoning over much longer time choices. So a real theme here is that we want to push decisions much closer to the edge. In order to achieve that, we start to run into limitations of current processing architectures. I want to imagine a future where we have the ability to make much faster decisions within our spectrum processor. Today, our autonomous spectrum systems are structured around relatively fixed sensor processors, where the signals coming in are processed the same no matter how they're observed, how they're related. They go through a rather standardized processing flow. This is true even for the RIFML's deep neural net implementations. Even as we're processing important signals, the neural network, the deep neural network that we're using to process that IQ data is static across all of the signals in the environment that it sees. And what this fundamentally means is that we're getting sort of uniform features across all the detected signals that might be present in the environment. The new idea here is that, well, if we're focused on decision making, where the features that we're trying to extract from the environment, the most important signals are the ones that are decision-centric, the ones that are going to affect the overall behavior of our autonomous RF system. We should focus our processing all the way at the front end on those signals that are going to make the most impact in our overall decision making. And that means if we have an underlying processing architecture that can adapt its pipeline at the scale that waveforms are received, at that microsecond and nanosecond time scale, we can actually change our processing pipeline to get much more actionable, deeper, enhanced information across the more important signals, while preemptively stopping processing of the unimportant signals whose feature sets, whose information wasn't going to influence our decision pipeline, or our overall agent's decisions anyway. A key enabler of this kind of approach is feeding that changing definition of importance from the higher level decision agent back into this underlying processor, and seeing those choices, those nanosecond reconfigurations reflected and executed by a part of the decision process that's living in the sort of the dynamic routing of signal data in the underlying processing. With this kind of approach, we can get far more useful information across far wider bandwidths than if we just try to scale up this sort of brute force extract the same information from every signal. Some key challenges, many of them lie in compute, many of them lie in algorithms. There's some fundamental trades in computing architectures between the density at which we can achieve processing and the interconnect flexibility that we want to enable these systems to have. Just thinking of it physically, we've got chip area that we can spend on interconnect, or we can spend it on processing. And the more chip area we devote to interconnect, the less processing that we're able to achieve. So is there a way to balance that trade so we can get the useful information out, the useful computations out of the system at a much higher level than if we try to do a brute force approach or try to have an arbitrary level of flexibility? Can we let our the kinds of information that we want to be prioritized in an RF system flow back into our underlying processing architecture? Another related processing challenge is configuration speed, where the more choices that we empower our processor to have, the more difficulty that we're going to have in having it switch at scale. You can think of having multiple signals simultaneously routing through a flexible interconnect fabric. How do we make sure that those signals are processed in a way that the processing chains don't collide? And preserving our high-level definition of signal importance at the processing layer. Overarching all of these challenges is we need to rethink how we structure our, if we're able to create a successful processing architecture, we need to rethink how we structure our algorithms to target such an environment, where the reconfiguration of the processor isn't something that's done to switch between algorithms, but that reconfiguration is folded into the algorithm architecture itself, and part of its fundamental implementation of the choices that we want our autonomous RF systems to make at machine speeds. Going back to the agent architecture, let's focus a little bit more on this decision plan element. And this really rolls into a number of different characteristics of the agent. One way to interpret this decision plan is as the agent's design. That this decision plan says, well, these are the perceptions we want to come out of our sensing system. These are the actions we want our decision system to take. It really defines how this entire system is architected, both as well as defining our higher level objectives and any sort of performance standard that any adaptive agent can use to evaluate its own performance in the context of its autonomous behaviors. How are these decision plans developed today for agents? Really, we've got two different approaches. We can think of these as sort of the wave 1 AI and wave 2 AI approaches. With an expert system, we start with defining requirements. What does the expert believe that our autonomous system should do in these complex environments? These requirements are codified in a physical document or certainly in the software implementation that then translates into the decision plan that our agents are actually implementing. Or we can do a more data-driven approach using wave 2 machine learning, where the design comes through curation of data, where we take sample data that we expect to be representative of the operational environment, and use that to develop our decision plan that our online agents are going to execute at inference. The huge challenge with both of these approaches is we assume that either the requirements that expert has defined or that the data that we've sampled in our machine learning approach is representative of the environment that we're going to be operating in. And the more that the more the environment deviates, the less we're able to guarantee performance. At a high level, the new idea is that can we, using the compute power and exploratory design principles, can we co-develop, I'll just call it requirements, decision plans, and the environments in which those decision plans will be evaluated? Can we co-develop those objects so that we can, rather than settling on a design and then evaluating it in the target environment, actually rapidly iterate through a number of designs in order to identify the strengths and weaknesses of particular approaches against a broad set of potential requirements. So rather than having a single point design, we've identified a broad range of design options, each with different points of sensitivity, and perhaps settled on a set of corpus of designs that can address a range of particular conditions. We can think of this as this kind of design automation in some ways being analogous to for classifiers an architecture search, where we have a defined set of evaluation environments, and we are actually able to find the architecture that optimizes performance against that set. But here we have a more complex design that we need to implement, where we typically these agents are designed with a heterogeneous machine learning system, where we have different sort of a pipeline of different machine learning technologies that all sort of interact in complex ways, and our ability to do the equivalent of an architecture search across all the degrees of freedom of that complex pipeline and evaluate it against unknown environments, very challenging. So are there methods to apply modern software design automation techniques to ensure that we have robust machine learning agent architectures across broad ranges of uncertain environments? We can think of this as really an alternative to trying to simulate all possible environments in advance, where we know that we fundamentally don't have the compute resources to create high fidelity simulations over every possible scenario. How do we use that same concepts to efficiently distill to the right set of evaluation conditions that best prepare our agents for these uncertain environments? So I'll really just in summary, the high-level goals of the RIFMLs program were achieved. We demonstrated that the performance gains of deep neural networks do translate to the processing of RF signals, achieving two significant program goals against two of our challenge problems, both showing the scalability of our fingerprinting and the ability of important signal detectors to be rapidly retrained for new signals. There are at least two significant new research opportunities in RF autonomy that have fallen out of this work. One is developing new classes of processors for reconfiguration away from timescales. The other, developing new methods for training RF agents for uncertain environments. And I'll kind of end where I began. That the ultimate goal here is to really bring to incorporate the benefits of RF autonomy while overcoming the challenges of uncertainty, pulling in the kind of the third wave AI technologies to enable this. And broadly, I'm really looking for a dialogue with this research community for ideas that fit in sort of the two swim lanes identified, or really any new research idea that could be used to improve the robustness of our RF autonomous systems in these complex and uncertain environments. And I'll stop there. Happy to take any questions from the audience. Please. Do you want to use the mic? Flip the switch.
I think this is one important thing we need to consider uncertain environment. But one question is, if we consider environment is uncertain, and I develop some algorithm, develop some solution, so how can we measure the performance? Is there any ground truth, or is there any way we can prove it is optimal, close to the truth?
I think the core answer to that is that you will fundamentally never be able to demonstrate that your system can perform in arbitrary uncertain environments. You can only test it against those environments that you actually can expose it to. When we talk about ground truth, I think this is another area where I'll say we don't necessarily have great answers in what the optimal behaviors should be under the broad range of complex conditions that these RF agents might experience. So ground truth in terms of, well, this is the behavior that we always want in this condition is difficult to determine in advance. But I think that is one of the keys to unlocking this challenge is to sort of potentially pose this problem as a corollary to an explainable AI problem, where we're not need a way to incorporate within our automation that auditing of these various architectures against various performance standards. So the architectures under evaluation have to be able to report their own performance in a way that we as human engineers can audit that performance. Fundamentally, you're not going to get to the point where you can guarantee performance in any arbitrary environment, but what this approach can potentially help you do is increase the speed at which you can address those new environments. Much like we saw under RIFMLs developing new detectors for previously uncertain signals, the promise of this class of technology is that through this kind of approach, we can much more quickly update our architectures as we start to experience these sort of future environments where there's a much higher degree of RF autonomy.
Thank you for the great talk. Really interesting. So, at a high level, you really, highlighted how machine learning is important to achieve RF autonomy in some sense, right? I wanted to hear a little bit more about some of the challenges, right? You mentioned explainability of models and at least that's what I could figure one of the challenges, right? I'm assuming security of these models is probably another challenge, actually. Explainability by itself poses additional challenges, right? Because explainability means you're releasing more information about the model itself. Depending upon who the explanations are fed to, they can lead to privacy challenges as well. So, what is can you give some thoughts on what are the challenges to RF autonomy? When you use machine learning, what are the main challenges?
Sure. So at a sort of a fundamental issue that we're wrestling with here is that we're trying to project forward into an environment where we've now, much like the vision of the Spectrum Collaboration Challenge, we have a future vision where rather than having sort of fixed behaviors for RF systems that have to operate within sort of well-defined, very constrained licenses, we've now empowered them to operate over large degrees of freedom to optimize their own performance. And when we think about it in those terms, there are any number of issues that arise. I mean, fundamentally, you cannot design a system that's optimized for any possible set of conditions. So this is kind of a no free lunch problem. So we have to think about, well, given that we cannot optimize for every eventuality, how do we at least define the sets you merge the sets of heuristics or other kinds of domain expertise, fold that into our machine learning architectures. I mean, that's sort of a core challenge of this third wave. It's not necessarily replacing the technologies of the first and second waves. It's finding a way to integrate them in new and more powerful ways. So what are I'll say for this future autonomous RF environment, what are those sort of core heuristics that are most useful for for, and how do we integrate them with traditional machine learning approaches? I would say a related challenge is, I'll call it the system analysis and system integration. We have good tools for assessing the performance of individual blocks of machine learning functions. If we want to test and evaluate a classifier, there's a well-defined way to do that. If we are now sort of combining that classifier into a complete intelligent agent that can adaptively change, say, how it communicates within the spectrum, there aren't good high-level tools that lets us analyze how, say, the performance of that classifier block translates up into the performance of the overall agent. That decomposition, that sort of requirements decomposition that is sort of so critical to system design using traditional tools is very difficult to do with this kind of approach. So developing new methods for system integration and evaluation and how we properly couple the performance of these individual machine learning blocks into this heterogeneous machine learning pipeline is another core challenge. Hello.
Two questions. First of all, nice talk. Sorry, the question is out of context, but I'm not sure that I know a lot about RF autonomy and all this kind of stuff. But as a follow-up on the previous question, doesn't this open up a whole new attack vector for attackers to actually integrating machine learning in such systems that we are not already sure about how to verify that the machine learning model is secure and cannot be attacked by an adversary?
So it's both I think, a disease and a cure. You're correct. If our RF systems are static, they never move, they do exactly what they've always done with no changes, then there's no adaptive behavior for an adversary to potentially attack or exploit. But we've also then sort of given the potential adversary sort of the benefit of time to figure out how to attack the static target. So fundamentally, yes, adaptation does introduce new ways, new potential exploits, but I think the alternative of static allocations is fundamentally not a solution either. So we have to think about and certainly incorporate security into our considerations of the design of future systems.
Okay, yeah, that makes sense. And another one, when you say that there will be reconfigurable hardware that operates in a very low latency, you don't mean FPGAs, you mean something better, right?
So I'm not, so just background, so Microsystems Technology Office at DARPA, one of our research areas is next generation processor architectures. So I'm proposing here that potentially there are other processing architectures, say beyond what's commercially available as FPGAs, that could bring this level of reconfiguration and enable adaptation at waveform timescales. If we were able to overcome the processing challenges associated with that, could we realize significant benefits in our spectrum sensing systems?
Okay, thanks.
Certainly.
Thank you for the talk. I had a question about gathering and training your models in those unseen environments and scenarios. Are you thinking of reinforcement learning approaches to adapt your neural architecture parameters in new environments because, as you said, labeled data sets are not available for those new environments that the agent goes to.
So I would say reinforcement learning is a potential area that could provide benefit for these kinds of architectures. A big challenge of reinforcement learning is the sample efficiency. So you need a lot of examples, a lot of interaction with a relatively stable environment in order to learn the lessons of reinforcement learning. So as we move towards higher levels of autonomy in the spectrum, is there a point at which you don't have the sample efficiency you need for reinforcement learning to provide a benefit? And I think there's the potential. There's two potential directions there where to address that problem. One would be reinforcement learning approaches that are tolerant of a high level of dynamism in the environment. The other might be comparable approaches that have much higher sample efficiencies. So I think those would be two challenges that would have to be addressed in order to apply reinforcement learning to this kind of problem.
Thank you.
Hey, I've got a question jumping off one of the previous things about the adaptive processors. So it's a suggestion that, or it's a proposition that it should improve in some way. But has there been any work related to the adaptive processors actually improving anything? So of course,
so there, I'll say without referencing any specific specific architectures, yes, there's been, I'll say, considerable work showing in the feasibility of alternative processing architectures that can have significant benefits in processing density over equivalent FPGA designs. I think the open research question is there a way to substantially realize those gains for spectrum processing applications? And what kinds of architectural features need to be included to best realize those gains? You can think of it this way, that in some ways the complexity of the environment pushes you in this direction, because you cannot have processing, I'll say statically allocated processing, fixed accelerators, sort of as dedicated silicon waiting for the right signal to show up in this kind of complexity. Your processors can't scale that large. So what I'm proposing is that there's evidence that these kinds of processors could be built. Can we identify the right spectrum sensing approaches that would really highlight the utility of that class of architecture for this problem set?
okay, and that sort of thing. So there's a suggestion that it could be built, those processors could be built, but before
Yes.
you get to that, it is important to, I mean, we can still simulate these sorts of things just to see, do those extra paths?
Yes.
Right. So, okay, thank you.
Thank you for your talk. So also have quick question. The first one is, you mentioned for the important signal, what's the specific definition for the important signals? And the second question is that you discussed intelligent agent and their feedback system. So do you have some simulator, especially for RF, that signals? Last one is, I know there is the DARPA competition for our fingerprinting. Do you have plan to release some data set for this community? Thank you.
Sure. Let me take the last question first. So the The RF data set is available to researchers with government working on government-sponsored programs. So if you have a government sponsor for your research, have them reach out and we can work through those details. At a, I'm sorry now, your first and second question?
First one is, so you discussed important signal.
Oh, yes,
I think
yes, definition of important signals.
Yes.
So under the RIFLs program, we defined it in two parts. An important signal was either a signal that matched a previous observation, like we had an example of a signal that we wanted to see signals like it in the future. That was an important signal. Another important signal was an anomaly. If we have a background that we know contains no important signals, can we then, looking across that kind of set of background signals, can we find new signals, anomalies that have been never before observed within that background? So that's a different definition of importance. So I'll generalize that and say that in this sort of intelligent agent, autonomous agent view, an important signal is a signal that affects a decision. That you should take a decision-centric point of view, that the signals that you want to hear more about are those ones that are going to either change your scanning behavior, change your transmit behavior, or provide useful information up to some application level that wants to know about those signals. So I think that's the broader definition of importance.
Okay.
And then the second question was on simulators. I'll say our performers have developed a wide range of different simulators for exploring different parts of this problem, and I think that's probably something we can unpack offline.
Okay, thank you very much.
First, I thank you for your enlightening talk. I'm Yemi. I'm currently an assistant professor at UT San Antonio. And I have one question. So you mainly talk about how the autonomy in receivers and transmitters. So there is also some research on like the RIS, reflective intelligent surfaces, which is designed to change the radio environment. So could you please share your ideas about how that fits into the total RF autonomy scope?
I'm not sure I understand. What kinds of materials that change the propagation environment?
Yes, it's like reflective. It's like the reflective surfaces that can change the wellness channels.
Well, what are applications of that are currently under consideration?
There are a lot of so previously we mainly talk about like the how we can change the transmitters and receivers.
Yes.
Yes. So like the RS is like the reflective intelligence services, so that they can like the you can model the wellness channels.
I see. So I would say that would be just a new class of agent that would be entirely passive, but would have the same kind of potential ability to observe the environment and then change its reflective behavior against some higher level goal. They potentially be included as a new class of agent.
I see. So you say that is something DARPA may be interested in.
I'd be happy to have, this is not something I'm familiar with, be happy to have further discussion about what you're thinking.
Great, thank you.
Well, I'll be at the panel this afternoon, so if anybody thinks of any questions over the course of the day, or of course in a break, happy to have a discussion. Thank you.
Probably cannot, maybe not.
So, okay, let me show you a place, for example. So, if you go to the WiseML website, and after the slash type in PPT upload. So, and you can tell this to all the speakers today. So if you type in PPT upload and press enter, you will see a file drop web page. If you upload it here on my account, I can pull it from on this laptop directly.
Okay.
And you can do that from your phone or laptop, yeah, right? So this is the link, right? So WiseTech website and then PPT upload.
Upload.
Yep. Yes.
Do you want to show this on?
Yeah, that's what I was gonna do.
The video WiseML sessions will be held here.
I'm sorry.
WiseML workshop sessions will be held here.
Yes, yes. Today we just have the.
I am the first presenter of the first session.
Okay, so you would be do you want to use this laptop or your?
Yeah, this one.
Okay, so I'm gonna pull this.
I can send you an email because I was plastic in the airport because of they check. I can send you email the presentation.
So we do this. Let me zoom in. So upload your slides on this link, right? So if you have a talk, do you also you want to use it on a laptop?
I'm planning to use this.
You are free to use if you want to. Alternatively, you can upload your slides on this link. I will be able to download it. Either way is fine.
Yeah.
Upload it.
Okay.
Yeah, this one.
Okay. Oh. Okay. Yeah. Let's see if
Try to open.
yes, I'll do that. Bias hacker. Oh, no.
The deep learning is mine.
Oh, the deep learning. Yes. Yeah.
I'm the third presenter. So.
Okay. So, let me.
It
So,
looks good.
okay.
Okay. And try him.
Yes.
Okay.
Okay. Looks good.
Great.
Okay. So you're free to either upload or you can use your laptop. That either way is fine.
Maybe type it more. Upload your slides by this link.
Where is my cursor?
Who's uploaded?
Sorry.
Who is uploaded so far?
We have two speakers, and including the keynote speaker was
Okay, so keynote plus one more.
plus two. It's up to you. It's not.
I don't want to have to do this all the time.
Yeah.
There's mine. Hi. I was just refreshing to make sure mine is there.
Okay. So you are the
Two. Second.
second. So we have a second.
Which one?
On this one right here.
The first one, right?
Yes.
It's good.
And this is first.
Now I'm trying to.
So we have first, second, third, fifth. Do we have the fourth?
I don't actually know the program.
This is the first.
For this, we would have to. Let's see.
We have the first, second, third, and fifth. But I'm not sure whether we have the.
Okay, let's see. I mean, they can bring their laptop as well.
Maybe just show the first one.
I'm sorry?
Sure,
Sure,
this is
okay,
fine, yeah.
open. Let me minimize that.
We can wait for the speaker.
And Which one is that?
Don't know, just open. Just open slide and check.
So that's the second one.
Yes.
Yeah, that's okay. So let me open that in the PDF, in the Acrobat, because it's not signed.
So let's start the first session.
By the way, could you also wonder whether you have a pointer or okay, here, just use it.
Just use.
Okay.
So let's start with the first session. So the first speaker is Alma. Yeah. He will give us talk on analysis of augmentation methods for IF fingerprinting on the impaired channels.
Thank you very much. Hello everyone, this is Dr. Ömer Mekül from University of Ottawa, and today I will present our paper entitled Analysis of Augmentation Methods for RF Fingerprinting under Impaired Channels. And let's outline what we'll talk today. First, I will give a motivation, then related literature, and I will briefly give the system model and problem definition, and then a slight background and data set introduction. And I will present our proposed approach based on data augmentation, and I will give the numerical results and conclusion. I will conclude the presentation and just give future works. Let's start with the our motivation. We consider autonomous vehicles, in fact, critical infrastructures, unmanned aerial vehicles, or other critical infrastructures, and they are prone to spoofing attacks. And okay, there are already some solutions because security is a broad field, and let's consider a different solution. Because wireless devices have malfunctions due to their production, and their effect can be seen as radio frequency waves. They have their unique behavior, depends on their production, and this unique characteristic is called as RF fingerprint of the device. And we already know that in the 5G or the later generation 6G, it has a slightly different name. But in the 5G, we consider it as the ultra-reliable and low-latency communication. It is one of the three core features of the 5G, where they aimed 1 millisecond latency. And for this purpose, RF fingerprinting provides a physical layer security. So moreover, we can consider it as a more robust solution more practical solution than the other solution. At least we try, and that is how the RF fingerprinting emerged, and people start to work on that as a promising field. Let's give a brief literature. I took this one from our paper to give the table, which can make it the issues clearly. In fact, we consider 4 features here. Not using modulated or synthetic data or real data, or augmentation or no augmentation, and different data or heterogeneous waveforms. And when you consider the literature, this work has unique features which considers all of these 3 features. In this work, we consider real-world data. We use the raw samples of real-world data, not synthetic data. We consider augmentation. Augmentation is a well-known approach, but the important thing is how you augment your data. And we consider different data. That is the classical one, except one of these work. We train on day 1, and we will train on day 2. And we consider heterogeneous waveforms because we plan to use it in the 5G communication later. And as you know, when the 5G emerges, the other generation, the other device, other waveforms will not be that because when you consider 5G transmitter, there will be also the Wi-Fi transmitter. There will be also the 4G or LTE transmitter. We say long-term evaluation because it will continue to develop. Although there is 5G and other 6G, the LTE will be exist in the future. So when you consider 3 type of waveform, so the problem will become different when you consider the 5G or the single type of waveform. And let's define our problem, first giving a system model. I just want to illustrate with this figure. As you see, there are different base stations, and 2 LTE, 2 5G, and Wi-Fi. And when you consider that we have, for example, one mobile phone with the single receiver, and the base stations transmit their signals, and but the base station 1 and base station 3 can make spoofing attack, or a spoofing attack can be done through them. For example, think about the base station. For example, when the base station 2 sent the signal, it can be considered as the signal is coming from base station 3. Or when you consider the base station 1, the signal can be considered to transmitted by the base station 4. So in our problem, in the RF fingerprinting problem, we try to understand which device, which transmitter sends us this signal. How we will consider the previous transmission in the previous day, in the day 1, in the train data, and we will understand it is the device, the fingerprint of that device, and say that, this signal is not transmitted by for example, base station 2. It is actually transmitted by base station 3. So the fingerprinting help us to understand and overcome the spoofing attack this way. And what is our problem? We aim to achieve the high accuracy on day 2 test data based on the known day 1 data, train data. And we investigated data for the channel impairments, and also we consider the environmental changes, like in temperature, because it affects the fingerprinting. And we worked with data sets composed of 3 different communication technologies. namely 5G, Wi-Fi, LTE. Thus, we consider heterogeneous waveform. And we use powder dataset used by the Kochik-Chouhiri's group in Northeastern University. But we will start to work on, we will start to collect. In fact, our industrial partner, Fingerprinting company, start to collect their own data. And we will produce our data set at the early stage, we can say. And let's introduce the powder data set a bit deeply. This powder data set is presented by Chouhiri's group at Northeastern University in their 2020's paper. And it includes 60 .bin files for each day of day 1 and day 2, totally 120 files. And it includes 3 waveform taken by 4 transmitters, and each transmitter takes 5 samples. And we assume we have only 1 antenna at the receiver side and 1 IQ values provided by the powder dataset, like SISO, single input, single output. And I also want to give a slight background. Okay, we try to understand the transmitting, we try to understand the characteristics, but also we should consider that we need semi-flat channels. Not directly flat, but semi-flat channels to understand that. But if the channel is too bad, like this one, as an example for LT transmission in day 1, and it is difficult to understand its characteristics. And that is an example for the. That's an example of a bad channel, a Wi-Fi bad channel for the day 1. And in those bad channels, it is difficult, and it is, in fact, we cannot understand the fingerprinting. So we need at least semi-flat channels. So to overcome there, we can use some localization or maybe some other techniques, and we try our best. But semi-flatness is important to understand the fingerprinting of that channel. And we consider channel impairments. And as we say, dropping accuracy on day 2 is investigated for channel impairments and also by considering environmental change. What we do here, we consider data augmentation with white Gaussian noise. White Gaussian noise is a classic model. When you consider information theory, 7 decades ago, they consider some Gaussian noise or white Gaussian noise. But when you consider the current channels, the 5G or the new generation, so it is a bit more idealistic. We will talk about that. And you consider auxiliary classifier GAN, and we just give a classical structure. We also do the augmentation with that. We also consider the tapped delay line and clustered delay line, TDL and CDL here. And let's consider the implementation result, and then I will give a bit comment about that, evaluation about that. In this paper, we consider augmentation. By the way, okay, I missed the point. Sometimes we consider some issues as take for granted. Why? Because when you consider all those papers I show in the table, they generally start with, they have a 2-stage approach. In the first stage, they consider CNN, convolution neural network. But the issue is, if you want to achieve a good accuracy, about 90 or above 90, you should add the second stage. And in the second stage, for example, the Chouhiri's group use triplet loss or some other work. But in our paper, we consider augmentation because it is, I think, it is more practical when you consider our problem. Work with our industrial partner, Tinkeref. And we consider augmentation. That is why we focus on augmentation here. And as you see here, those are the accuracy on day 1. When you train data on day 1 and test on day 1, of course, you will achieve a near perfect accuracy. It is okay. But the issue is accuracy on day 2. And without augmentation, it is about 74, 75. And when you use 80 white Gaussian noise only, then the accuracy on day 2 is about 77. A slight change, but not improve much, because when you consider real-world samples, now we are about, we've already passed 2020, so our channel has different characteristics as it was modeled 70 cases ago or 60 cases ago in information theoretically. So AVGN doesn't work well. And when you consider auxiliary classifier generated with network, just as an approach, as a benchmark, we can consider. We use that, but maybe because of it also cannot understand that it gives a good result on the day 1, but it seems it is a bit overfitting, so it doesn't understand the day 2. But when we consider TDL, CDL, these are suggested by our industrial partner because the MATLAB has TDL and CDL functions, and they give some realistic approach. I will talk it a bit deeply. Okay, when you consider data augmentation with AVGN, then our samples from 5G, Wi-Fi, and LTE channels are used for this implementation. And as I said, AVGN is an idealistic model, and therefore it doesn't enhance our performance much compared with no augmentation. And when you consider ACM, it overfits for this problem. When you consider CDL and TDL, it gives good results compared with the other augmentation approach or no augmentation approach. Sorry about that. Sorry, the last thing, I missed the point. Okay. TDL and CDL, I want to give a bit more how we use TDL and CDL, how we achieve 88% accuracy in this problem. We use MATLAB generated channel profiles. Okay, we consider TDL and CDL approach, these functions, the related functions in MATLAB, and used our original real-world data set with raw samples. And we use we write a MATLAB code, and we process that, and we use TDL and CDL data. What is TDL, CDL? Clustered delay line and tapped delay line. We had some delay, and now we will produce some new bin files. Okay, we had, for example, 60 day 1, 60 day 2, but what we do in TDL and CDL, we just work on day 1 data. Okay, when you consider the 60 samples of the day 1 data, we use TDL and CDL and produce another 60 CDL, 60 TDL bin files. Similarly, we also produce TDL plus AVGN, it is optional, and CDL plus AVGN. So we produce 240 bin files more from the original 60 bin files. And as I said before, in our data set, we assume we only have one antenna at the receiver side and one IQ values provided by the powder data set. And by TDL and CDL, how we achieve this 88% accuracy, or why does it work well? Because it is, when you want to make augmentation, you should use some approach close to, you should make an approach by considering the channel features, channel characteristics. If it is 5G or it is Wi-Fi, you should consider that. For example, when you consider AVGN, it is idealistic. But when you consider TDL and CDL, they are already used in some other 5G
5G operations. And as I see from our industrial partner, they say that we work very well with TDL and CDL, and they give very good results for our other works or other projects on TDL and about 5G. So TDL and CDL are very appropriate when you consider these waveforms, 5G and Wi-Fi and LTE. That is why augmentation with TDL and CDL help us to produce some reasonable data. And these are our TSN graphics. We just, that is our train data. When you consider, we have just, two dots, two green dots on the yellow one, and also some a few dots more as anomaly or at that point. And these are the characteristics from the day one data from the powder data set. As I said, we will create some new, in fact, our partner will create some new data set. Of course, it will have different characteristics. And also, we produce, train, and test TSNA at the same time. And here you can consider that we classified well. And also less some of what we'll talk today. We use time domain raw IQ data with single IQ value and 99% accuracy on day one. That's classic, near perfect. And then when you consider day two accuracy, we consider augmentation methods, AVGN, ACM, and also we consider Rayleigh channels, but it doesn't work well. I consider, for example, Rayleigh fading, Nakagami fading, those are considered in the wireless communication, or Weibull Raisian. So maybe it can work well, but it doesn't work well. After then, we consider CDL and TDL, and it gives good results. And also, as this is a part of industrial project, they expect us to, our system to be also resilient to the interference. They say, okay, you are working very well in academically, it is good, but when you consider real life, there may be an interference, and as company, we expect the system to be resilient to interference up to minus 15 dB interference. What is minus 15 dB? For example, when you consider your amplitude as X, then minus 15 dB, for the minus 15 dB, the amplitude of that interfering signal should be 15 dB less than the amplitude of main signal. When you consider the 15 dB, it is about 6. So, for example, one of them is the main signal has an amplitude of 6 milliwatt, or excuse me, 6 milliwatt, then the interfering signal should not be more than, should not be more than 1 millivolt. So that is the issue. And we work on that, and it is okay. And we also consider larger data sets or some different data sets as option. And also we consider some different augmentation techniques. We make the augmentation to all the trained data set, but there may be some other approach, and we are working on that, and we hope we will have some good results in some other paper, but just, maybe just a bit more time be needed. So also in this project, we have another line. We consider additional layer with phase information. Because we generally use DC offset, when you consider DC offset amplitude, okay, that is the main value, main feature. But okay, phase can be also considered. Phase offset can be considered another feature. So we also work on that, and IQ compensation. And these are our references. When you consider the second reference, that may be our main work, main close work. We work on that. And also the fourth one we also consider, but not more especially. We use the data set. When you consider the second one, it says powder. We use that data set. What's that? Okay, in the last one, I will just say thank you and thank you for your listening patience. And as I say, my name is Ömer Meykül, and I am from the University of Ottawa, and our project leader, principal investigator is Dr. Burak Kantarci. So you can send me or Burak Kantarci email if you have questions, and of course I'm happy to take your question here.
I think we have limited time, so okay, so for your data generation, what additional data
Excuse me?
I mean, so what additional data you generate by your generation model?
You say additional data?
Yeah.
When you consider augmentation, we have the data. Okay. What we do in augmentation, we can do different augmentation techniques, but what we do, augmentation is to increase the amount of data to learn that. So we try to increase the amount of data on day one. And by making the transform TDL and CDL, we create some new bin files. For example, in the TDL, we produce 60 more bin files from the 60 day one data. And similarly for CDL, we did the same one. And then we make our, and then we run our code, and then it gives this result.
Okay, thank you.
In fact, I give my email, but the last slide is not working. So that is why I can come to the first slide. And yeah, this one is my email, and this one is our professor's email. Thank you very much for listening.
Yes. Plug this in. Hopefully this works. Okay. Okay. Great. Is that full screen? Is this one? Oh, it does work. Oh, weird. Okay. All right. Great. Hello, everyone. My name is Stephen M. Hernandez, and I am here from the Department of Computer Science in Virginia Commonwealth University. And I'm presenting our work on online stream sampling for low memory on-device edge training for Wi-Fi sensing. This is not, okay, that's fine. So the goal of this work is to allow for on-device edge training for Wi-Fi sensing. I want to emphasize that. So towards that, in this presentation, we're going to look at the background on Wi-Fi sensing, background on online stream sampling for machine learning, and look at the introduction of our proposed system for variable low high loss our sampler. We're going to look at a few comparisons and evaluations and then conclude this presentation. So what is Wi-Fi sensing? Wi-Fi sensing, the goal is to use Wi-Fi not only for communication, but for sensing physical attributes or physical actions that are occurring within the environment. If we can use Wi-Fi, then we can leverage those signals that are already existing in the environment without having to necessarily add more hardware in every single room or anything like that. So the key idea is this allows for device-free sensing. We do not need to have wearables or sensors on the body of the person that we are trying to track. And also, Wi-Fi is omnidirectional. So a camera-based system is also device-free. We do not need sensors on the body for a camera. But a camera has a small field of view, while Wi-Fi or radio-based systems are transmitting omnidirectionally, so we can essentially sense in a full field of view in a 3D environment. Additionally, Wi-Fi is designed to propagate through the walls, so we're not only stuck with sensing in one room, we can sense in rooms through the wall in additional rooms. So here's a quick illustration so that we make sure we understand the idea of Wi-Fi sensing. We have our transmitter on the left and a receiver on the right, and the transmitter sends a signal and it propagates through some signal path. And we can describe this signal path using a metric called channel state information. Now, like I said, it's an omnidirectional transmission, so it's not just a single path that necessarily goes from transmitter to receiver. So if we add a person doing some physical environment, well, that original signal path is going to remain, but there's going to be another signal path that's going to reflect off of the body as they perform whatever action. So we should be able to use channel state information to gather some information about this multipath environment. So here's a quick overview of channel state information. We can use channel state information to understand the amplitude and phase changes on multiple subcarrier subfrequencies using orthogonal frequency division multiplexing or OFDM. So each of those frequencies has a slightly different variation of the frequency, and thus the multipath environment will have small changes against each of these different subcarriers. And this is going to be a really very high-level overview of machine learning. So for machine learning, we're given some input X and an output Y, as we all know. And we want to find some model that minimizes some loss function. So for our X, we're just using that channel state information. And for Y, we are trying to detect, it could be a set of activities. Here in this illustration, we have no activity, and then the activity occurs. So this is just a binary sort of thing. But you can have multiple classes. So there's a lot of Wi-Fi sensing research that's occurred so far. But really, I want to focus on edge-based systems, so very small devices. The issue with non-edge devices, which is what most people are looking at, is that we require high computation speeds. We need multiple GPUs or server farms to train the model and also make predictions. And if we're using a server-based system, then we're going to have a network round trip. We collect the data at the edge. We send that data to the server to make those predictions, send it back to the edge to actually integrate with something like a cyber-physical system. And that just adds a lot of time and latency. It's also poor scalability. If we're using, even if we're just using a GPU that is, or multiple GPUs on some desktop system, let's say, that's going to be high. It's going to be a high equipment cost. So we're not going to be able to deploy this at a large scale like you would see in regular sensor-based systems. So with the proposal here of using edge-based systems, we should achieve high scalability because we can use very low-cost systems and microcontrollers. For example, this is a very small device, the ESP32 Wi-Fi enabled microcontroller, which is what we use in our experiments. It's all system, it's all built together. You don't need any additional hardware necessarily. So for this, you do not need networking. To make those inference, you should be able to create some very small model, some tiny model that should be able to run on this device. Now, of course, there are problems with going to an edge, a small embedded sort of system. And those problems are described here. We've got slow computation speed, and we've got very low storage space. So the solution that we are looking at in this presentation and in our paper is to store fewer, but more important samples within a buffer to help personalize or train our model on the edge. So this is kind of the description of how that would happen. Per X and Y sample that we talked about for machine learning, we need to think about, should we store the sample in a buffer? And if we store it in the buffer, which samples or which preceding samples should be replaced? So in this illustration here, there we go. We've got our transmitter on the right. It's transmitting our wireless signal over, passing through multiple people doing whatever physical actions to the receiver. And the receiver collects the CSI, passes it to a stream sampler, which decides, is this sample important? If it's important, then we store it in the buffer for training our model. And if it's not, we just discard it. Now, this is an online system, so once we decide that we are going to discard the sample, we will never be able to see it again. So once we have our buffer, we can, like I said, pass it into our machine learning model. Now, there are quite a few sampler methods. There's more in the paper if anybody's interested, but the more interesting ones are looking at, let's start with 1 and 2, most recent lowest loss and most recent highest loss. So every time a sample comes in, we can run the sample through our model and calculate the loss, that is the loss per sample. And the idea for the most recent lowest loss is that we want to find the samples that have the lowest loss. We want to retain those samples and discard any that have higher loss. The idea is, if our model is doing well with these samples, then we guess that those samples are representative. And if they're representative, then we should retain them and not lose them, because then we might lose representative data. Now, the most recent highest loss method, on the other hand, takes the opposite approach. A high loss corresponds to a very high error. And if the model sees samples with high error, we assume that the model is not good enough. And it really needs to look at those problem areas, and it needs to store those so that it can continue training on those samples. Now, both of those methods have conflicting purposes. So what we're going to then show here is that we should have a variable amount of both lowest and highest loss samples. We should not just go for one or the other. So that's where we introduce this next part, which is the variable low-high loss sampler. So when we perform our experiments here in this work and in our paper, we take an approach kind of like this. We collect data over multiple rounds of different activities. Here we have 4 different physical activities happening in the environment. In round 1, our sampler must select which of those samples are representative. And then after the round, we give a small period for training. We do not train while collecting the data. And after that training period, then we can go back and collect some more, another round of physical activities that are happening. Now, our assumption is we have a small device that has a buffer that is so small that we cannot store all of the samples even from a single round. So we really need to find what are those important samples in that round and which samples are available from the previous rounds, and make sure we select those really important samples, because otherwise we will lose them. We will not have the ability to train on those samples at all. Now, in this illustration, we have 3 rounds of collecting activity data, but in our final experiments, we actually have 25 rounds of this. So here's one of those, one of our evaluations. We can see on the left side, we've got an x-axis that shows those 25 rounds. And on the y-axis, we have the number of samples that are retained. So let's look at the most recent lowest loss, the blue line, and the red line, most recent highest loss. Those are what we're really focused on comparing. We can see as we get to round 7, the blue and red lines start retaining 100% of their samples. They're essentially getting stuck with whatever their high loss or their low loss samples are. And if you get stuck, you're going to be repeating training over the same exact small amount of data. And if you keep training on those same samples, your model might not be able to increase in accuracy. Now, the VLHL method, our variable method, shown in black here, does not have that same problem. We do not retain 100% of our samples at any point in these rounds. So if we then look at the right-hand figure, again, on the x-axis, we have the rounds from 0 to 25, and we can see that those blue lines and red lines at round 7 do end up getting stuck with the same poor accuracy because they are retaining the same samples over time. But our VLHL method actually continues to increase in accuracy beyond this. Now, there's a couple of variables that we want to look at when we are training. So after each round, we do our training for some number of training epochs using our buffer, and we also have different internal buffer sizes. On the left side, we have the number of epochs that we train at the end of each round of data collection. When we have a very low number of training epochs, obviously, we're not training for very long. So our model accuracy is very low. And as we increase the number of epochs, our accuracy can increase because we have more time to learn from these samples that we've collected. But we find that, well, as you increase the number of epochs, the longer the period is in between collecting data, and that just extends the time it takes to train and collect data for the system. So what we find is, even with something like 10 epochs, we can get a significant accuracy. It's similar to running for 50 epochs at the end of each round. So we do not need to continue to increase number of epochs just to increase our accuracy. On the right-hand side, we can see on the x-axis, we have the buffer size, and it increases from left to right. We've got our accuracy again. And of course, as we increase the buffer size, the accuracy, again, increases. We have more data that we can use to train our model. What this shows here is that when we have very small buffer size, like on an embedded device, it's really important how we select our important samples. If we do not select, if we do not make good selections, then we're going to have a problem. We're going to have very low accuracy. But if we're intelligent, then we will be able to achieve greater accuracy than if we select poorly. Okay, that's not the right button. All right, so in conclusion, the goal of this work was to move towards allowing on-device edge training for Wi-Fi sensing. And the way we worked towards this in this presentation is to introduce our variable low high loss sampler, which reduces the storage required for online training and increases the accuracy compared to other samplers. Now, the future work is, there's so much more that can happen with edge training. This is just one small component. There's so many different things. Someone, the earlier presenter talked about things like quantization and different model pruning and things. There's so many different things to explore to improve edge machine learning. So that concludes my presentation. If anybody has any questions, you can email me, or I'd be happy to take these questions now. We do have so based on that ESP32 microcontroller, we've been working on a tool to try to collect that CSI, or to collect the CSI and to allow for this edge-based sort of system. So if anybody's interested in looking further in the edge for Wi-Fi sensing or anything with channel state information, please feel free to take a look at this. So thank you.
Is this one question about the edge training process? Since this training process occurs with labeled data in a supervised setting, how can we assume that in some edge environment we're able to conveniently have these labels?
I absolutely agree. That's a big challenge. So one of the things, there's a few ways that you can handle this sort of thing. Let's say we have some sort of co-system. So we've got a camera and we've got a Wi-Fi. Well, the camera, again, has a small field of view. It can recognize the actions happening over here, and it can use those potentially as labeling data. Now, of course, it does not understand what's happening behind the camera, so we cannot get the labeled data back behind the camera. But what we can do is something like that. Find a co-annotator system. Thank you.
Thank you for sharing this good tool. And let's follow the first question. I think for the RF sensing, the challenge is how to segment data set for the different labels, right? Okay. So you use the camera. And for this one, you have the training stage and how to determine to transfer from training stage to the test stage.
Training to the test stage.
Yeah.
I see. Yes. So that's a good question. We do not have that here. When we do our simulations, this is not a real-time training versus testing. We actually, I mentioned I have 25 rounds of collecting data. Those 25 rounds are for the training. And then afterwards, I have 25 rounds, which is what I use for evaluating. Those are never seen by model. But yes, there needs to be more work to figure out how best to allow the training testing split in real time. Absolutely.
Do we have additional time? Okay, another quick question is that, so, and for your current system, and how to, okay, so you can separate the training and the test, and also for the online part, how to train. Okay, I can ask this question after this. Okay.
No, yeah, we can talk more afterwards, absolutely. But that's a good question. There's a lot to it. Absolutely. Thank you.
Great talk. Thank you for that. Just a quick question follow-up to the camera point you highlighted. If you focus on only one centric approach of the camera to collect the data, wouldn't that kind of deviate from the omnidirectional strategy that you're trying to implement? Well, how do you approach that?
So we do not use the camera based here. That's just an example.
Okay.
Absolutely. But like I said, the camera does have a small field of view. So can we use the field of view to find the true labels and then also use it for behind the camera, so that outside of the field of view? So the camera system does exist, but it's not capturing everything while Wi-Fi sensing should be. But
do you think like 360 view might help, perhaps, to make it more omnidirectional?
That's true too. That's true too. One other area that we're looking at is not only the idea is to have these very small edge, these embedded devices that are very cheap and can be deployed everywhere. Not all of those devices necessarily need a camera. So can we collaboratively learn from some of the devices that have cameras and use that for devices that do not have cameras? So maybe that's a better way to explain that.
Yeah, thank you.
Thanks. All right, thank you.
No, I think this is something.
The deep learning localization. Yeah, I'll get that one.
You can use this.
Great. Okay, thank you. Good morning, everyone. I'll take this off. My name is Frost Mitchell. I'll be speaking on our recent work, deep learning-based localization in limited data regimes. This is a joint work with my co-authors Anika Bassett, Sneha Kasera, and my advisor Aditya Bhaskara, all at the University of Utah, as well as Neil Patwari at Washington University in St. Louis. As wireless devices become more and more ubiquitous, the unauthorized use of these devices also becomes more common. One particularly infamous example is a man in Florida who drove for 2 years with a cell phone jammer in his car on his daily commute before he was apprehended solely due to the labor-intensive work of one particular telecom company in the area. We would hope that as cognitive radio and dynamic radio networks increase the ability for flexible spectrum sharing and allowing devices to potentially have the hardware to transmit on far more frequencies than they typically do now, we could have some sort of more robust, more responsive localization system that hopefully wouldn't take 2 years to find a violator. We envision a crowdsourced system where a spectrum monitoring authority can request data from a pool of legitimate authorized users in a network, and this user data would be shared with the spectrum monitoring authority, which they would use to perform localization. In this crowdsourced setting, we're not assuming that the crowd is made up of specialized hardware. Instead, it would probably be inexpensive consumer devices. And so without specialized hardware, it would be more difficult to run typical localization algorithms such as time delay of arrival or angle of arrival, which require some careful synchronization. Instead, we assume that these devices can only provide received signal strength values or RSS values to share with the spectrum monitoring authority. As well, similar to other works in this setting, we are assuming that there may be multiple transmitters in a given environment rather than just one device. Our localization technique is called TLDL, or transmitter localization using deep learning. We view localization as an image-to-image transformation process. This may be a novel idea to some of you. The idea is that an image representing a 2D map of the location of each sensor is transformed by a neural network into an image representing the XY coordinates of each transmitter. This idea was introduced initially by Zubo in 2020 in the DeepTX Finder model, and then more fully as the same image-to-image transformation setting by John also in 2020. So the general training process that we have is as follows. On the left there, we have a set of sensor devices shown as the small handsets, and then we also have multiple transmitters shown as the blue towers there. And we take the set of sensor devices, which includes the XY coordinates of each sensor and the RSS value, and convert that into an image, this sensor image X, where each non-zero pixel in X represents the location of a sensor. And we set the value of that pixel to the corresponding RSS value. We perform a similar operation for the transmitters. We take the location of any transmitters in the environment and create a target image Y, where each non-zero pixel represents the location of a transmitter. Note that our convolutional neural network here is not trying to predict the coordinates of each transmitter explicitly. Instead, it's just learning to approximate this image Y. Right? We're only approximating this target image. For a loss function here, we use the mean squared error. You might have noticed that this is, in fact, a binary classification problem where we're determining if each pixel is or is not a transmitter. However, in our experiments, using a cross-entropy loss, such as would typically be used in a classifier, fails to learn anything viable, presumably due to the weight imbalance of the two classes, that most of the pixels in an image do not actually represent a transmitter. During our inference process, the pipeline is slightly different. We similarly take the input of sensor information, produce an image X, and then feed that to our convolutional neural network, which then outputs a prediction Y hat. But this Y hat will necessarily contain some noise and artifacts. So we introduce a threshold where any pixel values below a certain threshold are set to 0. And we also use a mask operation, which suppresses transmitters in the immediate vicinity of one another. After this threshold and max operation, any non-zero pixels remaining in the image are output as the set of coordinate predictions. As well, you can observe that this process of taking real-world XY coordinates and converting them into pixel locations will have some discretization. This distance represented by each pixel is a tunable parameter specific to the problem and environment you're operating in. In this work, we use 1 meter consistently as the distance for each pixel. For our convolutional neural network, we use the UNet architecture, which is originally used for image segmentation. Briefly, the two main advantages that this architecture offers is, first, it has a very large receptive field. If you're not familiar with this concept, the receptive field is a measurement of the number of inputs that are used to determine a single output element. So in other words, the amount of physical space that one output pixel can represent in the learning process. As well, this network has residual connections between early and late layers, which allows us to train a much deeper network, and relatedly, it allows us to preserve some of the high-resolution features that we may learn in earlier layers of the network. We expect a technique such as this to be deployed in an environment with very limited training data. To compensate for this, having a very small set of sensor and transmitter locations, we introduce some data augmentation techniques. The first is this sensor dropout, which is essentially a way to simulate a smaller crowd size of data. So given some sensor locations in a single environment, we randomly sample this set of sensor locations to choose a small subset that becomes our limited crowd for this single sensor image. This is partially to provide some variability in the training data set, and it's also it gives us the ability to simulate a more realistic crowdsource setting where we might expect only a very limited number of transmitters rather than the number of transmitters that we could collect during some dedicated data collection phase. The second data augmentation technique we use is simply just to inject some noise via the power variation. So given this small set of random transmitters in a single training sample, we randomly vary the power of this set by up to 20 decibels, which may seem excessive, but we observed even greater variation than that in actual real-world data and not just in simulation. We evaluate this technique on 5 real-world over-the-air data sets. 4 of these are from previous works by my co-authors. They range from various environments such as outdoor parks, to large indoor spaces that are 20 by 20 meters. For this work, we also collected one data set on the Orbit testbed, which is an indoor testbed with open access to various software-defined radios. One thing I might point out is that these environments are not typically open. There are a variety of different obstacles and walls. In one data set, for example, the entire environment consists of 4 square hallways surrounding a very large collection of office space rooms, so there is no line of sight anywhere in the entire data set. For each of these data sets, we extend the number of samples that are shown here to 5,000 for training using our augmentation techniques. Before we can discuss results, I wanted to just review some of the metrics that are used in evaluating a localization technique. First, we have the most obvious one, which would be the localization error, or the Euclidean distance between a ground truth and a prediction. We can also have cardinality errors, which would be an error in the number of predictions output by our system. We could have misdetection, where we are under-predicting the number of transmitters, or a false alarm, where we are over-predicting the number of transmitters. And then last, we have the optimal subpattern assignment metric, or OSPA, which is a sort of hybrid metric that combines our localization error with a fixed penalty for any cardinality error. In this case, we used 15 meters. We compared TLDL against 4 other RSS-based localization techniques, including 2 deep learning image-based techniques, Deep TX Finder and Deep MTL. We found that we outperformed all the other techniques in the OSPA metric. In this table here, we break down these results specifically into the localization error and the cardinality errors. The results shown here are the average of 3 different random trials with unique training and testing splits. In particular, the impact of our large receptive field can be seen by comparing results from TLDL and Deep MTL. Deep MTL used a very similar fully convolutional approach to this localization problem. However, they have a very restricted receptive field. And in these results, it would seem to indicate that this has occurred in a much larger cardinality error. Next, we compared the performance of our data augmentation techniques. We trained TLDL with and without this augmentation. Datasets 1 and 2 have a very limited set of samples of only 44 unique transmitter locations. And so we can see a clear improvement in applying this augmentation technique. Datasets 3, 4, and 5 have a much larger training set of 400 and 1,500 samples, and so we don't observe the same improvement in performance. So in summary, we do see a huge improvement in accuracy by applying these localization techniques, or these augmentation techniques, excuse me. Last of all, in implementing a localization system such as this, you would expect to have a reasonable runtime. Here we have measurements of the localization techniques on a 12-core AMD CPU. For each of the deep learning-based techniques, we are able to evaluate a single image in less than 15 milliseconds. So in other words, this is easily fast enough to be part of a routine spectrum surveillance routine. So in conclusion, we presented TLDL, a deep learning-based localization technique. We presented a novel data augmentation that can be used to simulate smaller crowds and to train effective models on very limited data. And then we've shown that this technique outperforms others in 5 small over-the-air data sets. However, there are many reasonable extensions that could be made. First, we've shown that this technique works on very small areas. Another question is how it would work on a large scale. The Powder testbed at the University of Utah is a 2 by 2 kilometer open access over-the-air testbed. We intend to evaluate TLDL in this area and observe how the larger scale of this environment can impact our accuracy and our runtime. Additionally, every time you train TLDL, it's tuned to the specific environment. We would hope that with some adjustments to either the architecture or the type of learning model that's used, it could be possible to transfer a model between similar environments, or at least to allow for a convenient fine-tuning on a very small amount of data. Our initial tests have shown that with at least the data we have now, we haven't observed any reasonable improvement in transfer. And finally, in a real application, TLDL would be receiving data from a set of very heterogeneous devices. We expect that as well, some of these devices could even be adversaries that are trying to either disguise behavior or direct attention away from certain locations. And so TLDL would need to be robust against such an attack. This concludes my presentation. Thank you very much. So we don't, the noise that we're adding is actually just a random scaling of of the power of each of our received transmitters, right? It wouldn't make sense, for example, to add a Gaussian noise to the image, because in the image, we know 0 values represent not a receiver, and then a non-zero value does represent a receiver.
You randomly generate from what, for example, from MATLAB or another tool, or I say, is that noise is generated from a real sample, or how you generate? We say noise, when you consider noise, it is okay. You can add quite many noises.
So it's simply just a random scalar that we're varying the power of our receivers by.
Okay. And when you also say 20 dB, it is about 20 dB when you consider that 20 dB less than the main samples, the amplitude of main samples. So
it was 20 dB less than the maximum value received. So we actually just decreased by a random value up to 20%, which was about 20 dB, but would vary depending on the maximum value of the sensors in that set.
Thank you very much.
Thank you for your talk. I had actually 2 questions. One was, so how do you decide how to deploy these sensors? I guess the topology of these sensors would affect your accuracy. And the second one is, how does the transmitter power affect your accuracy for localizing the transmitter's location? Thank you.
Yeah. So for the first question, we are assuming that we don't have the flexibility of determining where our sensors come from. So for example, in a crowdsourced setting, we would not have control over where the users are going, or like in the powder test bed, the radios are at a fixed location with a few mobile radios, but again, we do not control the position of those radios. So as to being able to have more accuracy in certain locations based on the positioning of our sensors, that's completely right. And we wouldn't expect to be able to provide perfect coverage without control of these sensors. And then your second question on the transmitter adjusting their power based on the environment characteristics, that's essentially what the second type of augmentation is intended for. The ability to increase or decrease the received power at the set of sensors would be mathematically equivalent to increasing or decreasing the power of a transmitter. Generalization over unseen channel environments and your model I actually have some preliminary data on this. The answer is not very well. So that's, I think, the open question that remains to be solved, right? How can we train a model that could do well in even a very similar environment? Yeah.
I also have a question, 2 questions. Number 1, why is your data images? Couldn't you, this is my second question, have you considered taking an image and converting it into a different format, like let's say a line, by using like Hilbert curves?
For the second one, we have not considered any such thing. As for why we're using images in this space, An image is a convenient representation of a spatial domain, right? So in this case, we're using this set of coordinates and converting it to an image so that we can provide a clear spatial representation of the distance between the sensors that we have. Is this the most appropriate thing to do? Probably not, but it does seem to work reasonably well.
Thank you.
All right, thank you very much.
Okay. Good morning, everyone. Today I give talk about the voice fingerprinting for indoor localization with single microphone array and deep learning. And I'm Xu Wang. I'm from California State University, Sacramento. This is joint work with my student Shivan Kumar and student Chao Yang and Professor Shivan Mo. Okay, this is outline. I will introduce the four part. First one, I give the background for the voice localization. Second part is I discuss the system design, and then we discuss the experiment study. Last one is I summarize my work and discuss the future work. Okay, so first one is let's discuss the background and introduction in this work. And as you know, as increase of the Internet of Things, okay, there are many smart speakers now in the smart home, and like the Amazon Echo, the Apple HomePod, and the Google Home. Okay, so if you check the bottom figure, you can see the global smart speaker market will reach $19.91 billion in the next 2 years. And based on this very large demand, okay, we know the smart speaker open another new interface for the users. We can use the smart speaker to have some connection to the internet to control some other smart home device. Okay, so based on that, there are several applications for the voice control of the smart home device, or like the human-computer interactions, or some voice-based application. Okay, so we just discussed one application for the voice-based indoor localization, and because voice localization can improve the smart speaker's performance in the different ways. Okay, for example, if we consider communication, and if we do the long range, like the communication, and for these things, if we know the location, then we can do the beamforming and to point that the audio signal to that person. And second part is that if we have the location, and this location can provide useful contact information, which better to understand user's intent. Okay, for example, if user want to turn on the light, and also that smart speaker can determine which light can be turned on based on the user location. Okay, third part is that, we know localization is used for the location-based service, right? And so the voice localization can offer localization-based service. And for example, the smart speaker can automatically adjust the room temperature if smart speaker know where the user is, so which can reduce that energy. Okay, so many applications are on top of the voice localization. Okay, so what's the challenge for voice localization? I think last talk discussed about like the multiple transmitter localization. Here is for voice localization, I think this is very hot and very interesting topic. And for this is we can use like a smart speaker. We have the microphone array to estimate the user location. And what's the challenge for that? There are several challenges. And the first challenge is that in the indoor environment, there are multiple paths from the speaker to that like the Amazon Echo node. And also there are some, for example, the red part, they're non-null set. Okay, so the wall block the signals. So for the microphone array, just to record and receive the very weak signal. And the third challenging part is it's challenging to get the signal source. So this is unknown for that. Traditionally, it is for the microphone array, it is very challenging to estimate the distance. And so the last challenging part is that, especially for the indoor environment, current work in order to estimate the user locations, I need to know the indoor environment deployment. For example, know the position of the microphone array. Okay, on top of this, so many challenge problems, and also we give the current work and the current solution. And I think 5 years ago, also there are a lot of work for the voice localization, but for that case, I need to use the multiple, that microphone arrays rather than a single one. Okay, if we have the multiple microphone arrays, then we can use geometric-based method for that voice localization. For example, we can use we can estimate time delay of arrival, TDOA. Okay, use that general cross correlation and phase transform, this solution to estimate that. And also we can use like a multiple signal classification, music, to estimate direction of arrival. So all these methods needs that allow set to determine that location. And what's the state-of-art work? So 2 years ago, from the MobiCon paper 2020 that proposed the Warlock. So this is the first solution, just use the single microphone array to locate that user. Okay, specially proposed integrate learn and cancel algorithm to find the location. And follow this work, the first work just focuses on a single user. And can we extend to the multiple user? So this is a very, very challenging scenario because they need to handle multiple paths, also multiple users. So this solution to propose the future to distinguish for the different signals. And another one is, new version is, can we also previously to estimate especially to the angle arrival, and how to combine that deployment and like the direction angles together to improve the performance for the single user. So this is from the NSDI work last year. And what's the limitation for current work? What's the challenge part? I think this still is the open problem using the single microphone array. So the challenge part is that the number of the paths on non-set component are not easy to determine. So we need to consider how to estimate that how many, the number of paths. Second part is that, so all these three work needs to estimate that the room structure. For example, the distance between that microphone and the wall, all the angles. Based on that structure, then just use the single microphone array to estimate user location. So let's focus on our work. We just propose very simple, easy solutions called fingerprinting-based solution. I think today we have the several RF fingerprinting. And we use fingerprinting for indoor localization, also include 2 stages. And the first stage is offline training. We collect that data and the location pair, and we train a model, use deep learning. And the second stage is that if the device collects new data and feed the data to the neural network to predict location. And this solution is very good in non-null set, also in the multiple path environment. And so many work on top of fingerprinting from the received signal strength RSI to current channel state information. And also our work also proposed several CSI-based fingerprint-based localization from DeFi to current wrist lock. And on top of our previous work, we use this idea for the voice fingerprinting and to handle that multiple paths in the indoor scenario. Okay, so this is the introduction part. And the second part, we can discuss our system design. Okay, for this system, you can see we just used a single microphone array and to collect audio signals, and also including the two-stage and offline training and online test. And before the offline training and online test, we have the data pre-processing to transfer the audio signal to the image signal. And for the offline stage, that especially we use the short-term footage transfer to transmit audio signal to the image signal. And we also validate different deep learning models because we get image data. We can consider use transfer learning, use the pre-trained weights to adjust to our small data set. And then for the online test, we can collect that spectrum data set, feed our neural network, and also we propose top-K probabilistic method for the localization. Okay, first let's check out the voice data pre-processing. For the voice data pre-processing part, we can see here the right top figure to show that just in the time domain that figures. Okay, for this one, we cannot extract any frequency domain data. So first solution is we just use fast Fourier transform to transfer from the time domain to frequency domain. Okay, and another solution is we also can use the several time frequency transformation solution like short-term Fourier transfer, and which can extract the data in the time and frequency domain at the different time intervals. Okay, so after we transfer the audio data to the time frequency domain, we can get some features. We can check out our this feature in the time and also some feature in the frequency. Okay, for example, this figure shows we collect that data in 3 seconds and also up to the 48 kHz. Okay, another one is quickly, I think this is fundamental things. I quickly introduce that. And we use deep learning on which model we need to choose, right? Deep learning, I think this is one type of the machine learning, and special for the large data set or image data set, we can use the deep learning for the classification or for the regression. Okay, which can handle automatically to extract the features, right? And to handle large data set class classification task. And also deep learning can get the higher classification accuracy. And okay, which model we use? And we know currently we have the traditional 3 models. And the first model we consider autoencoder. Autoencoder is to denoising or to get features. Second part is the convolutional neural network. Definitely this work on top of convolutional neural network because we get image data. And the third one is long short-term memory, LSTM. And in the future, we want to combine this solution for this voice localization. Okay, so on top of this remodel, we focus on the deep convolutional neural network. And currently, there are several architectures, right? State-of-the-art architecture. And this work is just to validate that performance. For example, we validate the Inception version 3 and ResNet 101 version 2 and Inception and ResNet version 2. Okay, last one is combine the first 2. And because this is with a very large number of the weights, okay, in our new data set, we can use the pre-trained weights to adaptive to new data set. And we can consider the fine-tuning the transfer learning. Okay, so first model, Inception 3, version 3, I think this is very good image classification model, and we get very good results in ImageNet. Okay, and we first validate this system, and we can reshape our spectrum coherent image to the input size of 299 times 299 times 3. And also we use that pre-trained ImageNet weights to learn the feature of our the audio spectrum data set, use transfer learning. Specifically, we just fine-tune that the fully connection layers weights, and also to fix the lower layer weights. And then our output, this part we just consider classification. So our last fully connection to attach the soft marks to use the 15 output nodes for the 15 locations. Okay, second model is quickly introduced that this is the ResNet, very popular solution. In 2016, this got the top 1 accuracy in ImageNet competition. And we use this one, and the basic feature is that there is the residual block, and also our previous CSF-based localization. Also, we propose like the deep sharing convolution ResNet network, and we just on top of that, and use this for this voice localization. Last one, can we combine the first and second together? This is a very powerful model and intercept the inception framework and ResNet the framework, and so make this network deeper and wider or get that features. Okay, so let's check our training data set. We consider 2,400 spectrum image for the model training, and also 615 spectrum image for the validation, and also our parameter like this. Okay, so because we just use classification model, right? For localization, most of our work use regression. And for the classification model, directly used classification model, it get very poor accuracy. So our solution is, okay, if we get that especially top K or the prediction labels probability, we can use that to choose the top K output probability. And then the final user location is estimated as the weight or average of top K locations. Use this equation. Okay, especially the LI, that is the training locations, and the PI, that is the output of that neural network. Okay, so in this paper, we consider top 3 output for the location estimation. Okay, let's see our experiment study. And especially we validate use the real testbed with the especially current, this is very popular testbed for the microphone array, because first one, we have the several smart speakers, but the current smart speaker cannot report all original audio signal. So we need to use like the Raspberry Pi connect the real speaker, and there are 2 types of speakers, smart speakers. And one is 6 circular array, another one is 4 circular array. And we validate this system for the test, and we just, this paper, we just show the 6 microphone arrays. And also we train our model with the Google Colab Pro and with the TensorFlow. And we validate this system in the 2 scenarios, the students, the room, and one is smaller, the environment, and 5 times 10 meters areas. Now the left part is larger areas, and including the dining room and the living room, and also the different areas. And we just validated this system. Can we get the unit feature for the localization? So you can see that here we use different color to represent, that is training data set and test data set. You can see training data set and test data in the different locations. So for on top of that, definitely there are different distribution. And if we choose the classification model, definitely for the confusion matrix, this is not very good. Okay, let's show our performance part. And the first one is if we consider inception vision 3, and if we just for the 15 location, output location, we directly use that convolution neural network in inception 3 to predict that the accuracy very small, not very high, just 0.6. And but we can see based on the computation matrix, we can see most of like the top 3 and with the similar locations. So we can, after we print output that probability, we can merge these top 3, to calculate our location. So red part shows that, the CDF over the errors. You can see the median error of our system is under 1 meter. And if you check out that 80% of the error that under like 3 meters in the room. Okay, so second part is get the similar results using the ResNet 101 version 2. And the last one, we show the inception and ResNet version 2. Combine that together, we can see for this model get the small better results compared the last 2 models. Okay, we can control, like you can see the 0.5 that the median error is like 0.7 like this. Okay, also the 8% of data, the error under okay, the 2.5 meter. This is good enough. Definitely there are some, okay, the incorrect locations just with small probability and just larger errors. And especially we can also compare the top 1 and the top 3 that errors over the 2 environment and also with 3 models. We can see our last model for the, especially for environment 1, get the mean error, okay, so that is 1.6 meter, and in environment 2, we get 1.55 meters. And this also better, especially this is just top 1, and if we consider our solution is top 3, it can reduce the error, okay, smallly, so from 1.6 to the 1.56 meter. Okay, let's conclude our work. So in this paper, we validated voice fingerprinting for indoor localization using the single microphone array. So this is first work used that single microphone array for the indoor localization use voice signals. And we discussed our architecture, and we used the spectral image to train that model, 3 models. We propose use top key probability method for the location estimation. And we show the result, last model can get best performance. And in the future, definitely we want to augment our data set, and we handle the different domain, like the different days and the different scenario, and to improve the robustness of the voice-based localization in ANSI, the scenario. And also combine, because previously we can use GCC and to estimate DOA, we can use this one to narrow the searching area for the localization. Second part is that if we collect more data set, we can also use the regression model to predict that the location. Last one is, this paper just assumes that there are just a single user to speak and a microphone to estimate location. In the future, also we want to extend from single user to the multiple user, like up to 3 in the one room, and just use single microphone arrays. Okay, thank you. Any question?
Hi there. Localization for the voice is an interesting idea. But you collected the data, or your group has collected the data. What was the actual words that were spoken?
Okay, so there are 2 solutions to collect data. For example, first one is like the speaker can say something like, hi, Alexa. Okay, the second one is also we can record this, use speaker to replay this sound. And then our microphone array, we use this device can record that data for the training.
So you say you use the speaker for the source?
Yeah, speaker is source. There are 2 types of things to play signals. One is human, we just see, like, hi, Alexa. Second one is we use speaker to play that signals.
Okay. And then also, on slide 22, could you repeat what the difference is between top 1 and top 3? What is the 3?
Okay, so thank you for this question. And the top 1, that means, that is back to the basic classification. For example, for the soft marks, for the 15 labels, that show the 15 probabilities. Top 1 just means we just use the maximal probabilities as the output, right? And top 3, we choose the top 3 maximal probabilities, and then we use the weighted average to get estimate location.
Okay, thank you.
Okay, thank you for your question.
Thanks for the presentation. So I do have a question. So for example, for the voice localization applications, what are the real requirements for the localization accuracy? For example, it looks like for the applications that you mentioned, we don't really care about whether you are 100% accurate or, within, for example, a few milliseconds or things like that. But what we care maybe just like which room I'm currently in, or we don't really care about the exact location.
Yeah, exactly.
But we really care about, based on application, maybe the rough region that I'm in.
Yes,
so
yes.
In this case, if our requirement is just not that high, why the existing work cannot satisfy that? So why should we, using those voice localization to improve the accuracy to that high level?
First one is that's a very interesting question, and so currently for the room level, we just consider okay the person in this room or another room. That is enough for so many applications like turn on the light or turn off. And the current solution is for smart speaker, mainly use the DOA, right? But the DOA, I mentioned that challenge. There are multiple paths in one scenario. And currently there are 3 still are work from top conference to show that. But also that very challenge to determine, okay, how many source, how many how many source, how many like the paths from the source to this. This still challenge for the model-based. So we use the easy solution. Can we use the learning model, okay, to predict that directly? Simple solution to address model-based challenge. This is the idea for this paper.
So what's the advantage of voice localization compared to the Wi-Fi localization, for example?
I think this is complementary technique. Wi-Fi also, we know there are several current, several work, and also there are some limitation for the Wi-Fi because current no any app for the Wi-Fi based indoor localization. And the voice, we can say that one is for localization. We have the location, we can improve other function for the smart speaker because current smart speaker is very, very important, that interface between the user and that device. If we can do that, we can do the beamforming or other contact some activities for the smart speaker. So I think that gives additional directions for this area, for the indoor environment.
Okay, thank you.
Thank you for your question.
Okay, actually now is the time for lunch, so I will keep this presentation quick. I'm Yishi, I'm a research associate professor at Virginia Tech. This work is on, basically it's on IFO emulation and its applications. So what is IFO emulation? Usually when we're talking about transmission, that means we have a transmitter to transmit data intentionally. But IFO emulation is you have some micro device. This device is running some code or running some programs. When it's running, it will release some IFO signals, and this is anti-intentional. This can be recorded by some probe or some antenna and can be saved by some device, and then we can analyze them. If we analyze them, this can reveal some information. For example, we can know whether there is a device nearby is running, and we can know whether there is a device that currently is running some programs. And by using this information, one can perform a side-channel attack, such as we can attack the crypto algorithm on the device. Another application is if we use IFO emulation, actually we can use it for transmission purpose. And the benefits of this is there's no additional energy consumed because we already use the energy to run the code, and in addition, we can use it for transmission. So there are different use cases, cover the communication, low power device monitoring, and energy efficient communications. The first task is we need to detect this IFO emulation. To detect it, we set up Android microcontroller in this study as the device, and the clock frequency is 16 megahertz. We need to sense at 16 megahertz or its harmony frequency to receive this IFO emulation. But in addition, we need to isolate it from other signals such as interference and also the DC offset. We will collect data at different distance. In this study, the distance is from 1 feet to 10 feet. So this is the results we collected at 32 megahertz. We use 32 because we found that singular at 32 is stronger than the baseband 16 megahertz. We will see that at different status, once the device is on or device is off, we can always receive some IF emulation signals, and we can also observe the DC spark. This is caused by hardware. There are different ways to detect them. A simple way is to use any detector. This is very efficient and effective if the distance is not large. To detect them, we use fast Fourier transform to process the data, and we use 1,000 point. We will compare this with the average of the three strongest signal. This technique is tested on data set collected with the different threshold value and also distance. So we figure out that any detector is very efficient if it's 1 foot away. But if we further increase the distance, for example, if we increase to 4 feet, the accuracy actually is very small. So that means we need to use a more powerful detection algorithm. This more powerful detection algorithm is deep learning. Deep learning has different algorithms and different input data format. We tried them and found the CNN is maybe it's the best among all the options, and the input data format is 2D spectrum graph of the data. For the 2D data, we use 1,000 point image, and we put 10 as a group, so we will have a 2D graph. For the data, we will split them 1820 for training and testing purpose. Here is the results. We can find that actually deep learning can work very well for a distance up to 9 feet. But of course, if you further increase the distance, performance will drop. The next topic is about communication. So another use case of IF emulation is we can use it for communication purpose. This can be observed by checking different harmonic frequency. In this study, we look at the 18th because this has the good signal we observed. And we also tried different codes and find 4 unique block of codes that cause different center frequencies. That means we can use them for that transmission purpose. To have a communication scheme, we need to design an encoding method and also decoding method. For encoding, because we have 4 block of codes, so one straightforward is we can encode data at 2 bits, and there are 4 samples corresponding to the 4 block of codes. But we find that actually this performance is not good. Another choice is just 1 bit, there are 2 samples. And these 2 samples corresponding to 2 blocks that have a largest difference between them. We find actually using this scheme, it will give you higher accuracy than the first scheme. And the second scheme we also encoded, and on the 18th harmonic, we can see the sample spectrum graph and also observe the DC spark in this figure. For the decoding method, actually, we need to first remove the interference. So the first step is isolate the DC offset. We will move the central frequency of the signal into the center. And once we move it in the center, we can observe there is a DC spark caused by hardware. So this will be also filtered. And once we filter the other signals, we only have the encoded signal. This signal is somehow similar to the 2FSK modulation schemes, so this can also be decoded similarly. This is the decoding details shown in the figure. For the decoding, actually, one thing we want to note is the threshold actually change over time. So we need to use the algorithm to determine this threshold dynamically over time, and using this threshold to determine whether this is high singular or low singular, corresponding to 0 and 1. For the communication setup, we use 6-character ASCII code, and we transmit at 100 milliseconds per symbol. So it will test at a different distance to study the effective of the scheme at a different distance and the accuracy performance. We find that actually the performance is very good for 1 inch up to 9 inches. There is no error in decoding, but after that, we actually cannot tell the difference between the coded data and the noise at 12 inches. So this only works for short range. And to have it work for long range, again, we use a deep learning-based decoding scheme. We again train a CNN network to decode the IF emulation singular, and we again split that by 18 and 20%. We find that if we use deep learning, it can successfully decode IF emulation singular for a distance up to 4 feet away. But of course, if you compare with the simple scheme, this is much better because the simple scheme can only decode the singular within 9 inches. So as a conclusion, we started an interesting phenomenon of IF emulation. IF emulation is the singular liquid when the device is running some code. And we find that we can use energy detector, and also we can use a deep learning-based detector to detect such IF emulation. Further, we found that we can use the IF emulation to transmit data, and they have some advantages than transmit data directly. And we found that the encoding decoding scheme can also based on simple scheme or based on deep learning scheme. And again, deep learning scheme is more powerful, can support the transmission over a longer range. So is there any question? So if no question, we can, now it's time for lunch, and we will continue. Ah. Yeah. Okay.
Thank you very much for the presentation. As I just see from the paper, quickly see from paper, it is a really promising approach, but maybe I said something. In this communication, we try to benefit from the unintentional RF emissions. But as I see, it is a promising technique. To take place instead of the direct communication. So I say direct communication, classical wireless communication, and when you consider in classical wireless communication, it has quite many techniques, you know, modulations, so constellations, the others. So it is an established one, and how this can take the place of that. So I hesitate about, okay, it seems you know, very promising, but when you consider the communication, you know, quite many techniques, quite many signals. So how can you detect that? So maybe I miss some point.
So this is just I think is a promising scheme, but still with a limitation. You can say that even with the deep learning, the communication range is still very limited. So it is a communication scheme for short range communication. Probably it can only be used for maybe indoor environment.
You will it for what, mainly you say?
Maybe for indoor environment. Lot of outdoor for long range, just short, very short range, probably within one room. So in this case, I would not say it will replace any existing communication scheme. Probably it will be something similar to Bluetooth. Yeah, just
for, especially when you consider energy harvesting sensors. In that, I say, for example, communication, but when you consider the classical sensor network or outdoor network, generally, yeah, they don't have quite many transmission rates, and they have generally on-off scheduling. So when you consider that simple schemes, especially, it seems very promising that once. And also another interesting thing is you say if there is no RF emanation, no RF internet transmission, then we can understand, we can infer that sensor, that node doesn't work and doesn't have energy to make transmission, or as I see from paper, right?
Yes.
It is interesting because there is a really there is a topic, there is a research line on this, such a problem about guessing the energy in the battery and making scheduling decisions. But with this technique, you can infer the battery levels or battery levels which includes the enough energy to make the transmission. So it is really interesting work. And thank you very much for the presentation.
Thank you.
Just one quick question. I know that this is a very preliminary work into this sort of area. I'm curious. One of the advantages of dedicated wireless devices is that we can do some complex sorts of multiplexing, right? We can have devices on neighboring channels without causing interference. If we're relying on RF emanation, we would expect most devices of a certain type to be in roughly exactly the same frequency band. Is there some accommodation that you think could be used to allow multiple devices to transmit in the same band?
Yeah, this is a very good question. If we consider RF emanation, actually, the band depends on the hardware itself. So probably, if they are the same type of product, probably they will work on the same band. So this can be one issue if you want to implement in reality. But this can be somehow relieved by the short-range communication property, because it's short-range, so probably there's no much device in. Yeah.
Thank you.
Okay. Okay, so let's continue the workshop at 1 p.m. And also the authors can upload their slides. I will show the link for the presentation.
systems. We do a lot of research in this area and want to share with you today some of the work that I did with my colleagues, Josh Robinson, Joseph Carmack, and Dave Kudo in the areas of RF fingerprinting. In particular, we've been working on this problem for a while, and this talk today is focused on looking at some of the real-world operational aspects of that and how we can start pushing our research closer to addressing some of those challenges. So overview of what I'm going to be talking about today. As you guys have all been seeing, there's been lots of great progress in the RF machine learning field, and that includes RF fingerprinting, as we've heard in a few of the papers and in John's talk this morning. But a lot of the work to date has been a bit limited in scope. It's been that initial proof of concept that you need to get through from the beginning, and the applications have been relatively narrow, so only a few factors vary in the test cases, looking at how they're addressed, things like SNR and so forth. So in this paper, we wanted to take a step back and look at it more from a systems perspective. How do we expand the solutions that we're designing to be more robust to real-world signal environments, as well as how do you integrate in with other functionalities in a receiver. And the work that we're doing, we're building on our RiffNet classifier. So our RiffNet classifier, what is this? This is something that we initially developed under the RF Machine Learning Systems program, the RiffMOS program that John spoke about this morning. It's a deep learning approach that we specifically tuned for RF signals. So we did a bit of a study on the characteristics of RF signals. Where do we want to be invariant to it? Where do we want to have equivariance pull out and so forth? And we came up with this solution that is based on these dilated causal convolutions, these DCCs that are performing most of our feature extraction in the orange part here. These have some nice properties in that they're causal. As you think of RF fingerprints, those are imparted on the signal from the hardware. So there's memory states to those. So having that causal nature to pull out the memory of transistors, capacitors, and so forth is important. And then it's dilated. RF signals have very large bandwidths, and the data rates are very large. This is a bit different than audio signals and images. So we wanted to have this dilated property so that we could sample from larger scales of the signal and still pull out features that were meaningful and get those really large receptive fields that you need for RF signals. We've done a number of other works, and we've got some papers that detail a lot on this architecture. But this is kind of what we settled on for that program. And I'm happy to answer questions after as well, getting into more detail on the architecture. But on that, the RiffMOS data set, which again is the Wi-Fi and ADS-B signals, we were able to achieve greater than 95% accuracy out to classifying 10,000 devices, which is pretty amazing. For this work, we're using that data set. It's complex valued IQ data. We're processing IQ into the network, and we're sampling at 100 megs. We're also doing a little bit of augmentation for this work. We're simulating some direction of arrival and some geolocation information on the data so we can look at it from a full receiver standpoint. And then we're also looking at challenging signal environments where there's going to be a lot of signal overlap, signal-on-signal conditions. So in particular, the focus areas that I'm going to talk about today is data availability during training. So in the RF domain, it's highly unlikely that you're going to have a fully representative data set for all the operational conditions that you expect to see. So you need to be robust to that. And just in general, operation robustness, there's a lot of uncertainty with the operational unknowns. So how can you make a solution that is a little bit more robust to this uncertainty? There's a lot of scene and environmental factors. So things that affect signal propagation, and they can potentially affect these subtle fingerprint characteristics. And then as you think of it from a systems perspective, how can you get integrative gains into the system? as well as how can you tap into the other resources that are being processed on the system to improve performance. And then, of course, our RF devices are inherently edge devices, so we want to be able to move this processing closer to the edge. So some thoughts on how you get the computational load down to do that. So first up is data availability during training. So some of the things that we've looked at here, and I detail a couple other papers from our references as well. First is transfer learning. So let's assume that you don't have any data available ahead of time. What can you do? Well, you can train up the feature extraction part of your network, and you can actually do that in a completely unsupervised way on synthetic data or other data sources that are available. And then during operation, if you've got some time in the beginning to collect an initial smaller data set, you can fix those feature generation part of the network, and you can learn classifier layers on top of that. And we've been able to show that you can get some good performance with that. We trained on completely synthetic data, just doing a reconstruction, so unsupervised reconstruction, and we had no emulated RF fingerprints or anything in that. So just learning good features for the RF domain. And then we did some selective retuning with a real-world operational data set, and we were able to get within 3% of the accuracy as if we trained on the full operational data set. So showing that there is promise in pre-training these networks on available data sources and performing that transfer learning. As well as another thing that you face during operation is, in the RF fingerprinting sense, is novel devices. So you may not know all the devices that you're going to encounter as new devices are coming online. People are constantly getting new cell phones and so forth. So you need to be able to handle and detect that there are new devices present, as well as that device continues to appear, you want to be able to cluster that together and say, not only is this a new device, but this signal is the same one as I saw a minute ago from this same device. And we've been able to do some work showing that this architecture has the capacity in the, get the mouse over there, nope. Up in the, if you go near the classification layers, you have a latent embedding space. You can treat that as a clustering layer, and you can enforce some additional loss functions on there so that the devices that you know about are clustering tightly together. And if things are falling outside those regions, you can declare them new. And you can also start to cluster new devices. So as you start to build online clusters as new clusters appear in that space. All right, shifting over to operational robustness. I talked a little bit about pre-training in the transfer learning sense. There's also just the greater pre-training sense of learning all the weights of your classifier ahead of time on available data sets, and then peeling off the classification layer and putting on a new layer as you have new devices that you're looking at or changes in the sample size that you're looking at. The computer vision image processing field, as well as natural language processing, is largely built on pre-trained networks now. It's really easy to go and download a network, VGG16, ResNet, pre-trained weights, and then just learn that classification layer. We wanted to look at how that translates to RF fingerprinting as well. So we did some studies with that, and we've shown that you can move from training on smaller population sizes, moving to larger population sizes, as well as going the other way and understanding some of the performance trends as you go there. Also, we found that exposing during training to more signal types actually helps performance. So if we only care about classifying Wi-Fi signals during operation, we actually found that if you train with additional signals such as ADS-B, which you wouldn't expect the feature types to be as similar as those, the structure is fairly different, it actually helps performance for that Wi-Fi operational set in that you are getting a lot more data into your training than you initially had, and those lower layers of the network that are just general RF feature extraction layers, you're getting a lot of benefit in those layers, while the later layers in the network that are more application specific you're still able to get that from the Wi-Fi. And then also some things that we looked at is how can you be robust to these unknowns during your training. So you're expecting to see a lot of signals that you don't know ahead of time. So during training, you can synthetically or grab from other data sets additional signals that you don't know about and put them in your training. That has a nice effect that those clusters I talked about in the latent layers, it keeps the clusters for your known devices fairly tight as you're putting in these extra ones, as they're taking up capacity. So it's forcing those to be tighter and you get better definitions. And it keeps the probability of false classification with these unknown signals down pretty small. We've been able to show that we can embed a signal that we are looking for in a population of 1,000 previously unseen devices of the same type, and the probability of false classification can remain under 1% with this technique. And then I also mentioned that signal-on-signal conditions are something that you face. We've done some work in the past looking at interference from other signal types, and there's plenty of other work that looks at that as well, especially when you have different SNR mismatches or different signal type mismatches. We've done some work where we've shown that we can suppress 30 dB of interference, so a large power interferer is within your signal. You can suppress that through this deep learning approach, and in a reconstruction fashion, you can recreate the intended signal without that interfere. But a harder case is when you're actually SNR matched. So you've got two signals, the same type, and they're about the same SNR. So you don't have this successive cancellation that you can do, and the parametrics are the same. And we actually took a data-driven approach to this, looking at some data-centric approaches where if you're expecting to see conditions like this in training, you can actually upsample that, during operation, you can actually upsample that during your training. So you can artificially create more and more cases of that. And what we see is that helps the classifier still perform well and have a graceful degradation as you have more and more signal interference. So the plot here showing the accuracy over the percent of the signal that's overlapped. In the blue, this is if we don't upsample and create more cases like this. You see as you see interference, your performance drops off fairly rapidly with any form of interference on the left there, and drops off quite a bit. But if you're able to expose this during training a lot more, then the network actually has to learn features to tease that apart, and it's more tuned to handle that when it sees it during operation. You got more of the plateau slowly degrading over time before dropping off with the full overlap. All right, shifting to ways that you can gain back some performance in an integrative sense. There's ways that you can combine multiple signals. We call this multi-burst processing. So if you can assume that, say, 5 signals coming from in short succession from this direction are from the same device. If I make that assumption, I just don't know what the device is. How can you use that information to increase performance? You could put all of those into the network and have the network try to learn the correlation between those. But we actually found that an easier way and a way that improved performance better was to pass each of those signals in independently into the network and then do post-classification fusion. We found that the correlated correct class probabilities would pop out a lot more in that case, as they were typically in the top 5 candidates, while you would get spurious other ones popping into that top 5. So all those non-correct classes will get suppressed in this case. And just moving to processing a burst of 2, you'd get a 20% increase in performance. So that was a nice finding there. And that's shown in the top figures here. And then you can also fuse across classifiers. So getting independent looks at the signal through multiple classifiers provides you an increase in performance as well. So this could be distributed across multiple receivers or within the same receiver, just running multiple classifiers on the signal to get that independence. A similar type of fusion in this sense, but instead of across multiple signals, across the same signal and multiple classifiers, and you get an increase in performance, but you're also taking a computational hit. So that one is not as tuned to being edge deployable. And then looking at how you can pull in additional information. So one of the things I mentioned on the previous slide is this multi-burst assumption, assuming that information comes in from the 5 signals that you have come in from the same device. Well, let's remove that assumption and let's actually prove it out. So what if you have information you can integrate with other functionality within the receiver, and you've got something like a directional arrival on the top, or a some type of geolocation with some accuracy, as shown on the bottom. What that allows you to do is that allows you to mask out and start tracking where devices are, so you can start to rule out a bunch of other devices. And so the set of things that you're trying to classify over as you have this additional information starts shrinking way down, and you're able to reduce your error and improve performance quite a bit. And we show that on the bottom with a 1,000 device case here as the geolocation error. So as a function of the error of the geolocation function gets smaller and smaller, you're getting the correct thing more and more. The green dot was the multi-burst processing that I talked about on the last slide. So getting that 95% accuracy is at the green dot. You can actually achieve that without multi-burst processing if you've got a geolocation error of about 5% of this area. All right, and then last up is computational considerations. So all this work that we've done in this paper and on the RIFMOS program was on a GPU server. We're using NVIDIA V100 GPUs. Only need a single GPU to train in each of these test cases, except for the 10,000 emitter test case. But the number of flops that you need is fairly large, and you can see that that is primarily driven by that dense last layer to get to the classification, where you see the gigaflops for getting to 10,000 devices is out in the 50 gigaflops. So that's relatively large, while the core feature extraction is on the order of about 2 gigaflops. And the processing latency for all of these cases is about 2.5 milliseconds. So ways that you can reduce the architecture to reduce that computational constraint and increase decrease the latency. John mentioned some of these earlier, but decreasing the weight precision, doing the architecture and network search to decrease the network depth or remove some of the layers, decreasing the number of filters, some pruning techniques, and then just looking at naively, if we look at a smaller model by instead of taking in the large signal, if you take in smaller bits of it, trying to understand where in the signal you get most performance. So this is taking an 8 microsecond slice, only classifying over smaller bits. So a lot smaller model. This is on the order of the subsequence feature stack. So you're only at about 0.1 gigaflops. You see a lot of the classification accuracy comes near the beginning parts of the signal where they're highly stable. And with that, I'll just go ahead and conclude that we're excited to present this work and be here today, and at large, excited for the community. There's been a lot of great progress. And as we're starting to get beyond the proof of concepts and move out to thinking of some of these operational constraints and how we can be more robust to complex environments, we're glad to be contributing to that. And I will note at the bottom, though, that all the things I talked about today are not in a single system. We're looking at a single architecture for all of them, but they're kind of independent studies. So a next step would be to integrate all this together into a single system that can handle all this. All right, and I'll conclude there. Thank you. I'll take questions now. All right, thank you.
I have a question.
Yes.
Okay, so you mentioned for the this real case, So do you think what's the challenge to use the machine learning or deep learning for your current operation scenario?
Yeah, so one of the biggest challenges, and not unique to the RF domain, but in general, when you're using deep learning, your requirements are kind of baked into the network from the data that you're using. So whatever the training data that you're using, your operation is going to be good when you're within the distribution, whenever that's similar to it. But once you start varying outside of that distribution, that's where you can start to get some unexpected performance. So trying to understand the conditions under I should trust my data because this data is similar to something from my training set is important, as well as trying to get that graceful degradation so that as you start getting further away from your training set, you kind of have an understanded degradation in your performance.
Thank you.
In the area of transfer learning, one of the general ideas is that by finding some architecture that has sufficiently complex and informative features in an earlier layer, then we can accomplish a number of various tasks, which it seems like that's what, in general, your approach with this RiffNet architecture has been, right? That we found this upper layer that we can apply to a lot of different tasks. Do you feel like there are any major extensions that need to happen to these initial layers to transfer to new types of tasks, or have you found it? Have you found the solution?
So definitely not found it. Yeah, great question. There's definitely a lot of work to be done. So yeah, if people aren't familiar, the concept of transfer learning in general, as you go deeper into the network, the features you learn at the beginning of the network are kind of just more generic. In computer vision, those are, you've got gradients as you go across the line and things like that. And as you go further in the network, you're pulling out features at more and more abstract layers. So really we've done some initial studies, but really not in the depth that's needed. And hopefully the field at large starts diving into understanding what are those core features at the bottom. Is there a set of core features for all of RF? My initial thought is probably not. It might be a little more specific. And then really how far into the network do those features translate as you're going across signal type and application. So I do think there needs to be a lot more research in that area.
Thank you.
All right, thank you.
Okay, let's focus on our second paper. The title is Automatic Machine Learning for Multi-Receiver CN Technology Clusters. And, okay, the first author will present that.
Did you upload this slides?
Second one?
Yep.
Oh, then.
Thank you. Hi everyone. This is Amir Yazani. I'm from University of Arizona. This work is with my PhD advisor, Marvin Kroons. Title of paper is Automatic Machine Learning for Multi-Receiver CNN Technology Classifiers. I will divide the presentation to 4 parts. First, talk about the multi-receiver signal classification problem. Then talk about our automatic machine learning approach to finding near optimal classifier design and pre-processing design parameters. Then talk about our evaluation results and conclude the presentation at the end. Convolutional neural networks have been used for various spectrum sensing tasks, modulation classification, transmitter identification, technology classification. They all use IQ samples, windows of IQ samples, and then feed them through these convolutional neural networks to give classification results. Processing IQ samples is good because you're bypassing special signal processing stages. For modulation, you could think of, you don't need to do any decoding or demodulation. And for transmitter identification, our fingerprinting, you don't need to do carrier frequency offset estimation, for example. So in this work, we focus on technology classification at the 5 gigahertz band, where you have Wi-Fi, 5G, NRU, and LTE-LAA coexist. These technologies, if they want to coexist harmoniously, it's better for them to adapt their parameters, protocol parameters, based on each other's transmission activities. So they have to sense each other's transmissions and adapt their protocol parameters accordingly. But this requires different technologies to adopt technology-specific receiver design. To mitigate that, we using machine learning modules, specifically CNNs, is good in mitigating that concern. Prior works only considered a single stream of IQ samples, processing them and windowizing them. But in this work, we consider a receiver classifier that is equipped with multiple RF chains with separate antennas. So we are doing classification over multiple IQ streams received from different synchronized receivers. And as we've heard today from multiple talks, doing architecture search and doing optimization for the structure of the classifier and the pre-processing stages can improve classification accuracy by great margins. I will show the results at the end. But going forward, this slide is supposed to show the pipeline of our multi-receiver signal classification problem. The classifier is equipped with capital N receivers. The pre-processing stage decides how many of these receivers it wants to process for further classification. I mean, we will show that processing more IQ streams does not necessarily improve accuracy, and this parameter should be defined as a hyperparameter. And it should be optimized along with the architecture of the neural network. As other pre-processing parameters, we have the size of the window size of the IQ samples used for a single classification instance, and whether to normalize this window of IQ samples. So the output of the pre-processing stage is a sequence of inputs of size W times 2 times n, lowercase n. This 2 comes from I and Q. And the output is a softmax layer giving us a probability distribution, and the finalized output is the maximum class, the class with the maximum probability. This slide illustrates how this windowing approach works. So data sample 1, you could see, you could think of these multiple RF chains used for classification as different colors of a picture. If we think about the image classification problem where we have red, green, blue channels. So IQ streams from different receivers act as different channels of the input. So we have this multiple input channel going through the convolutional neural network model. And each of these data samples are then fit to the CNN model for classification. The goal is to find optimal architectures with optimal pre-processing and learning hyperparameter settings. We talked about the number of selected streams from the total number of available receivers. Size of window is a hyperparameter, and the decision to normalize or not normalize these windows of IQ samples is a hyperparameter too. We have learning hyperparameters, choice of optimizer, learning rate, batch size. These are all defined as hyperparameters. And as for our architecture, we define the architecture as a set of hyperparameters and then try to build this space of hyperparameters and find the best configuration from this space that basically minimizes cross-validation loss. The problem we define as a hyperparameter optimization problem, hyperopt problem, and we solve it with hyperband. I will talk about hyperband in the next slide. But just looking at the optimization problem at the bottom of the slide, capital L is the loss. It's the cross-validation loss. And we want to minimize the expected cross-validation loss over randomly selected training and validation sets. So it's a bi-level optimization problem where at the training phase, we want to minimize loss over the training set, but we also want to minimize cross-validation error using good hyperparameter configurations. Mu star here is supposed to show the best hyperparameter that gains the least cross-validation error. Okay. The hyper-CNN architecture, gaining insight from image classification architectures and signal classification CNN architectures, they all start with a set of convolutional layer and max pooling layers to extract features, and then a set of fully connected layers are used to conduct classification based on these extracted features. So we go on and model the architecture of this hyper-CNN by introducing a feature extractor block that includes a number of convolutional blocks. Each convolutional block, as you can see, consists of one convolutional layer, one dropout layer, followed by a max pooling layer. And the parameters within each convolutional block, such as number of filters in the convolutional layer and the size of each filter, activation function, stride size, all these parameters are defined as hyperparameters. Similarly for the classifier, which includes fully connected layers, the number of fully connected layers are hyperparameters. Neurons within each layer are hyperparameters. Activation function, dropout rate, all hyperparameters. These along with the pre-processing hyperparameters and learning hyperparameters build our total space of hyperparameters. So I said we would try to solve the hyperopt problem using hyperband. Hyperband is a multi-fidelity optimization technique. Before going through that, there are simpler approaches to finding hyperparameters, best hyperparameters. You could think of exhaustive search or grid search, which is exponential in the number of hyperparameters. A better algorithm that works is random search. It works a lot better when you have inhomogeneity in the importance of hyperparameters. Some hyperparameters might be affecting the performance, the validation error, the decision that we make through the selection of those hyperparameters affects the validation error more than the others. But these algorithms are black box techniques, and they don't work well when we have large data sets or complex models, complex deep learning models. So multi-fidelity optimization techniques train and evaluate on subset of features or subset of data sets or subset of total number of available training epochs. And they tend to give out the finalized output based on evaluation on these lower fidelity training and tested configurations. Hyperband improves on successive halving. It's in the figure you could see successive halving considers 8 hyperparameter configurations. It starts by associating a fixed budget to all these configurations, but then the budget is finished. You could think of budget as the number of available training epochs, or again, subset of features, or I forgot about the last one, but basically the worst performing half of the hyperparameters are dropped when the resource is finished for all hyperparameters, and the resource for the remaining best performing half is doubled. And successive halving just continues until only one hyperparameter is left. The problem with successive halving is that we don't know, we have to manually select the set budget for each configuration at the beginning. So we are prone to the risk of associating too much of a budget to a bad performing hyperparameter, or assigning too less of a budget to a potentially good hyperparameter. Hyperband considers a combination of number of configurations and their associated budgets, and runs instance of successive halving for each of these configurations. So you could think of a parallel optimization technique going on, and the finalized output is the finalized best performing hyperparameter over all those configurations. Going to our evaluations, we generated 2 data sets, one with simulations, the other over the air experiments. We generated Wi-Fi LTE 5G waveforms, 64 QAM waveforms, and then passed them through an 802.11ax indoor channel model, center frequency of 5 gigahertz, and a sampling of 20 megahertz for the receivers. The transmitter-receiver distance is 3.8 meters, and the distance between the receivers is 50 centimeters. For each technology, we have 100,000 number of data samples, and we simulate this for a classifier that has up to 6 number of receivers. Our over-the-air experiments have used NI 2921 USRPs, but to synchronize our receivers, we used octoclock, and its maximum frequency was 10 megasamples per second. We generated data sets for transmission gains for 0, 5, 10, 15, 20 dB, and I think, okay, this slide shows that we run hyperband for our hyperopt problem for all of these data sets. The figure on the right shows an example of the optimal CNN architecture gathered for when we tune the model for simulated data set of SNR 0 dB. This model tends to give the best generalization accuracy over unobserved SNR values. I will talk about that more in a later slide. But the table on the left shows that these almost all of these architecture tend to select multiple streams of IQ samples to process for signal classification, not a single one, not using a single stream. This baseline CNN classifier is manually tuned. It is a single layer, single convolutional layer architecture with a single fully connected layer at the end. We compare this model when we set as input multiple streams of IQ samples. We vary the streams of IQ samples. In the next slide, it shows it better. The classification, this shows the testing classification accuracy. When we select 60, 20, 20% respectively for training, validation, and testing. You could see on the left that actually increasing the number of IQ streams decreases the accuracy. This, however, the OCNN architectures always perform better than the manually tuned architecture. And the selected number of streams should also be selected as a hyperparameter, because just increasing the number of streams does not improve accuracy. On average, accuracy is improved by up to 46% for simulations and 25.58% for over-the-air experiments. One quick note about our OTA experiments is that the receiving bandwidth at the receivers is half the transmitted bandwidth. So the classifier it's not having as much of a high bandwidth in simulations as for OTA experiments, and it's due to our hardware limitation of our octa clock, which is limited to 10 megahertz. So I talked about generalization or unobserved data sets. It's expensive to gather data sets for every SNR values. We might want our model to generalize well to unseen, unobserved, or scenarios where it didn't get any training data from. So this shows how actually normalizing the IQ samples can improve generalization accuracy for those data sets that the model was not trained on. Adjacent SNR means the two consecutive SNR values on the left and right. So if you consider the -5 dB SNR value, we trained a model for the -5 dB, but tested over -10 and 0 dB. On average, with normalization, generalization is improved by a factor of 2, and it is expected to have higher generalization accuracy for closer SNR values than for the ones that are deviated much more. And that factor is 20% improved performance for the adjacent SNR values. Concluding the paper, most devices are equipped with multiple receiver transmitters, so it would be plausible to think that classification can use multiple streams of IQ samples for doing a machine learning task. It's also good to include the pre-processing parameters used for data parsing as a hyperparameter along with the architecture of the neural network. And that can improve accuracy by 46% for our simulations and 21% for our OT experiments. Normalization can also improve generalization for unobserved data sets. Thank you so much for listening to my presentation.
Okay, let me first ask a question. So I'm very interested for your generation part. And you train for one SNR. What's the motivation or what's the advantage for your model can guarantee, okay, the test accuracy is also good on the different SNR, especially in the lower SNR? I think this is interesting. Also, this is challenge.
So if I hopefully I understood your question correctly. You mean how our model...
What's the advantage your model can guarantee this generation if you train from the -5 dB and test the smaller, like -10 dB? How to guarantee that generation?
So this figure actually shows, I mean, if we do not do any normalization, the model performs really bad. It's basically a random guess. here I'm showing that when we, this figure here, I guess you can't see my cursor, but if you consider the bar plots for -5 dB, we are training the model for -5 and testing it for -10 and for 0 dB. So it shows that the model performs, it's around 70% for -5 dB. But if you go to higher SNR values, generalization accuracy improves. So the guarantees I would say is that the model tends to give better predictions when it's trained on higher data sets and tested on SNR values that are close to that training data set SNR.
Yeah, because normalization traditionally to skew that data set. If we consider lower SNR, that means there more noise into that data set. So I think this is a challenge.
Yes.
Maybe your model that is a good fit for this.
Yeah, they tend to, the noise, you're definitely right.
Yeah, thank you.
Yeah, thank you.
Can you talk a little bit about what is the relationship between these multiple signals, right? Do you measure KL divergence on mutual information for us to understand if the mutual information across these multiple signals is of threshold, is better? Do you have some insights on that? Or is your data just random?
If you mean, have we done any like analysis like towards the?
You don't know how this mutual information impacts your what you learn.
So I would say that I mean, it's beneficial for a receiver that just wants to deploy a machine learning module to do a basic classification of saying the transmission is LTE, 5G, or Wi-Fi, instead of going through like complicated signal processing stages. So, oh, I mean, we tried to show that using automatic machine learning instead of manually tuned architectures is a better way to design these models instead of just manually tuning these. And one other thing that we showed is that the pre-processing values should be defined as hyperparameters. This is important because the same concept can be applied for other machine learning tasks for signal classification, transmitter identification, or modulation classification. This was maybe a proof of concept for and a use case we studied for Wi-Fi, LTE, and 5G, but mostly we wanted to see the effect of multiple receivers and automatic machine learning used for setting jointly the architecture and pre-processing stages. Thank you.
Okay, let's discuss our third paper. Paper title is the K-new K generation using neural networks from the wireless channel. The first author, Xuewei, will present this work.
I didn't upload the.
That's okay. You want to use USB-C?
Yeah. HTML.
Okay, so this does not look like it has a display out, so I'll take this entire thing out.
Okay. Hello, everyone. My name is Xue Wei. I'm a PhD student from the University at Albany. Today, I will introduce a method for K generation named KNew. K generation using neural networks from wireless channel. In this talk, first I will introduce the motivation of our work. What is K generation and why is K generation important? Next, I will show the system model, how our model is designed and the details of our method. Then I will show the simulation setup and the experiment setup. After that, I will analyze the results we got, and last, draw conclusions and provide an overlook of the future works. First, what is K generation? In cryptography, a K is a string of characters that's used for outing data so that it appears random. So the K generation is a process of generating keys. K generation helps avoid key sharing and the management overhead. The keys can be generated from common channel filters between the legal pairs. Here we also think the channel decorrelates beyond half a wavelength. Also, if a key can be guessed, the cipher can also be broken. Next, the steps for K generation. To generate a key, first we have to probe the channel and extract the common channel filters from both the transmitter side and receiver side. To reduce the key mismatch, we also have to perform privacy reconciliation. As for the adversarial, we also have to reduce the partial information about the legal key that the adversarial can obtain. The existing attacks for K generation may be trying to disrupt the channel probing process, reduce the K generation rate, and even infer the generated key. Besides this, there are some challenges for K generation. First, the channel measurement performed at Alice and above may be beyond the coherence time of the channel. So the true channel is reciprocal within the coherence time, but the channel measurement is not. Next, the hardware impairments at both the transmitter side and the receiver side may make the K generation rate to be even lower. Besides this, a simple quantization and thresholding may result in a higher probability of different cases. In addition, a simple mapping of quantized channel estimate to a K may lead to a greater risk of being guessed by the adversarial. Next is some related work. We divide the K generation method into three categories: the K generation in OFDM system, the decomposition method, and the neural network models. Here are some methods and their disadvantages. To overcome the challenges of K generation, we propose our model, KNew model. Our model used two autoencoders to decompose the channel measurements to a compressed latent space L, and this latent space captures the common features between the measurements of Alice and above, and then L will be quantized to generate the K. The strength of KNew model is achieved in the following two ways. First, we utilize the channel decorrelation beyond half a wavelength. Next, the L can be guessed only if all the parameters of the model can be obtained by the adversarial. Next, about our system model. The main idea is to use two autoencoders to construct the channel filter and at the same time to extract the channel filter and at the same time reconstruct the channel estimates of the other side. So let's take a look at the system figure. We have the transmitter and receiver Alice and Bob. And the H sub BA prime and H sub AB prime are the channel estimation at Alice and Bob. At each side, we have an autoencoder. So the autoencoder will first map the channel estimation to a compressed latent space L, and then the L will be remapped to the channel estimation of the other side. So for example, at Alice side, the autoencoder A will first map the channel estimation of Alice to the latent vector LA, and then LA will be remapped to the channel estimation of Bob's side. We also have to minimize the error between the two latent vectors LA and LB because they represent the same channel. Then we can extract the bits from the latent space. This is how we generate the K. About the adversarial model, we assume the adversarial is passive and can listen to the other communications between Alice and Bob. She can also measure both the channels between herself and Alice and Bob. The adversarial may experience the same multipath effect of the channel, but it's half a wavelength away from the Alice and Bob. So it means the adversarial's channel is uncorrelated from Alice or Bob. And about the KNU model, it might also be known by the adversarial, but the model parameters are not known. Because the model is trained based on different devices. And if you want to guess the parameters, she has to guess about 60,000 parameters. The 60,000 multiplied 64 bits, it's a large number. Next, the channel estimation model. First, for the true channel response, within coherence time, the true channel is reciprocal, but beyond the coherence time, it's not. So I have the relation equation of the true channel response. Next is how we model the channel estimation at Alice side and Bob side. H sub BA prime and H sub AB prime are the channel estimation at Alice and Bob. H sub BA and H sub AB represent the true channel response. The epsilon is the estimation error, and the n is the communication noise. The last two items represent the hardware impairments of the transmitter and receiver. Based on the time interval of the measurement times, we have two situations to derive the channel estimation of the other side. If the time interval between TA and TP is less than the coherence time, it means the true channel response, the channel is reciprocal, so the H sub AB and H sub BA is the same. So it's easy to derive the channel estimation at Alice and Bob. The result is shown here. And if the time interval between TA and TP is greater than the coherence time, the channel is not reciprocal. So according to Chick's model, the channel can be represented as a sum of sinusoids. So we have the equation here. The alpha represents the correlation coefficient between H sub AB and H sub AB, H sub AB and H sub BA. And n sub 0 can be modeled as a Gaussian distribution with a mean of 0 and a variance of sigma, which represents the uncorrelated part of H sub AB and H sub BA. Then we can derive the channel estimation at Alice side and Bob side. The results are shown here. Next is our autoencoder structure. We have two autoencoders at Alice side and Bob side respectively. For each autoencoder, it has its own encoder and decoder. The encoder maps its channel estimate to a latent vector L, and the decoder will reconstruct the channel estimate of the other side from the latent vector L. After training, we just need the encoder to get the latent vector and then extract the K. We don't need the decoder after training. Next is our loss function. Our loss function has three parts: loss A, loss B, and loss L. The first two, loss A and loss B, represent the reconstruction loss. For example, at Alice's side, the loss A is the loss function to reconstruct the channel estimation of Bob. So we calculate the mean square error between h sub AB prime, which is the channel estimation of Bob, and h sub AB double prime, which is the reconstructed channel estimate of Bob. Similarly, at the Bob side, loss B is the loss function to reconstruct the channel estimation at Alice, so we minimize the error between h sub BA prime, which is the channel estimation of Alice, and h sub BA double prime, which is the reconstructed channel estimate of Alice. The third one is the loss function of the latent vectors. We minimize the difference between LA and LB. And we also introduce gamma. It's the regularization item here to balance the different losses. So the total loss function is shown here. After we get the latent vector, we can extract the K. First, we normalize the latent vector L and then extract beta, the most significant bits from each element of L. So if the length of the latent vector L is n/4, where the n is the FFT size of the OFDM symbol, we will and we extract the beta bits from each element of L, so we will get the total number of the K will be beta times n/4. Next is the simulation setup. The channel frequency response is estimated by the long preamble in Wi-Fi packets, and we choose the FFT size n is 64 with unused subcarriers K is 12. We simulate a 4-pass relay channel with any Dopplers. The other parameters are shown here. We simulated the channel in MATLAB and trained our model in PyTorch. For the simulation data generation, we use 1,000 differences in the relay channel function to include the variations of the same kind of channel. We trained the entire system at a low SCR level and test the model performance when SCR is 5 dB, 10 dB, 15 dB, and 20 dB. In the testing phase, we choose 200 seeds that are different from the training data sets to ensure the model is not data sensitive. We trained the two autoencoders simultaneously in each epoch. Next is the experiment setup. We fix the Alice position and transfer different Bob's position. The distance between Alice and each Bob position is about 3 meters. We transmitted Wi-Fi packets from Alice, received, and Bob for 2 seconds. So it means the time interval between the TA and the TB is about 2 seconds. Next is the results we got. First, let's see how each step works. The left picture is the channel estimation at Alice side and Bob side. The right one is the corresponding latent vector at Alice and Bob side. So we can see that if even the channel estimation at Alice and Bob are very different, we can still get a very similar latent vector with just a slight difference here. So this is one of the benefits of our model. So first we have the channel estimation, then we get the latent vector. The third step, we can extract the bits from the latent vector. If we extract the 2 bits from each element of L, we will get 2 times 16, which is 32 bits, without any mismatch. Next is the squared error between two Latin vectors. We can see it's a small value here, meaning that the two Latin vectors are very close. Next is the performance of KNU model with simulated signals. The left one is the KGR per II, which is a K generation rate per element of latent vector. We show KGR per II at when the channel SR is 5 dB, 10 dB, 15 dB, and 20 dB. And the average number of KGR is about 4 bits. So it means that at least we can get 4 times 16, which is 64 bits K. And the KGR per II increases with the SR. The right one is the KDR, which is K disagreement rate. We show KDR at different SRs when KGR is 2, 3, and 4. Typically, the K disagreement rate is about 0.03, and the KDR decreases with SR, but increases with KGR. Next is the performance of KNU model with the over-air data. We show the squared error between two Latin vectors at the three different positions of Bob, and also show the K generation rate. The squared error is a little bit higher than before because the real channel is more complicated than the simulated channel, and the K generation rate is greater than 2. If we choose K generation rate is 2 bits, we can get 2 times 16, which is 32 bits of Ks generated from single channel estimation without any mismatch. The KGR remains unaffected with the different positions. Let me summarize our work. Our model used two autoencoders to extract the common channel features and reconstruct the channel estimation of the other side. Our model mapped the non-reciprocal channel measurements to highly correlated case. About the K generation performance, we get a high K generation rate, which is greater than 64 bits per channel measurement, and a low K disagreement ratio, which is about 0.03. And in the future, we will consider the various adversarials in KNU model and how to deal with them. These are some references. Thank you for your attention. I'm looking forward to answer your questions.
Hello, thank you for the presentation, interesting work. My main concern about this work is you are using the autoencoder parameters as pre-shared secrets between the two parties. While, and the number of those parameters are too large, actually. You showed that it was 60,000, I think, number of parameters. So it's somehow, there are very strong security, classical cryptographic algorithms that if you have this amount of pre-shared secrets between two parties, you can generate keys with a very strong security guarantees. So what's the role of this channel here? So what I want to say is, at least based on my understanding, these methods using the fingerprinting or fingerprinting and these things is to reduce the amount of pre-shared secrets that you have between two parties. But now you're using a large amount of pre-shared secrets. What's the advantage of using the channel response
to generate the key, given that you can say that the autoencoder parameters can be considered as secret keys that are pre-shared between the parties.
You mean what's the advantages of using the channel to generate the key?
Could you go to previous slides? Go back. Yeah, in the next slide.
Next one.
Next one, yes. So here you see Eve needs to guess 60,000 parameters, right? So it means that Alice and Bob has already 60,000 parameters shared between them. They should know these 60,000 parameters, right?
Actually, they should just know half of this because they don't need the decoder part. They just need the encoder to get the latent vector.
Okay,
so
30,000 parameters.
Yeah.
And each parameter is I assume, is a float, for example, 32 bits. So 30,000 times 32 bits, it's a large secret shared between these two.
Yes.
So how do you handle this?
So, I mean, if it's a large number to guess, so it's difficult for Eve to guess these parameters. So Eve cannot know the parameters of the model. He cannot get the model, so he cannot generate the latent vector, and he cannot get the key shared with Alice and Bob.
I agree with that. Yeah, it's a very strong algorithm. So Eve cannot guess those parameters, correct? But my problem is, what's the first purpose of this type of key generation from channel or any general RF fingerprinting algorithm?
You mean, why do we need to use the channel to generate the key? Oh, it's an interesting question. I didn't think of this before.
But it was an interesting work. By developing this method, maybe it can be a good extension to this work.
Because for key generation, when I learned this definition, is first for the Alice and Bob, the transmitter and receiver, they have the same channel. They probe this channel and they extract the common feature of this channel and to generate the key. This is a common process of key generation.
I agree, but then why don't you use these pre-shared secrets, for example, to generate your key? You have pre-shared secrets. You can use a nonce, generate a key with classical or traditional cryptography.
You mean we use other information to generate the key? So
it's okay. I just wanted to think about that. So my main problem is, for this method, you need a large amount of pre-shared secret.
Yeah, but if the Alice and Bob, they can get the channel estimation, or they can get the channel estimation, and they have this model, they can generate the key by themselves. They don't need to share the key of the managed key, to save this space or something.
But this is a major problem in communication networks with a lot of users. For example, 5G or this type of communication, that you should have this pre-shared key with every user. If the keys are not unique, the parameters of the autoencoders are not unique, then Eve can also use the same parameters. If they are unique between parties, then generating this many unique parameters between all these users and pre-share them between. This is one of the major problems with symmetric key cryptography. And that's why people use, for example, public key that has their own problems and so on. But I think this is one of the weaknesses of this method, that you need this amount of pre-shared parameters between two parties to be able to generate key from the channel.
Yeah.
Thank you.
Thank you.
Okay, so if you have any other questions, you can discuss after this meeting. Okay, let's discuss our last paper, also the best paper, MR, iNight, Jane, the framework for edge deployment of the deep reinforcement learning on embedded software-defined radio.
Thank you.
Give me one moment. I'll upload it to the website and then download it.
First one. Yeah. No, the second. Yes.
Sorry.
Thank you. Good afternoon, everyone. My name is Keyvan Ramzanpur. In this list, the one before the last one. So I'm from Andro Computational Solution. We actually work on developing, including machine learning applications, different layers of communication protocol stack from physical layer to upper layers. This work is about a DRL framework for simulation and actual deployment of DRL engines to optimize some of the physical MAC layer challenges that we have in our system, mainly focused on ad hoc networks in jamming conditions. So I first give a introduction, a brief introduction, problem formulation, what we are going to optimize, what are our network conditions. Then we'll introduce our proposed in-house GIM framework for combined simulation over-the-air measurements for training a DRL agent, and then we'll see some simulation results, test running experiments, and conclusions. So the main problem we are solving in this work is dynamic resource allocation in ad hoc networks. This is a major challenge that has attracted many different machine learning techniques and deep learning to solve the problems. In the commercial section, we have unlicensed band that allocated to 5G and coexistence networks like Wi-Fi 5G networks. So the resource allocation, channel selection, power control are of important significance to performance of the networks. In our problem that has similar characteristics but more harsh conditions is an ad hoc network in jammed environment without a centralized unit to schedule and synchronize the users or schedule the users, that the users are autonomous and they would choose the channel and power control and the resources they require. Machine learning has been used in different areas, from physical layer in beamforming, waveform selection, to upper layers, frequency selection, spectrum sharing channels. And in 5G networks, there's a large domain of research on implementing intelligent RAN controllers, specifically in ORAN architectures. There have been recent works in applying reinforcement learning in resource allocation and beamforming, specifically waveform and channel coding selection within the context of ORAN. But our network, as I mentioned, is ad hoc network without this central base stations for scheduling. So that's a little bit more challenging problem to address. And there are no closed form solutions for solving the problem. That's why we have chosen reinforcement learning in contrast to a supervised learning approach, which is most common in addressing solving resource allocation, beamforming, and traffic routing protocols in networks. So in supervised learning, we would need a training set with known solution. So we have different possible conditions. The data can be collected either over the air or from simulations, and then we have the solution to that condition. We know that what's the optimal solution in that condition for the specific problem. But in this network environment that we are investigating, is this optimal solution either doesn't have a closed form solution, or it might not be available, the solution to us. So that's the main motivation of using reinforcement learning to observe the environment, to simulate the environment in any harsh condition that we want. We have jammers, we have non-synchronized nodes, we have multi-user interference, and then the problem is to increase the performance as much as possible. So that's the formulation of reinforcement learning. The problem is tactical networks, as in brute force tracking networks. We have very high node densities that are supposed to share the channel resources without scheduling. So the nodes are sensing the environment, and they should make the optimal decisions. We also have deployed these networks under the secure networks that called low probability of detection, low probability of intercept communications, which we use the CDMA communication with long spreading codes to address the LPDI property. So the requirement is, as you might know, is first, the nodes are non-synchronous, so they are not scheduled. They just sense and choose the channels. They should adjust the power. It's a power control problem that minimizes the interference, multi-user interference, maximizes the rate, or maximizes the outage capacity, so to speak, minimizes the packet drops or packet loss. And an important constraint in our work is also secure communication. So we have to consider the LPDI constraint. LPDI, well, there are many different approaches to meet the LPDI requirements by designing the optimal waveforms that cannot be intercepted or detected by an adversary. But at least in this work that I am presenting the results, we didn't consider the waveform generation part, but we know that the detection probability and intercept probability highly depends on the power, the received power by an adversary. So we want to minimize the transmit power as low as possible so that the probability of detection and intercept is minimized, but meanwhile, the packet drop or packet loss is also minimized. So these are two contradictory conditions. there is also jammer available in the environment. In our adversary model, jammer model, we are considering different frequency channels available to the transmitter and receiver nodes, while the jammer can also randomly jam partial of these channels. But we don't assume that jammer can jam all the available channels, because then that's not possible to transmit reliably. But the jammer is randomly jam partial. At least one channel is available that is not jammed. But in that condition, all users want to use that available channel that is not jammed. So we have two sections of this problem. One is a spectrum allocation. We have a few channels, let's say 4 unlicensed frequency channels in 2.4, 5, and 6 gigahertz, and then the users are supposed to choose the best channel that minimizes their packet loss. But they also, when they choose the channel, they should also control the power in a way that the multi-user interference is minimized, so that the network throughput is maximized. So this gamma relation is what we use as the reward function, part of the reward function in the reinforcement learning algorithm. We want to maximize this SINR for all users. So not a single user is not supposed to take all the resources, while all other users experience severe interference from this user. So this is the reward that all users are trying to maximize simultaneously. The constraints is quality of service constraints. The main components of this quality service constraint in this work is LPDI problem. We want to minimize the leakage or probability of detection or intercept of the signal by an adversary who doesn't have the knowledge of the spreading codes. So our assumption in this adversary model is the spreading code is not known, but the adversary can use cyclostationary property of CDMA signals to detect at least the signal. So the state space that we use at every agent includes the distances between every user and its neighbors in the ad hoc network, the channel state information that every node has from its neighbor users that uses the beacon signals that nodes periodically transmit to inform their presence to their neighbors. Those beacon signals are used to estimate the channel state information for every node and its neighbors. The interference that is sensed at both the transmitter and receiver side. So the point here is when that each transmitter can sense the interference, but because of the exposed node, hidden node problems, interference is not enough to make the optimal decision. But the receiver, the transmitter also uses the previous interferences that the receiver sensed and transmitted back in the ACK message to the transmitter. This is a part of the state information, and also the SINR, which SINR gives us a metric on whether the previous decisions were enough to keep the desired reliability, or it was so large that it can reduce the LPDI constraint probability. The action space is a joint scheduling and power control. By scheduling, what we mean by scheduling is a transmitter should decide whether to transmit or not, and when it decides to transmit, it should also choose the optimal power. So this is what we mean by scheduling. This is not the scheduling in, for example, cellular networks that the base station decides the resources and then users use it. This is the scheduling that a transmitter, based on all the state that it receives, it should decide whether to transmit or not, and when it transmits it, chooses the optimal power. And the reward is, as I mentioned, gamma is every agent try to maximize the SINR given the interference of all its neighbors. If the transmission is successful, and if transmission is not successful, then the reward is the interference that every node causes for its neighbors. It's represented by minus I in this reward function, the second line, that this I is calculated from the model. So this channel state information that every node has from its neighbors is used to estimate the interference that it causes for its neighbors, and that is the negative of also that interference is the reward when the transmission is failed. So we use an axiomatic method for action selection. Well, that's we started with DQN networks, but as you might know, that DQN networks has supports discrete action space. One solution was to quantize the power levels, the allowed power levels that the transmitter can choose, but that didn't provide satisfactory performance. But DDPG can be considered as a deep deterministic policy. Gradient method can be considered as is similar to DQN network, in which instead of epsilon greedy policy, a neural network model is our policy. So the rest is very, very similar to Q-learning. So that's why some people say it's DDPG is an extension of Q-learning from lookup table-based approaches to policy-based approaches. So using the DDPG, we could support the continuous action space. The output can be either transmit, and if the output is transmit, then it gives a power level between 0 and 1, a scale that determines the maximum power, determines the power that transmitter is allowed to transmit. So this is the framework, the simulation and combined simulation experimental framework that we have used to not collect the training data, but to train the DRL agent. So in the bottom part in blue, we have the network, CDMA network, including the physical and MAC layer, AI engines that are implemented on RT, SDR, software-defined radios that I will discuss this RT radios later, but this is an radio, software-defined radio with embedded GPU on them. So the neural network models are running on the embedded GPU of the SDR. Then the physical layer and MAC layers are in-house designed, CDMA designed layer that are able to choose the spreading codes with different lengths from 8 to 256 chips. And the middle, at the middle part, we have the NS3 simulation environment. NS3 is the common simulation environment for network models. We have also developed a CDMA module in NS3. I think Andrew plans to release, there are no previous CDMA module available in NS3. I think Andrew plans to release it in public, this CDMA module, but this is a fully in-house developed CDMA module for CDMA networks, ad hoc networks based on CDMA. And the upper part, well, Open AI Gym is a popular framework for reinforcement learning, but we here use an AI Gym NS3 framework, which is a glue between NS3 and OpenAI Gym frameworks that in which it's the same Gym framework, but the environment is the NS3 network model. Then we have a model optimization. So to run this trained model on the STRs, we need an optimization part that I will describe later. So this is the overall process of training and deployment with NS3 Gym framework. We have at the left side, we have the NS3 that the states are given to a wrapper for this NS3, or let's say an interface for the NS3 that we call it here NS3 Gym Gateway, that receives all the data from the NS3 model. Then it sends it to another interface in Python, that is NS3 Gym Proxy here, receives the NS3 data from NS3 Gym Gateway, and then it sends it to translate it into OpenAI Gym framework. Then the data is sent back to the training process, RL agent, and the reverse conditions that when Jim wants to send the comments to the environment, then it's going to NS3 Gym proxy interface that is sent back to C++ interface and then to NS3. So here are the software-defined radio, the prototype from DeepWave Digital. DeepWave Digital is the company that produces these radios. You see the pictures at the left side. These are 2x2 MIMO transmitter receiver SDRs with a Jetson TX2 processing unit on board. That is from NVIDIA, and you can, with proper optimization of the neural networks, we have deployed even very large neural networks on this Jetson TX2 chip, but it needs proper optimization using TensorFlow. So the training process goes, these are the hyperparameters that have been selected in the NS3 Gym environment. The DDP, the actor critic network is trained in the NS3 Gym with DDPG reinforcement learning algorithms. Actor is a 1-layer fully connected, and critic is a 4-layer fully connected with ReLU activation functions. And here is some training results that we see the reward. The reward, as I mentioned, is the average reward. The reward is either the SINR if the packet transmission was successful, or negative interference that every node causes for its neighbors. So this is the average reward for 3 different agents in a scenario. This is with over-the-air transmissions using 3 nodes of transmitting and receiving SDRs. As we can see here, well, depending on the initial conditions, it might happen that one of the nodes is transmitting large power, so the reward is large. It receives high SINR, but it causes large interference for its neighbors. So this black agent here, the black curve, is the agent that cannot compete with the red and green agents. And the other agents are in the middle somewhere. So this is one of the main challenges in this distributed learning conditions, that every agent is autonomously choosing the optimal decision for their power control. So then the solution, our solution was using the federated learning concepts, considering that every agent is a autonomous agent experiencing part of the environment, then the optimal solution could be aggregating the learning experiences of all agents. So after a certain number of iterations, so here it's the certain number of actions if every agent takes, we combine the models that every agent has learned, and then we copy with a hard copy of those models into each agent that this training process continues. And as we can see here, then all agents are achieving almost close performance in terms of the rewards. Although, comparing to this case, the maximum performance is reduced a little bit. Here, the maximum reward is between 5 and 6, but here the maximum reward is close to 4. So that's the compromise here by using the federated learning, this type of distributed learning that we are forcing all models to a common model. The maximum performance reduces, but at least all agents are able to transmit their packets, not with a very high rate, but at least all nodes are able to transmit. So I talked about optimizing the RL model. Here is the inference time of these models with different formats. If we don't do any optimization with the actor-critic model that I described, the inference time is around 2.3 milliseconds. But with an ONNX model, that is a format of the neural network that TensorFlow can generate, the inference time reduces to 14 microsecond. And with TensorRT that receives this ONNX model and do some optimization, well, I'm not very sure about the details of the optimization it does, but I think one of the main optimizations it does is the quantization of the parameters, and it
Excuse me, can you finish 3 minutes?
Sure. Yeah. It will be finished in 2 minutes. Then the inference time is reduced to 0.2 microseconds. So this is the over-the-air results. As we can see here, the packet delivery rate compared to a classical DCPC model, which is a distributed constraint power control algorithm. The power delivery is close. With the DRL agent, it's at 92%. With DCPC, it's 95%. But the DRL agent can achieve this power delivery rate with a much lower transmit power, average transmit power, which is 0.19 milliwatts. So in conclusion, we developed this NS3 GIM framework to train DRL agent with combined simulated in NS3 and over-the-air experiments, and trained, and one of the main conclusions from this work was to have a fair distributed learning. We need some mechanism, aggregation mechanism like federated learning, so that all nodes can have a fair share of resource allocation. Thank you. If there are any questions.
Okay, if you have any question, you can discuss with author directly. So we don't have enough time. So we have 5 minutes break, then we go to the last section.
So you have one more presentation in the next session?
Yes, the second one, this one is my next presentation.
Okay, yeah, so that's already done with.
You need the mic.
Sorry about that. Hello again. Now we're starting our session on ML applications and security, and we have 5 sessions, and we will start with the presentation entitled as "Can You Hear It? Backdoor Attacks via Ultrasonic Triggers" by Stefanos Kofas. And Stefanos, the stage is yours.
Hello, everyone. My name is Stefanos, and today I will talk about our work on backdoor attacks through ultrasonic triggers. But first, let's talk about a backdoor attack and what it is. For a backdoor attack in a neural network, we have to hide a secret functionality in the network that is activated when the input contains a specific property. This property is named the trigger, and it's the one that activates the backdoor. For the rest of the inputs, the neural network should behave normally and with a good performance to avoid raising any suspicion, so that the user still uses the poison model, and the attacker can also take advantage of this backdoor and the secret functionality. The adversary can embed the secret functionality in the network through three different ways. The first one assumes that the attacker can change a small portion of the training dataset, and it is called data poisoning. This is the most popular, and this is what we chose for our attack. And the other two are the code poisoning, where the adversary changes the actual implementation of the deep learning framework, and weight poisoning, where the attacker changes the weights on the fly of a deployed model. But let's see a figure to better understand this process. So we have the adversary that has to choose the trigger, and here the trigger is a small black square box in the lower right corner of an image. And also the adversary has to choose the target label that the poison model will give when the backdoor is activated. During training, clean samples and poison samples are used to embed the secret functionality in the network. As a result, on the testing phase, when clean inputs are fed into the network, the correct label is given. And when poisoned samples are given to the network that contain the trigger, the target label is given. Usually, we use two metrics to calculate the effectiveness of this attack. The first one is the attack success rate, and shows the effectiveness of the backdoor attack. To find this quantity, we have to poison every sample in the test dataset, and then calculate how many times we get the target label from the poisoned model. The other metric is the clean accuracy drop, which shows how the original task is affected by the backdoor insertion. To see this number, we have to train a model with a clean dataset and another model with a poison dataset, and compare their performance on clean inputs. So for our work, we saw that most of the works that are using backdoor attacks target computer vision, but speech recognition applications and actual products are already out there and are used by many people, like Google Assistant, Alexa, or Siri. Also, we know that speech recognition can be used for user authentication, and for that reason, we have to make sure that these kind of applications are secure. Only a few works have targeted speech recognition, but all of them used either noise or audible triggers that can be noticeable by the user. So the user may think that something is going wrong and may understand that an attacker next to him tries to do something bad with the neural network. In this work, we didn't exploit the non-linearities into the sound processing system because we wanted to see and to show that various risks are introduced by higher sampling rates in the speech recognition system. Our threat model is a gray box threat model, and we assume that the attacker has access to a few poisoned samples in the training dataset, and this has made is possible right now because recent trends in machine learning, like machine learning as a service, outsourced training, and crowdsourced datasets, help the attackers to affect this small portion of the dataset. However, if the sampling rate of the training dataset is small, the attacker has to use a higher sampling rate. And in that case, the threat model becomes white box. The trigger that we chose is an inaudible tone of 21 kilohertz. And as I said before, we aim to highlight risks that are introduced by high sampling rates. Even though the speech recognition models are not usually, they don't usually use some high sampling rate, there are very popular public speech-to-text APIs from Google and Microsoft that still support up to 48, I think, kilohertz sampling rates. We decided to systematically evaluate the attack's performance based on trigger characteristics, so we used both continuous and non-continuous triggers. We varied its duration, and we also applied it in 3 different positions of its training sample: the beginning, the middle, and the end. Here is an example of our trigger. In the upper row, we see an audio waveform of the word down, and on the right, we see the FFT of this exact training sample. On the second row, we see our trigger that is applied in the beginning of the signal, and its FFT shows a very strong component on the 21 kilohertz, that is 21 kilohertz. The last row shows our non-continuous trigger, which is a trigger that is broken into 5 pieces that are equally distributed in the 1-second training sample. Again, the FFT shows a strong component at 21 kilohertz. For our experiments, we used 2 versions of the speech commands dataset. One used the 10 classes and the other the 30 classes. But because this dataset is at 16 kilohertz, we had to upsample its training data to 44.1 kilohertz. We used typical values for our input features, which were the MFCCs, and also we used 3 models: 2 CNNs, one big and one smaller, and one LSTM with attention layer to see how different models can behave in this kind of attack. In all these cases, we didn't see big performance drop by the backdoor insertion, so we continued with our experiments. First, we had to choose how many poison samples we are going to use for our backdoor, so we tried some initial exploration. Here we see a graph that shows the attack success rate on the y-axis, and on the x-axis shows the poison samples that were used. The upper part of the graph of the figure shows the performance for the CNNs in all scenarios that we used. We see that with the CNNs, the attack is very successful, and for that reason, we decided to use less than 100 poison samples. Here we used a 20 millisecond trigger, and we knew that maybe with different kind of setups, the attack success rate would be even higher, so we couldn't see any differences if we chose above 100 poison samples. On the other hand, the LSTM is more difficult, and the attack behaves differently, and the LSTM shows robustness against this poisoning attack. For that reason, we had to explore a little bit more why this is happening, and we ran additional experiments and tried to plot the attention weights to see what is going on. So here we show a training sample with a trigger, which is highlighted by the red rectangle, and below we show the logarithm of the attention weights for this exact input. We see that when we use 200 poison samples, the attention weights are not focusing on the trigger and are focusing on the actual useful information of the signal. However, when we use more than 200, so 400 samples, we see that the attention focuses exactly the time of the trigger in the training sample. For that reason, we concluded that the attention layer is more robust to small changes in the dataset and needs more effort from the attackers to make it to affect it in this way with this attack. Some general findings that we have is that the attack success rate is positively correlated with the trigger duration, and because our attack is inaudible, an attacker can use 1-second trigger to create a very strong attack that doesn't need many poison samples. Also, for a smaller perturbation, we saw that it's better to break the trigger into multiple parts so that more windows of the MFCC calculation are affected, which results in a stronger attack. As a general observation, we saw different behavior between the different models that we used, and for that reason, we concluded that the backdoor attacks may be used for a good purpose, and this purpose is AI explainability, as we can see how a model learns and what it learns. For example, in the LSTM network, we saw that when the trigger is applied in the end, this position results in a more effective backdoor, and this was not the case in the CNN network, in the CNNs. After this exploration, we decided to try this attack with actual hardware. First, we verified that 2 mobile phones, one Android and one iOS, could interpret sounds that are in the near inaudible frequencies. We did that with a spectrogram, and then we came up with the following scenario. We had an application that recognizes simple words, and we have a speaker that talks so that the application recognizes the words. However, if an adversary plays the trigger, a backdoored model should give us the target label. This is the interface of our application. We forked the TensorFlow Lite example from Google's GitHub. We did some changes. We had some support for MFCC calculation, and we used a poisoned model. In this example, we saw that this application recognized the word yes with 88% certainty. We installed this application in a Huawei P9 with Android 7. Maybe it's old, but the phone is old also. But this is not a problem for our experiments. In our experiments, we played the trigger through 2 different devices, one laptop and 2 home cinema speakers that are also very cheap, I think. And we tested, and we used 2 different scenarios. In the first, there was silence, so we just played the trigger and no one spoke. And in the second, the user used the phone to actually use the application. In the silence, we found out that the backdoor could be successfully activated, but the laptop speakers are not very strong, so the backdoor was activated only when the phone was placed right next to the laptop. However, with the home cinema speakers, we could activate the backdoor even with 1.5 meters distance, which was an interesting finding, of course. However, when the user actually used this application, the voice of the user was strong enough that could overcome the intensity of the trigger that was placed from our device, that was played from our devices. However, we saw with additional experiments that when the user placed the phone in a little bit bigger distance, or when the user talked a little bit, when the user didn't talk loud enough, the trigger could still be activated. For that reason, we concluded that the threat is practical, and we have to make sure when we use these kind of applications that our models are secure. So our work has also some limitations. First of all, if a lower sampling rate is used by the application, our trigger will not be effective, as it will not be understood by the sound processing system. However, there are some applications like music classification that need this kind of sampling rate and may be affected by a backdoor attack. Also, we know that a low-pass filter could filter out our trigger But this, if it is a hardware filter, could introduce additional burden for the developers. And if it is a software countermeasure, it may introduce some additional overhead on the performance of the application. As a future work, we plan to test our attack against countermeasures that are both backdoor specific or the ones that I mentioned before. Thank you for your attention. And yeah, I'm ready for questions.
Thank you very much for the presentation. And is there any question? No one? Okay. Okay. Just I want to. Could you come back to the sampling rate? That slide, please.
What sampling? What slide?
Or is one?
That.
I remember here. Okay, that one.
Okay.
I just want to say why you use why you use such iterations. What is the motivation behind that, and what are the three position, or not, for example, two, not four?
This choice was a little bit arbitrary, but we wanted to see yes, we wanted to see if both small and big triggers, how this can affect the attack performance. So we started from something small, and we ended up with something big that could take most of the signal that was played. The positions, again, for example, other works that do backdoor attacks in image try different positions that can be in the corners, in the middle, and for a wave file that is sound, we chose 3 different positions that cover everything, both the middle, which is usually where the speech is, and also the two ends that maybe they are not containing any useful information. So we wanted to explore like many setups, and we came up with these numbers.
Thank you very much for the answer. Then we can move on the next presentation. The next presentation may come. Now we continue with our next presentation, entitled as Undermining Deep Learning-Based Channel Estimation via Adversarial Wireless Signal Fabrication by Tao Hu, right?
Tao.
Huh? Tao Wang, okay.
Hi, good afternoon, everyone. So in this work, we investigate several deep learning assistant channel estimation and try to uncover some potential vulnerabilities. So first, let's talk about the motivation. So as we know, the channel estimation is actually the vital step for the wireless communication for the reliable and efficient data transmission. Usually that we will use channel estimation to identify the wireless channel distortions and then use the estimate channel to compensate received signals for the message decoding. So traditionally, we usually will use some statistic algorithms like the least square estimation, the maximum likelihood, or the minimum mean square error to estimate channel. Recently, as the deep learning become more and more popular, it also shows that we can incorporate the deep learning into the channel estimation procedure to further improve its accuracy. So here are some examples about how we can incorporate deep learning into the channel estimations. The first one that we can directly like convert the estimated channel matrix into the image to take advantage of existing machine learning techniques. We can use the image super resolution algorithms or the image restoration method to increase the channel estimation resolution and reduce its noise. Or sometimes that for the rapid changing wireless environment, we may not use we cannot use a big amount of data set for the training. So some papers also show that actually that we can even use untrained deep neural network to further improve the accuracy. Some other techniques have been proposed, like for some specific purpose, like for the deep amount, it is used to improve the channel sounding procedure for the downlink MU-MIMO network. And for the short payloads, because that for the large antenna arrays, so usually we will assume that the length of the payload is larger than the number of the antennas. But as the number of antennas keep increasing, sometimes the assumption does not hold. So this technique has been proposed to reduce the requirement of the payload length. And for last one, that when we do the channel estimation, we may not always get perfect channel estimation. Sometimes we will get some imperfect channel estimation, and in traditional techniques, we may not have many ways to improve that. But with the LSTM, we can define the temporal correlations between the consecutive channel estimations and further improve its accuracy. So it has shown that the deep learning had indeed it's capable to improve the efficiency and accuracy, but its security and reliability still become the main concerns. Because especially when the deep learning has been intensively applied in different tasks. So in our work, we would like to investigate all these existing deep learning assistant channel estimations and try to uncover some potential vulnerabilities. Here are some attacks that have been proposed by different works. The inference attacks, adversary attacks, poison attacks, Trojan attacks, or covert communications. And our work will focus on adversary attacks. So here is our attack design. So the objective of our attack is try to create a malicious perturbation to affect the channel estimation at the receivers. So it seems that it's very similar to the adversary machine learning. We will use some game to learn a substitute model and then create a perturbation. But when we examine it carefully, we find out that actually that there are still several differences here. The first, the design of the traditional adversary machine learning will benefit from the knowledge of the original input. So basically that we will always have the input, and based on input, we create the perturbations, and such that we will mislead the prediction of the model. But in our designs, especially for real-time wireless communication, you cannot always intercept the signals and then do the perturbation and then send it out. So it will introduce the extra latency and make it impractical. Also, unlike some other data domains such as the computer vision, the radio signal need to be manipulated during the propagation that will rely on the accurate synchronization. So I think that it needs nanosecond level the synchronization if we need to do some real-time processing. That also make it infeasible for most wireless communications. So because of these reasons, we want to find some other ways to launch our attacks. So as shown here, that instead of to create a perturbation to specifically lead to some predictions, we would like to create a universal adaptive perturbation that could affect the channel estimation for all possible symbols. Like no matter what symbols have been sent, we can always mislead the channel estimation. And so here is more details about how to formulate our problems. Like I said, that instead of customizing the perturbation based on the specific input, we want that our perturbation could be suitable for all the possible symbols. So the intuitive way to do that is we can send larger jamming signals that we can overwhelm the transmit signal, such that the receiver will get a wrong estimation. But such kind of the trivial mechanism will not work because will be easily to be detected by the receiver because the receiver will experience some unexpected signal power. So instead of customizing such kind of signals, we would like our the perturbation is suitable for all the possible symbols, and also that we want to minimize the interference signal power, such that it can hardly detect by the receiver. Here's the overview of our designs. We can see that first we will have a perturbation randomizer, because as shown here that we actually format our question into optimization questions, and if we don't have any random things here, that we will always generate the same interference signal here. So if we always send the same jamming signals, then it will be easily detected by the receiver. So what we do is that we want to add a bit randomness here. So the randomizer is like some initial vectors that is used by a lot of the block ciphers. So it will add some randomness here, and every time if you have different initial vector, you will have a different perturbation. So the perturbation, the generator will be used to generate the interference signal. And then for the last one, the Gaussian normalizer, because that even we add some randomness, but sometimes that the jamming signal is still like some it does not follow very follow that uniform distribution or some other distribution, then it can still be detected by the receiver while some statistic examination. So we want to enforce our interference signals as the Gaussian distribution, such that even the receiver will do some statistic examination, but still he will figure out that, oh, this is some general channel noise, and it cannot detect the attack. Now let's talk about some preliminary results of our work. So we consider the following three different channel estimation methods. The first one is the LDAMP-based channel estimations. Basically, that this is existing techniques. We will convert our channel matrix into images to further remove the channel noise. And the second is the DIP-based channel estimation. For this one, we will use some untrained prior model to improve the accuracy. And for the last one, LSTM, we will use LSTM to learn the correlation between the consecutive channel estimations to further improve the accuracy and resolve the imperfection of channel estimation. So here's our result. We can show that when we don't to launch any attacks, you can see that the channel estimation are very constant. So every time they will get some similar results. Also, that I should mention here that because in our experiment, we basically will use some static environment. So the channel does not change very much. We did the experiment in the midnight, and also we tried to make everything static there. So and then when we apply our attacks, say that then the channel estimation will become quite different from each other. So I think the channel distance for all these algorithms are larger than 0.5, which means that basically they're quite different. It's basically it's something like some random the channel estimation. And here is the evaluation of stereotypes, also undetectability. So we can see here that this is the result that when we apply like initial random the vector and also the Gaussian normalizer, when we apply all of them, we can see that even the receiver applies the statistical analysis, but still that they can hardly detect the attacks. Actually, that if we don't apply like the Gaussian normalizer or the initial vectors, then our attack can be easily detected by the receiver. Now let me conclude our work. So in this work, we investigate the multiple different deep learning-based the channel estimations and try to exploit their vulnerabilities. And we develop an attack that does not rely on the knowledge of the input. Actually, that's our attack works on all possible inputs. And that's one that we built an MU-MIMO network with the software-defined radio network, a platform, and contact the over-the-air, the real-world experiment, and to validate our designs. Thank you.
Thank you very much. Thank you very much for the presentation. Is there any question?
So thank you for your talk. So I'm very interested in how to generate the adversary sample, because if attacker doesn't access that neural network model, so what's the method to generate this noise for the neural network for the channel estimation? Another one is, what's the difference between this generate signal and environment noise or interference?
It's basically that because when we talk about it, if the receiver adopt like the deep learning with their channel estimations, so they will use the machine learning techniques, deep learning techniques, try to improve the accuracy. So what we do is that we will generate some perturbation that it's very I feel like it's very interesting that though it's very small, but for the receiver, still that when they do the estimation, the result, the estimate result will be different.
Okay.
So like,
do you need to assume that attacker knows the model?
The model.
Yeah.
So yeah, for the channel estimation, because channel algorithm should be public, right? Everyone should know the model. So we hear that we will assume the white box attacks. So that's also one difference between us, between our work with the previous works, or between previous adversary machine learning works, because they will always assume black box attacks. But here, we will assume that all these channel evaluation methods, machine learning, were known to all the the transmitters in the network.
Okay,
so that's
thank you.
everyone can do that.
Yeah,
Thank you.
Okay, then we can continue with the next presentation.
I mean, I already have it open, so.
Thank you. Good afternoon, everyone. This is Yang Hu, and I'm the second-year PhD student from Electrical and Computer Engineering at Rutgers University. And it's a great honor for me to stand here to present our work on behalf of our team. And our topic today will be a machine learning-driven analysis of phantom E911 calls. In today's talk, I'll introduce the motivation and contribution the problem formulation methodology results, and use cases of results. So first, what are E911 calls? E911 calls is an enhanced version of the 911 system that allows the emergency service to act more efficiently because it can provide the dispatchers with the location of the callers. Then what is phantom E911 calls? Phantom E911 calls is the E911 calls that are made accidentally and automatically when there are no true emergencies. So first, E911 calls is really important because it can provide the location to the dispatchers, which the timely emergency services rely on. And it will cause a waste of resources because there are high volumes of phantom E911 calls that pose a drag on cellular networks and take away from critical resources. And this can lead to really severe situations. For example, it is to be blamed for death. From the Fox News, we heard 2 people have died after mysterious phantom 911 calls flooded the 911 emergency dispatch system in Dallas, Texas. So we can see how crucial it is for us to study the phenomenon of phantom 911 calls because it will it will lead to this kind of deaths and waste of resources. So we should learn to find out where the issue lies and try to take possible actions to mitigate this kind of issue. And for the literature review part, there are multiple existing works have discussed the impact of increased mobile network complexity on its users, management, and the maintenance. Some works discussed about the causes at the network level, such as anomalies in base stations, exhibiting some rock behaviors or say phantom behaviors, or cells experiencing performance degradation due to the mobility. Such as there are also other anomalies such as the sleeping cells, which behave rockly. So the other works discuss about the causes at device level. An early investigation by a major US network services provider studied anonymous data, and it indicates that phantom calls are most like device level related. However, there are challenges of our study in phantom E911 calls. First, the mobile networks are advancing fast and resulting in ever-changing smartphone hardware and software. And second, some mobile networks contain the mobile devices from third-party vendors, which add further complexity to the network. And also, there are enhanced smartphone software without testing. Last but not least, there are also some data challenge from the machine learning aspect, which means we have huge difference in data sample size. More specifically, the data is unbalanced. The number of the normal calls is much bigger than the number of phantom E911 calls. So guess that if we were given some call records data, what can machine learning do to help with finding approaches to mitigate the issue about phantom E911 calls? Is phantom E911 calls related to the device level or the network level or both? So our objectives are listed here. First, we should understand the important features in call records data that contribute to a device initiating phantom E911 calls. And we should understand how much the responsibility is on device features and network features. Also, we should try to find some way to or to take some actions to mitigate the problem of phantom in-L1 cost. So we can save the important resources and avoid the tragedy. In our work, we pre-process the data and we separate the features into device and network level features. Then we encoded the data. Second, we implemented 2 diagnostic models. It is their k-nearest neighbor model and decision tree model. We classify and verify our hypothesis, which I will go over later. And the results showed that only a handful of features are strongly correlated with the device's ability to initiate the phantom in-L1 cost. And we also provided network operator policy suggestions to mitigate the problem of in-L1 phantom cost. In problem formulation, we discussed about the hypothesis and data and our machine learning methods. So based on our prior knowledge, we propose 2 possible causes that can, or say 2 scenarios. Say the causes can be device level and network level. First, in the device level, we hypothesize that the device misconfigurations contribute to a device going wrong. In this scenario, the device data features can help us to solve this issue and find out where the issue lies. And in the second scenario, we think the network issue may have occurred along the pipeline of LTE network, which we can see in figure 1. And UE is user equipment, and PDN is the network, and MME is the mobility management entity. So in this scenario, the network data features can help us to find out the issues, and we can give some suggestions based on these features. And figure 2 shows our data partition. And for every data sample, or say for every core record, we split the feature into network level and device level. Considering our data is imbalanced, and for KNN algorithm, for this supervised algorithm, we prefer a balanced data. So we applied the appended data in setup 1 in the KNN model. And we use Lime, a Python package, to analyze the feature importance. And in setup 2, we apply the decision tree model. And considering decision tree, the model intimates the human thinking, so it can help us to understand and interpret how the feature works. And then the output of the 2 models are labels. And we labeled the imbalance, we labeled the phantom in-L1 cost as 1 and the normal cost as 0. To introduce the methodology, it will include 3 parts: data preprocessing, data encoding, and model setups. Providing all features in the raw data are categorical. So firstly, we need to clean the data based on the following criteria. We drop the features that consist of missing values across all data samples, and we drop the samples that include missing values across most features. Also, we drop the redundant features, which means they have only 1 value across all core records, including both the phantom in-L1 core records and also the raw model IMEIs. IMEI here means the device identification. And we also drop the deemed meaningless features for the current problem scenario. Considering we have a bunch of encoders here, like binary encoding, Bayesian encoding, label encoding, one-hot encoding, and hash encoding. But we finally applied decimal encoding because comparing to the other encoding methods, decimal encoding is suitable for categorical data, and it reduces dimensions, and it requires less computational resources. And decimal encoding is actually the base n encoding when we choose n is equal to 10, and it allows us to convert the categorical data into the base n into the decimal integer. So figure 3 shows the pipeline of our KN model, which is based on the device level data. And here is the data preprocessing and the decimal encoding. And in step 1, we applied K nearest neighbor. KNN is a simple supervised machine learning algorithm used to solve classification problems. And KNN achieves classification by comparing the different labeled data samples, comparing the number of different labeled data samples around the target data, which is called the neighbors of the target data. And this is the pipeline of our setup 2. And these are also the same thing about the data cleaning, preprocessing, encoding. And for decision tree, figure 6 shows the simple example of decision tree. And for here, it's an example for deciding whether to play badminton or not. We can see each node represents a feature like the weather, humidity, and wind. And the branch represents outcome of that node. The leaves of the trees is where the final decision is made. So the decision tree intimates the human thinking, so it helps us to interpret the features, how the features work. That's why we choose decision tree here. And before we came to results, I would like to talk about the criteria we choose to measure our model performance. We choose average recall and average specificity here. First, I should introduce the definition of these signs, of these denotations. TP here denotes the number of true phantom inline calls, and FN denotes the number of false normal calls. TN denotes number of true normal calls, and FP denotes the number of false phantom inline calls. Sometimes we call it false positive. And here, recall represents the model's ability to accurately label the phantom call records in testing data. And specificity here, model represents the model's ability to label the normal call record data in testing data. And also it's important to realize that we should separate these two scores instead of simply using the average classification accuracy, because our goal is to test the model's ability to detect or say diagnose the phantom inline calls. But the average accuracy cannot do that. This is the results of setup 1, which is based on device level data of our KN model. And we use cross validations here. From these results, we can say our model is generalizable, and it even get the high accuracy in our testing data, in our new testing data. And from the detected log IMEIs here is the devices identifications. From the phantom IMEIs, we can help the customer care team to only focus on a narrow list of possible log devices. And in our experiment, there are around 25% IMEIs were tagged as, or say 25% devices were tagged as log. So it will allow the proactive action on the identified devices probably before the phantom inline calls is triggered or say is initiated. And this is the result of our setup 2. It's based on the network data and is the decision tree model. From here, we can see we got the high accuracy, the high average recovery and average specificity here. And we asked a question, is there any subset of the network features consisting the most decisive power of classification? So we testify that by a further decision tree model. And in setup 2, we verified that feature MTMSI. MTMSI is the MME mobile subscriber identity, and it is associated with MME group. And MME here is the mobility management entity. It presents a key control node for the LTE access network. And considering MTMSI is associated with MME group, and we confirmed feature MTMSI occupied around 99% importance in deciding or say diagnosing the phantom ENL1 cause. And we know it's associated with MME group, so we can find some geographic location about the phantom cause. So this will be helpful for us, or say for the customer care teams to locate the phantom cause. And we came to the last part of use cases of our results. In setup 1, the results help us in real networks to predict the device that have the potential to go rogue. So such devices can be suggested for discounted upgrades to solve the software issues. For example, if you bring your device, which is detected potential rogue or say potential phantom, then you can get the discounted upgraded to avoid the device to cause some phantom ENL1 cause. So this can save the network resources and reduce the volume of phantom ENL1 cause. And second, the setup 2 helps in the scenario when detecting a cluster of devices that are behaving in rogue, so that customer care teams can identify the behavior and place appropriate checks and balances to handle them automatically, rather than having to manually figure out the pattern in such cluster of rogue devices. So this can save huge amount of troubleshooting time for customer care personnel and network engineers, rather than having to manually figure out the pattern in such cluster of rogue devices. And thank you for your listening. Any questions here?
Presentation. Is there any question? Then it is better to move to the next presentation because we already 20 minutes late. And thank you very much for this great presentation again.
Which one?
Top one.
Yes.
All right.
Thank you.
The fourth presentation is on beam pattern fingerprinting with missing features for spoon contact detection in millimeter wave networks. And the presenter is Ya Yang.
Yes.
Right?
Hi everyone, I'm Ya, and I'm from ECE department at George Mason University. Today I'd like to talk about our paper called beam pattern fingerprinting with missing features for spoofing attack detection in millimeter wave networks. I will introduce it from the following 5 aspects. And in the first section, I will start from introducing the millimeter wave communication in 5G and NetG. As we all know, due to some emerging technologies like millimeter wave and beamforming, the 5G and NetG can provide us higher speed, lower latency, and larger bandwidth. However, due to the broadcast nature of the wireless medium, the wireless network is subject to identity spoofing attacks, which can be launched simply by impersonating the legitimate users through changing its IP address or the medium access control into the legitimate client. In that case, the faked data frame with compromised key can be transmitted to the access point. Typically, existing works about the spoofing attack detection based on wireless features can be divided into two types. The first type is RF or hardware fingerprinting, and second type is the channel or location-based detection. For the first type, this type of method can tackle the co-located attacker. However, it usually requires a higher-end analyzer to extract highly precise physical layer information like offset, frequency error, or the IQ samples. So this type of method would imply a higher cost or deployment overhead. And for the second type, this type of detection could imply lower cost or deployment overhead by easily extracting the signal strength from the device driver. However, this method is very vulnerable to co-located attacker. In that case, we'd like to know, can we have a detection mechanism that can tackle the co-located attacker and imply low overhead at the same time? So in this paper, we explore unique physical layer information that is SNR traces connected during pin pattern sweeping or initial access, and we regard it as our millimeter wave RF fingerprinting. We choose this type of physical layer feature due to the following two reasons. Firstly, it can be easily extracted from device driver in the off-the-shelf device, and it could be distinguishable among different devices and different channels due to possessing both RF or hardware and channel or location properties. So this type of physical layer feature can be used to counter co-located attacker with low cost. Like in this figure, you can see the client and the access point are following the beam pattern sweeping process to identify the best transmitter sector and receiver sector beam pairs. So during aforementioned processes, the SNR traces between the client and the access point at different beam pattern pairs can be extracted like in the middle figure. You can imagine it as the matrix. And in this matrix, each row and each column is an SNR trace. And then, if we fix the receiving sector at RX3 and are connecting the SNR traces all the time, we can see in the third figure the SNR curves of the same device with a fixed receiver sector at the same location could show a similar trend, although they have different amplitudes. However, existing works propose the efficient beam management to reduce the communication overhead. Their basic idea is to only test a subset of the beam patterns. However, this type of method would lead to the missing features. Like in the first figure, you can see the client delete the transmitter pattern 1 and transmitter pattern 3, and the access point eliminates the receiver pattern 2. So the SNR traces extracted from that mechanism could miss the features like in the column TX1 and column TX3 and the column and the row RX2. In that case, if we still fix the receiver sector at RX3 and are connecting the SNR traces all the time, we can see the values at index 1 and index 3 are missed in the third figure. So in conclusion, this type of efficient beam management method would cause two problems. Firstly, only SNR traces with missing features would be probbed, and also the missing patterns could be random according to different settings and scenarios. In that case, existing works for the spoofing attack detection based on machine learning don't work here. To our best knowledge, missing features are not well studied in millimeter wave eye fingerprinting. So here we investigate some methods aiming at tackling the missing features and corresponding open issues here. The first method is to just abandon the missing features directly. However, this type of method would miss useful information and lead to longer collecting time. So someone proposes the imputation approach, like replacing the missing values with the mean or variance. However, this type of method doesn't take information related to the class and the missing features into account. So someone proposes the probabilistic matrix factorization, yet restricted to non-random missing features. In that case, our work proposes a machine learning-based spoofing attack detection approach that can tackle missing features. To introduce our solution for missing features, I'd like to introduce the missing pattern block firstly here. The missing pattern block is a block of SNR traces that share the same missing features. Like in this figure, you can see the second one and the third one both miss the features at tx1 and tx2 and txn, so they belong to the same MPP. Then we define the total number of MPPs is n, and define W sub n as the weight matrix learned by the number n MPP. In that case, we can formulate our feature learning problem as follows. The input is the x of n, which represents the samples of SNRs in the number n MPP, which are collected during sector level sweeping. And the output is y sub n, which is the label indicating if there are spoofing SNRs or if it's normal. Specifically, in the training stage, the attack samples are generated from GAN. So on the other hand, we also introduced the multitask learning. We also formulate our problem as the multitask learning problem. Specifically, we consider the SNR traces that have complete features as the main task, and the traces miss some features as the auxiliary task. So we can formulate the objective function as equation 1, in which the first term is the cross entropy loss function, and the h is the sigmoid function of our detection model for classification. And we also add the second term as the regularization term. Obviously, we can see that the equation 1 is convex because the Hessian matrix of cross entropy loss function is semi-definite, and the Frobenius norm has the convex property. So we can obtain the optimal solution from the equation 1. However, to avoid the possible vanishing gradients caused by the Frobenius norm and the sigmoid function of the equation 1, we optimize the equation 1 with ADMM, that is the alternating direction method of multipliers. So with the perspective of ADMM, the equation 1 can be reformulated as equation 3, and the phi sub m is our introduced auxiliary variable. Then the augmented language function can be obtained as equation 4, and we also present the update rules as follows. The basic idea of ADMM is that it alternately optimizes each of the unknown parameters like W sub m, phi sub m, and gamma sub m until the convergence is achieved. If you are interested in the updated details, you can refer to our paper and also reference one, which is very classical paper for introducing ACM algorithm. So finally, we can get the final weight from the weighted sum of all W sub m, in which the ratio sub m is a proportion of different MPBs contributed in the training data set. So this figure demonstrates our system model for training and prediction or detection model. Firstly, we assume the efficient beam pattern sweeping is performed. So we select some subsets for beam pattern sweeping. Then, from this collected SNR traces, we can construct corresponding MPBs. Specifically, here we introduce the multitask learning by regarding the traces that have the complete features as the main task, and the rest SNR traces that miss some features as the auxiliary task, and incorporate the main task and auxiliary task to train our sigmoid function and optimize it with the ADMM. Then, in the detection stage, when new SNR traces comes in, we firstly construct a corresponding MPB and input it into our trained detection model to determine if it's normal or a spoofing attack. So to evaluate our model, we utilize the SNR traces collected from Talon routers under the settings of the SIM orientation, in which there are 36 default transmitting sectors and a fixed receiving sector, so that the feature dimension is 36. And this table presents the statistics of data in which A1, L1 represents the SNR traces of one router at location 1, and A2, L1 is connected by the other router at location 1. And also our hardware and software setup are like this. Firstly, to evaluate the efficiency of our model in detecting spoofing attacks, we firstly train the detection model with 200 samples and test the model on 5,000 samples, and both of them have the complete features. And this experiment can achieve almost 100% accuracy. Then from this experiment, we can obtain the half amount of features that have greater weight, and we regard them as our baseline features. So to construct the training data set, we firstly, we randomly discard 5 types of subset with the same ratio. And to construct the test data set, we randomly discard 10 types of subset with same ratio. So from this figure, we can see the training time of our model is increasing linearly with the training sample size. However, the accuracy always keeps almost at 100%, even with very small sample size. So it means our model can be applied in the scenario for spoofing attack detection. It requires high effectiveness and timeliness. To evaluate our model in detecting co-located attacks, we regard the A1, L1 as the traces of legitimate user, and A2, L1 as those of co-located attacker. And this table demonstrates the performance of our model, both trained and tested on data with all features. Then, similarly, we select the half amount of features with greater weight as our baseline features, and their indexes are like this. So this figure presents the receiver operating characteristics curve of the model on the traces that meet all these baseline features, and they are with different ratios. Our training sample size is 1,000, and the test sample size is 5,000. Specifically, the missing ratio of training sample is 50%. It means the half amount of the training samples have the complete features, and the rest miss all baseline features. And we also set up different missing ratios for our test samples. From this figure, we can see our model can handle that all those different types of all those different scenarios with different missing ratios. So it means our model can be effectively and robust. So for the final evaluation, we compare our model trained with complete features and missing features. Initially, the training sample size is 200, and they only contain the complete features. And the test sample size is 5,000, and it meets all baseline features. Firstly, we add several SNR traces that meets all baseline features to the initial training samples, with the size ranging from 100 to 800. And then to compare its performance with the model trained with only complete features, we also add several SNR traces with that only contain the complete features with the size ranging from 100 to 800. And those figures demonstrate our model can achieve better performance. So it may mean that it's not with our model. It's not necessary to train the model on only complete features, and so thus reducing the requirements on data quality. In conclusion, we are the first work to handle SNR traces containing the missing features for millimeter wave RF fingerprinting. And we also ensure a global optimal solution by developing an algorithm based on ACM and multitask learning. And our experiment results show that we achieve highly efficient spoofing attack detection, as well as handle the co-located attacker with missing features. For our future works, firstly, we'd like to give some insights about which features to enforce and which features to discourage. So we envision that there can be a certain domain knowledge for performing the efficient beam pattern sweeping. So in that case, we can just choose the subsets that can maximally affect the classification and also reduce the computing overhead. And secondly, we'd like to research the impact of mobility on missing features. Because in dynamic scenario, the channel fitting would be changed dramatically. So we'd like to know if there are some other regulations on missing features in mobile scenario, like in mobile devices. So thank you for your listening. That's all my presentation.
Is there any question? Hi, this is Paul. Could you restate why the features you have used are qualified for spoofing detection, like in the very beginning of your talk?
You see the efficient beam pattern sweeping.
Why the features like the SNR segments are used or gathered in the sector sweep? Why can that be used for spoofing attack detection? I did not fully understand.
Oh, you see the other features. Oh, you see why we use this type of physical layer information?
Yes.
Oh, okay. Firstly, actually we use the SNR traces collected during sector level sweeping because it can be easily extracted from the device driver, and it possesses the channel allocation property and also the RF or hardware property. So it can tackle the co-located attacker. But for the other physical layer information, like I mentioned, the offset frequency error or the RQ samples, they usually require higher end analyzer to extract highly precise that feature. So it would imply higher cost or deployment overhead. But our features can be extracted simply from the device driver. So it implies lower cost and overhead, and also tackles the collocated attacker. Yeah, thank you.
Let's continue with the next presentation.
Thank you.
The DT, right?
Yes. Cable.
Okay, now we are our last presentation, and Kevin will make the presentation entitled as Virtualization with Machine Learning.
Thank you. So hello again, everyone. So I'm going to discuss in this presentation some of the applications and importance of digital twin, especially in the area of network, 5G networks, IoT networks, and future security frameworks in the network. So I will first discuss some of the basic definitions and classical applications of digital twin. Then I will discuss the modern emerging applications, digital twin, and at the end, I will discuss the role of digital twin implementing a zero trust architecture as the requirement of next generation security frameworks. So a digital twin is basically a probabilistic simulation model that mirrors the lifetime of a physical entity. A physical entity can be any sensor, device, process, and anything. And by lifetime mirror, we mean it reflects the current state of the device and environment, the historical state and conditions of the environment. And one important feature of digital twin models is the prediction. Prediction can both refer to future, that what might happen in future, and also it can refer to the past, in which under different control processes in a system, under different stimuli, what would have been the response of the system or condition of the system under those inputs. So in summary, the digital twin is the real-time data-driven modeling. The major difference and characteristic of digital twin is the real-time part, that it receives data in real time, updates the model in real time, and feeds the state of the environment and devices to the control process. So classical roles of classically digital twins has been used for monitoring of remote distributed system. We have IoT sensor nodes distributed over physical space. So digital twin was initially developed by in the proposed and developed in the Industry 4 revolution for monitoring the devices and to deploy event detection logic. So event detection can be simple threshold detection based on if the state of the environment or state is a scalar, or it can be any deep learning or neural network model if the state of the environment is a high dimensional state. And it has been also used as a communication middleware. One of the major features of digital twin initial stages of development was interoperability of heterogeneous devices, IoT devices. So digital twin could be used because of this interoperability feature to as a communication middleware between different devices. So the devices, as we see in the lowest plane, would send the data up through a network that can be a 5G-based IoT network. And then the models of these devices can communicate using over the HTTP protocol, over the internet network. And then the responses can go back again to the devices through the corresponding digital twin model. So the devices do not need to have the capabilities to directly communicate with each other. They communicate with their own digital twins communicate with each other, and then the response would go back to the devices. So this was one of the main motivations, this interoperability for development of digital twin in the initial stages. But the most emerging and advanced applications of digital twin can be compared with the architecture of 5G networks. That is, separating the data plane from the control plane. So the main reason for digital twin is deploying a control process over a distributed system. So instead of deploying these control processes, logics, and function on the physical space, we can just send the data, all the measurement data and state of the devices through the IoT network to the digital twin models, and the control process is deployed on the digital twin, which is called the virtual space in this diagram. So this is critical for programmability and scalability of the control processes. Multiple parallel control processes can be deployed on cloud platforms while they can be updated in real time, they can be upgraded, they can be changed, or even multiple control processes on the same physical space for different objectives with different control objectives, for example, security, resource allocation in 5G networks, or maintenance in the industrial plants can be deployed on the cloud in parallel while there is no requirement for reconfiguration or changes in the physical space of the devices or processes. So this is one of the main tenets of software-defined networking in 5G networks, that because the control plane is separated from the data plane, now the control plane is deployed on the cloud. So now we have this cloud-based 5G networks that everything, all network functions are just deployed on a cloud, while the hardware, equipment, base station, and everything is the same thing, working in parallel with other networks, other 5G networks, or other 4G previous generation networks. So another interesting insight into digital twin is planning versus learning. So the concept of planning in reinforcement learning is updating the policy using simulated experience of the environment. So in this diagram, in the circle, we see the learning process. So we have a control policy, it interacts with the environment, we observe the state and performance metrics or reward returns from the environment, we have function approximations for value function, state function, action, queue values, and then we update the policy. So this is the learning process. We directly interact with the environment, and based on our observation, we make updates to the control policy, either with temporal difference or Monte Carlo-based techniques. But in this process, if we look at this vertical diagram, we can, when we observe the state of the environment and the actions that we send to the environment, the performance metrics, we can construct a model of the environment. And using that model, we can generate simulated interactions with the environment. So we don't, this can be either a separate learning process, or it can be combined with that learning, the online real-time learning process. We are learning in between the learning processes. We can also feed the simulated experiences. So this is called the planning part. So if you want to compare digital twin with this planning, digital twin is this model learning part. We receive all the data from the devices in the environment, we construct the models, and this digital twin would generate simulated experience. So this is digital twin can be considered as a parallel to the physical space that for the updating the policy, the control policy, we can use both data. Maybe, for example, the learning part can use temporal difference models. This digital twin, because we can run multiple steps in the future, or until the end of the task, or in n-step temporal difference techniques, we can simulate n steps in the future and combine that with temporal difference techniques that we use in the learning process. So this is one of the great advantages of digital twin. But to make distinction in the system science, we also have the concept of planning, system planning. It's a little bit different from this planning that I discussed. This is the planning versus learning in reinforcement learning. In system planning, we might want to include new components to the physical space, but before deployment, we want to do all the verification steps to make sure that the design, the placement, and the cost is optimal, and then really deploy on the physical space. So this is another application of digital twin that we call here system planning. So this, for example, we want to deploy base station or smart grid source, energy source. That can be either a design model, or it can be a real system but running in a lab in a simulated environment. Then the control process can treat this model as a physical entity that is really deployed, and use those data from this model in combination with the real physical space to explore for policy exploration purposes. And the last but not least application is off-policy reinforcement learning. So off-policy reinforcement learning will have theoretical advantages that has been discussed in the research domain in computer science, but it has also one important practical advantage. And the practical advantage is deploying on-policy reinforcement learning on real systems in real time is challenging because the policy is not, because of the large variance of the updates, the policy is not allowed to change significantly from the optimal operation and performance. So one important example is RAN Intelligent Controller, RIC, in the Open RAN architecture of 5G networks. So RIC is a collection of algorithms, either near real-time or non-real-time, XApps, RApps, that allows deployment of AI engines to manage different resources, for example, resource allocation, beamforming, routing, traffic steering, and everything. But deployment of these models in RIC is significantly restricted. First, the models should be trained offline. Then there is an extensive set of verification and a test set that these models must pass. And if it passes all the tests, then they are allowed to be deployed in real time. So it's challenging to deploy in real-time on-policy reinforcement learning in such a system. But off-policy technique is a plausible solution for this type of application, because we have a behavior policy that is interacting with, is our current, let's say, it's our current policy that is interacting with, deployed in the physical space, interacting with the environment, And based on these observations, we have a target policy that we just update the target policy based on the observations we get from interactions of behavior policy. And then, well, there are different approaches how and when to update the behavior policy. The behavior policy is usually updated less frequently than target policy, with either soft update or hard update. Like in DTBG algorithms, it's soft update. In DQN networks, it's hard update of the policy. But the point here is this target policy is is being trained in digital domain area, and when we decide to deploy it on the physical space, we use the digital twin models for verification, run all the tests that we require to verify that it passed all the tests, and then we can update the behavior policy with this target policy. So this is one of another important applications. So the envisioned architecture of digital twin for future large-scale distributed systems, we show here as a 4-layer architecture. The first layer is just the models, the model construction or model learning that for every physical entity, there is a digital twin model that receives the data and construct a model of the environment of that device and the device state itself. So this is updated in real time. It can also simulate the. So this is the first step that decouples the physical state from all the upper layers. As I said, the control plane and data plane or physical plane. Then the next layer is federated learning. So federated learning is important in this architecture because, as I discussed, one of the critical and important features of digital twin is simulation models. It's able to predict what will most likely happen in future, or what could have happened in the past under different control policies or under different stimuli. But every physical entity, every single device has a limited observation of it. It's partially observing the environment. But a distributed set of devices over the entire space, every device is observing different states of the environment. If we can aggregate the learning experiences of all these devices, we can come up with a more comprehensive model that has the capability of observing a larger portion of the environment state. So this can significantly help in predicting for the prediction capability of digital twin models. And the layer 3 is interlinking. The most important part is the interlinking model, layer 3. An interlinking model is the global model of the environment that is significant for the objective of control policy. For example, if our control policy is controlling the security of the state, so this model is the security state of all devices and the authentication processes, the authorization of links and so on. If we are controlling the Okay, sure. Okay, sure. After this slide, I will go to the final proposal for the application security, and I will conclude. So the interlinking model is global model of the environment for the objective of the control process. And then we can have the simulation environments, as I discussed, parallel simulation environments that are simulating the environment at different states, different inputs, and so on. So then an interesting application of digital twin is deploying a zero trust architecture. What is zero trust? Classical security frameworks are based on, or heavily relies on authentication. So authentication or identification, verifying the legitimacy of the identity that a user or device claims, is called authentication. So when authentication is successful, it provides a trust basis for other entities in the network that can trust this user. So whatever this user is doing, we trust it because authentication was successful. But the next generation security framework was based on zero trust architecture. Zero trust means we don't trust user even if authentication is successful. So that's why the name zero trust. So authentication doesn't provide trust. So that's zero trust. But then what should we do? So if we don't trust, what we should do? Then we have authorization. In classical systems, authorization is heavily relied on authentication. But here, we should have, in zero trust architecture, we should have a separate engine that authorizes individual accesses. And this is called the microsegmentation. And well, how should we authorize the DoD, the Department of Defense, has a document that that introduces a reference zero trust architecture, defines 7 pillars of zero trust, that every pillar should provide appropriate data to the authorization engine that we can authorize accesses. This is the application of digital twin. So every zero trust pillar, user, device, network environment itself, all of them are modeled and monitored based on the data that we receive from those. We model the security state, and all these models feed the authorization engine. And then authorization in zero trust architecture becomes a control process. We receive data, make a decision, observe the effect on the network, and this process continues. So this is how, thank you. Digital twin is important for security. Thank you. Yeah. If there are any questions.
For the presentation. In fact, we finished our time and now we are in break. If you want, I can take one question. Okay, just one single question. Then you can continue.
Thank you for the talk. My question is about the simulation in the digital domain. You said that these devices, physical devices, will try to find models of their environment. And the simulation, I'm curious, like, is the simulation model for each layer going to get updated as time progresses? Or, I mean, are these devices also supposed to be in a cycle for evolving the simulation model?
Yes, the models are updated in real time, but the real-time models are used in a separate engine to just run. For example, consider Markov decision process in reinforcement learning. You can take multiple paths in this Markov decision processes. Every node in this Markov decision process is a digital twin model. Okay, so this is digital twin model. This digital twin model is updated, let's say in a vertical direction, is updated real time, but in the horizontal direction, we can take multiple parallel paths in this MDP to simulate the environment.
Okay, thank you.
Thank you. Thank you.
Thank you very much for your presentations and thank you very much for your listening. Now we are in the break. After the 10-minute break, there will be a panel.
organizers of the workshop here. And just due to time, I'll just hand it off to each panelist to briefly introduce themselves. They'll give a quick talk on this topic, and then we'll open it up for questions and answer. So first, let me pass it over to Dula, who's joining us remotely, since we get you up on screen here. So go ahead. Dula, can you hear us? Can I get a thumbs up or something if you can hear us? Do we want to switch it over to one of the ones in the room here? Yonman, we have your laptop set up here, and we'll just need to switch this over.
Okay, good afternoon, everyone. It's my great pleasure to be on this panel. So I'm going to briefly talk about my research related to the privacy-preserving machine learning over wellness networks. It will be like the 5 or 6 minute talk. So this research is motivated by the fact that the data are increasingly generated at the edge of the network. By 2025, there would be about 463 exabytes of the data generated every day. And 3/4 of this data will be generated at the network edge. So this data can be used to enable new products using AI, such as autonomous driving, mobile health, smart manufacturing. And the traditional way to utilize this data is to learning in a cloud-centric systems, so that we send the data over a band-limited network and to a remote cloud. And the data are trained over the cloud to get some good AI models. And there are privacy and efficiency concerns in this paradigm. For example, the privacy is that huge amounts of user data needs to be transmitted to a remote cloud. And the efficiency issue is that the bandwidth limited network usually takes a long time to transmit those large volumes of data. And because of that, a new learning paradigm is to move this training over the cloud to the front end, and so that we can now keep the intelligence at the edge of the network. And that is what we call the federated learning paradigm. So federated learning enables us to train an AI model collaboratively without centralizing the data. And the basic idea is that we keep the data locally to the network edge, and we only share the model updates. And by keeping data locally, raw data never shared outside of each individual's device, and that provides the privacy by design. So, for federated learning, there are a lot of good applications, such as autonomous driving and the predictive maintenance, where the data are generated at end devices, such as the IoT devices or autonomous vehicles. However, in order to enjoy the benefits of federated learning, there are a few core challenges, such as the security and privacy concerns. So, although for security concerns, since the data now resides at each user's, so it's very hard to detect and decide whether the data are sanitized or trustworthy. And for privacy concerns, although the data are not shared, the model updates are still contain sensitive information, since they are trained over those sensitive data. And there are also statistical and system heterogeneity issues. For example, the devices participating in the federated learning can have different hardware computing powers, battery powers, and wellness connectivities. And so in order to ensure that the learned model can be trained at a low latency and have a good accuracy, we need to address these statistical and system heterogeneity issues. And in addition, federated learning involves a large number of communication rounds between the end devices and the remote cloud, and that leads to expensive communication. So if we want to address these challenges jointly, we need to consider the trustworthiness, the system efficiency, and the accuracy. However, jointly consider this is going to make the problem very complicated. And for example, achieving differential privacy may delay the convergence of your learning algorithms. And delayed convergence means you need to transmit more in much more communication rounds, and that is going to impact your communication efficiency in advance. Because of the time limit, I'm going to briefly examine the privacy issues in federated learning. And I have already talked about that by keeping the raw data to the edge, we provide the privacy by design. But there are still attacks existing showing that we can actually peek into those model updates to get the raw data. For example, using a logistic regression model, for example, there have been attacks that shows by using the stable dose of a patient, we can actually predict the fit genotype of the patients, and by using a model inversion attack. And in order to defend against those attacks, a state-of-the-art approach is to using differential privacy. And the basic idea of differential privacy is that we want to guarantee that by looking at the model updates, you cannot differentiate, you cannot tell whether a person participated in the training or not. And a classic way to achieve differential privacy is to add the noises to the shared model updates. The challenge here is that usually we want to have a low privacy budget, which quantifies how much privacy is lost during the process. But in federated learning, you have a large number of communication rounds. That means you have a very small privacy budget at each communication rounds. And a small privacy budget leads to a larger noise magnitude. So this is going to result in low model accuracy of your learned models. So another challenge here is that when we are training, a lot of time we are interested in the deep neural networks. Those are large models, we can see that on the top right figure that actually the magnitude of the differential privacy noise actually increases as your model dimensionality increases. And however, your useful information actually does not increase much, no matter whether you are training a small model such as ResNet 18 or large model such as ResNet 152. So in this case, when your model becomes larger, your noise is increased proportionally, but your useful signal does not. And that means for larger models, you have lower signal-to-noise ratio. And that makes it even more challenging when we are considering differential privacy in deep neural networks. So one of our work is to address how we can achieve high model accuracy and strong differential privacy guarantee at the same time, and pushing the state-of-the-art work of the privacy accuracy trade-off to a higher curve. And one of our papers is on how we can leverage the redundancy in these neural networks to achieve this goal. And so for here, I would want to explore another opportunities that is really interesting in this area. That is, we observe that the edge servers actually only needs to know the sum of individual model updates in each round of the federated learning algorithms. So because of this key observation, we propose that we can actually leverage the over-the-air computation in the wellness communication domain and ask all the edge devices to simultaneously transmit their model updates to the edge server using analog transmission. And this, by exploring adjusting the waveform superposition property of a multiple access channel, we can simulate a secure aggregation over the air. And that leads to both high spectrum efficiency and fast mode aggregation. And in addition, originally, when we consider differential privacy in the application domain, we usually add Gaussian noises that we generated artificially. But in the wireless communication, we can actually harness the channel noise in over-the-air computation to preserve privacy. And that allows us to have two birds and one stone. And on the right, we show the basic illustrations about how over-the-air computation can help. On the top, it basically shows, in a traditional way, each edge device transmit using a different bandwidth spectrum. And on the bottom, we use the over-the-air computation so that all the edge devices are communicating over the same, and at the same time over the same spectrum. And their signals are superposed at the receiver side. And so here is a brief description about how we can harness the channel noise for differential privacy. So on the top, we show you a Gaussian MAC channel. So the X here is a transmitted signal, which you can consider as the modals. And the modal X goes through a channel, which we use H to represent that. And then it is superposed by the channel noise. And that gives us a received signal Y. And we can actually leverage this channel noise by adjusting the transmitter's power. And that allows us to adjust the level of noises superposed to each individual input XIT. And with that, it basically allows us to harness the channel noise for differential privacy for free. And that is, so here is the summation of this approach. First, the intrinsic channel noise protects the privacy naturally without artificial noise addition. And second, the wireless signal superposition acts like a secure aggregation in the physical layer and improves privacy. So that's all for my brief talk today, and feel free to ask me questions after all the panelists present. Thank you.
Thank you. We're gonna go ahead and move on to the next talk now. Do we have Dola on? We can go to. We can go ahead and have Dola go then. You can leave that up here. Hold on, Dola, we can't hear you. Dola, can you hear us? We don't have your audio yet. Just hold on a second. It's on our end. Okay, go ahead and try again. We can hear you a little quiet. We'll just you can grab a seat. Yeah, she'll go now.
I'll try without the headphones.
Okay, we got you now. So you can go ahead and get started.
Can you hear me now?
Yes. Yes, we can. Can she see us?
Can you hear me?
Yeah, we can hear you.
Okay, I'll try to mute myself or make as low as possible so that I don't hear myself. That's not very pleasant. So, okay, so thank you for inviting in this panel. And so let's see what's current scenario it is right now for wireless security. Since we're talking about wireless security, how is it different from regular security aspects? The main challenges in wireless is that wireless medium is a broadcast medium. It's easy to eavesdrop and interfere and jam. And the other part is that we also have to support low power IoT devices, which normally when we talk about hardware cryptography, that is not the case. So the opportunities in what lies in the fact that the wireless channel is reciprocal and wireless channel decorrelates beyond half of wavelength. So also wireless channel and hardware, each one of them is unique. And using these opportunities, we have been working on a ton of research is going on in wireless physical layer security that involves both encryption, key generation, authentication that involves utilizes or harnesses the diversity in the wireless channel and the hardware. Also, to address the challenges of the wireless broadcast media, we have been also working on the various defense strategies against the adversary, which can be active or passive, both the cases. Now, when we look at deep learning is not new, but it has been more popular these days, mostly because of the availability of faster GPU and CPUs, and the data sizes have become much larger. And that's where the accuracies have gone better and better these days. And that's when we are moving more towards using deep learning for wireless security. So how does the future look like? To me, the future looks like that we will have stronger adversaries. They will be more capable, computationally more capable. They should be able to use deep learning algorithms. Previously, we were not thinking, 10 years back, we were not thinking of adversary who were capable of using deep learning algorithms. Also, we believe that the future will be with more antennas, and they will be omnipresent. So on the other hand, to counteract these adversity, what we need to do is to create stronger security algorithms, but also with the challenges that we have already described. So with those challenges, meaning that we will have to support IoT devices, which may not have enough capability to handle higher complexity algorithms. So possibly to push some of those towards centralized part of the base stations or the access points of the world, utilize the diversity in the channel and hardware in an efficient way so that we can still guarantee some or move to a more secured system in low power devices. Also, we can utilize or bring in some new cross-layer algorithms that can help enable stronger security system, which we haven't looked at because mostly the cryptography lies in the application domain, physical layer security lies in the physical layer, and they normally don't talk to each other. So what does deep learning brings in? Deep learning is overall a data-driven approach. In many cases where we have devised other algorithms, the total number of parameters involved in a system might be intractable. So these are the systems where we expect to see benefits coming out of deep learning models, where a data-driven approach might be useful or can help to reach better accuracy. Often, some of these algorithms are difficult to find a closed form representation, or often are computationally complex. So we end up doing a lot of assumptions and make the problem simple to actually implement in reality. So deep learning should be able to help in some of these cases as well. Also, our deep learning models are unique for any of these cases because previously algorithms have been mostly one-size-fits-all scenario, whereas for deep learning, we can retrain models for different specific scenarios, which can definitely yield better results. And of course, there are new areas of research that can show up, which we haven't looked at before. Like, for example, RF fingerprinting, we haven't looked at much before, but with deep learning, it has become a very interesting topic of interest now. So with that, we would like to revisit Kirchhoff's principle. And so what is Kirchhoff's principle? It was in 1883 that that was published in 1883 that the security algorithms should be public knowledge, except for the keys should be private. And all the secured systems today's like AES, DES, all of these still follow the same Kirchhoff's principle. Now, all Kirchhoff's principle is mostly trying to look at encryption algorithms, but that can be extended towards any kind of secured mechanism. That the algorithm for security is known, but how it is implemented, what is the key, and all of those remains unknown. But now we are talking about machine learning algorithms or deep learning algorithms that we train and retrain depending on the hardware, depending on the channel. So do we need to revisit Kirchhoff's principle? And that brings us some other new interesting ideas or topics that if a baseline model is known, is it how difficult it is to derive a specific model that is in use? So we can say that, well, the deep learning model structure is known to Eve, except the parameters are not known. But if Eve has enough data, can she recreate those deep learning models themselves? That's the question that we have to answer in future. And to just wrap up, I would like to talk a little bit about what kind of research that we have been working on in our wireless security domain. So one of the work that we are working is encryption and decryption. So we are generating neural networks, or we are creating neural networks that can generate cipher signals from known from bits. So it takes in bits and gives out signals. It goes through the channel, then the decryptor actually decrypts it. Now, how we implement it is in the paper. I wouldn't go into the details, but the interesting part is, again, cross-layer encryption, which has not been done much before. We are now trying to bring in these features which can be implemented with some knowledge of the channel. The next work that we have also worked on is covert communication. And this is another work where we have used adversarial neural network to create a signal that looks more like a hardware noise. This is another avenue of research that has opened up. And the last one, which is also a WiseML workshop, is a key generation problem, which key generation has been done for many, many years. It's not new. But this is something that we have been working on. We started working on looking at the deep learning algorithms. How can we extract more number of keys from the channel than before? So that's the main essence of this particular research. And with that, I would like to stop here, and we'll be happy to take any questions later on after everybody is done. So.
Okay, thank you, Dola. We'll go on to the last talk now we can switch back over to the room. And then we'll open it up for questions after that.
Okay, Governor, I can share my research related with artificial Internet of Things for our fingerprinting in adversary environment. Okay, today I first talk what is the AIoT, and also I discuss the 3 applications regarding the security. Okay, first one is, okay, current we have the different IoT device. Also, we use the deep learning. And the current very good trade is we can combine that together. We call this is the artificial Internet of Things, AIoT. So for the AIoT, we have several applications, okay, from smart home to smart health to indoor localization or to the human-computer interactions. Okay, what's the challenge part if we use RF signals for the AIoT system? Okay, if you check this figure, okay, there are several fundamental challenges for RF fingerprinting solutions. And the first one is if we consider the RF signals and we consider like the different domains, if we collect data from one room and test data in another room, we collect data one day and test data another day. So there are domain and target shift in the RF signals. Okay, second part is that there's some noise interference or adversarial attack for that model. Okay, currently this become also very fundamental challenge part. And the last one is that for RF signals, it's challenge to collect label data for some technique of some signals. Okay, so we need to discuss these several 3 challenge and corresponding solutions. And meaning focus on 3 examples for this. And the first example is for wire localization. Okay, so for wire localization, I think our workshop there are several work from the voice-based, Wi-Fi-based, several wire localization work, and we can use RF fingerprinting. And my previous work used the Wi-Fi SSI for indoor localization in this area. Use the different feature for the indoor and localization. And we can consider use the traditional model from the autoencoder. I proposed this work in the 2014, and also to extend to the convolutional network, long-short memory. To current, we consider more robust model like the deep gauge process. Okay, what's the channel part for indoor localization? Because we use RF signal. Okay, first one is if we consider SSI, I think today also we have one paper discussed how to attack channels information. And if we attack that, definitely if we use the SSI for indoor localization, and which will generate high indoor localization errors. And our current work validate that SSI-based indoor localization under different white box and black box attack. And we show just the basic that attack will influence indoor localization accuracy. Second part is that currently from the Wi-Fi localization, we can transfer to 5G indoor-outdoor localization. And we can consider from the SSI data, if we had multiple antenna and with large bandwidth, we can transfer to the ADP, that image. And for this image, if you see the figure, if we add a noise and get a similar that image, but feed that image to the neural network, and which get the very high errors. So we proposed some model-based, like the neural ODE model, to improve the robustness under adversarial training. Okay, and this is the first example. Second example, we need to show how to use RF fingerprinting for the human-computer interaction. I show like a human pose estimation and a human activity recognition. So current solution is we know we can use the sensor-based, which current transfer to the Wi-Fi, radar, acoustic-based. And one solution, can we estimate 3D pose? So Recently, one solution is we can use the camera help that RF signal to estimate that location, 3D post locations. But there is also the challenging part. I think I mentioned that in the beginning. And if the domain change, for example, a person in a different location, and also the different angles or collect different persons. For example, here in the same gesture, just in a different environment, you can see that figures show the different values. How to handle that? I mentioned that we can use the data augmentation. I think today we have several talks discuss that. Here we proposed one data augmentation combined meta learning to augment the data set and also transfer to unsafe domains. We can see our performance will increase. Okay, also consider the security part. I think last speaker also mentioned, okay, we need to guarantee privacy efficiency. And here is we need to consider, okay, if some user upload some fake model to the server, also will influence that accuracy. Okay, how to guarantee that accuracy? Also consider the trade-off that the fairness and also the robustness system. For this one, also one solution is we can use the clustering or grouping and to group different users in a different group. Some user just the normal user and upload correct models, and some user to upload the fake models. Okay, last one I just show current. I collect several data set. Okay, I publish data set in my web page, and this data set including RF fingerprinting data set for the different. Later I give the example to show that from the Wi-Fi based, LoRa based, RFID based, and UAV based. You can use this data set to do some research and to validate your machine learning, deep learning model. Okay, and also this web page also lists several data set for the modulation, for the communication system, also for the indoor localization with different signal, and also wireless sensing, for example, gesture recognition, human activity recognition based on different radar device or Wi-Fi device. Okay, here is give example for this, and we use the several different Wi-Fi the RF fingerprinting the data set, and for this table, some data set from the USRP, some data set from just the commercial Wi-Fi card. Okay, so if we have that enough data set, then we can use that to validate some idea. For example, current our one project is that we want to show can we validate for the different domain. If we collect data, for example, what's the definition for the domain? If you collect data for one day and adapt to another day, if you collect data for one place and then adapt to another place, if we just use traditional like CNN model, you can see that performance is not very good, especially for the target domain. And if we consider like someone use the data augmentation, here we show if we consider like domain adaptation or use the meta learning per type of neural network, and then we can get a very good performance. For the target domain, also we can keep very high accuracy. Okay, so current I also list the future work and for the database, the RF fingerprinting under the attack. For example, current work is how to generate high quality on the data set, how to collect large scale data set. Like the ImageNet, our community also needs the large data set to validate or propose some new model. Second one is which feature, and we can use like someone use IQ, someone use the spectrogram, and which feature and which technique, new device we can use for our fingerprinting. How to design, multimodal and cross-modal. I think I give the example to show that we can use the camera help the RF signal for post-estimation. And another way is that we can see today we also have one paper and to clarify the technique, protocol, and modulation. And currently we can collect the data from the Wi-Fi, LTE, 5G in this close area, how to validate that model. Another way is that how to address dynamic environment. This is still a fundamental challenging problem. There are no the unique solutions, and also this need to consider new solutions address that. Another way is that how to handle some attack. Okay, currently we know there adversary attack also important for the, we can say, inference on the neural network. So how to improve that? Just adversary training, that's not enough. Okay, next thing is that in order we have the different technique, different device, billions of IoT device, we need to collect the data, how to design that robust fed learning to keep privacy, to improve robustness, and to consider fairness for the user. And also last one is, in the future, also we need to propose the model-based deep learning, okay? I think compared with the image-based, also the ImageNet, there are no domain information, but for our wireless scenario, we have channel model, we have the modulation or the coding. We need to add that information, okay, or use that information to get like the gain or other thing to generate data set or to design some neural network model. Thank you. This is my talk.
All right. Thank you. And I think in the interest of time, and John, you didn't have any additional comments, right? You talked on this topic this morning. So as you saw, the panelists, they have some common themes here. You see their work has shown a lot of promise in using these emerging techniques in deep learning and moving out to some of the new stuff. You saw discussions on channel and being able to mitigate environment, federated learning as a common theme here. But we are about at our time here. We need to wrap up at 5:30, so we can take a couple quick questions, maybe for the panel, and then we'll have to move the rest of the discussion out into the hall. But does anyone have a quick question that they want to go ahead and ask? Why don't you walk right up here?
Hello, I want to ask Dola one question. You mentioned that you plan to use neural networks for encryption and decryption. Do they have any benefit compared to the techniques that we actually use for encryption and decryption? I'm not sure that I see why we should use neural networks for this kind of task.
When we look at encryption has been done in the mostly using bit and modification of bits. When we have don't can hide information or the objective here.
Dola, you're coming in a little choppy there. I think we've got your slides up on the screen, so we've got your email there, and maybe we'll send a question that way. You're largely broken up as you're talking, sorry. All right, let's leave that up for a second so people can take down the email. Any other questions for the panel? And I guess we'll constrain it to the panelists in the room. All right, if not, then we can informally, if you've got any questions, you can ask them out in the hall. But thank you all, and thank the panelists for attending and pulling together those briefs and giving it to us. And I think that concludes WiseML for this year. So thank you all for making it a success and submitting your papers and participating in this community.